So it's not clear how it goes in the next few months.
Here on this top of the hill, we have one engineer and 2 students are directly infected and residing in campus itself. So
yeah, go ahead.
On this top of the hill in a remote place, if situation is bad, then I don't know. There are other places, of course, it is, and Pune is, of course, on the top. So
yeah. These 10 people are the ones who are mainly living in campus, but about 35 people in total. Most of them security guards, cosmetic people, etc., who do not live in campus, but they have also been affected. People among the people who live in campus, about 10, 12, including a student, postdoc, so on. Yeah, it's not a good situation.
Yeah, it will keep on increasing as per expectations till May first week, and after that, if at all Indian Janta cooperates, then it will start declining.
Yeah. I think it. The way I understand it is certain class or certain clusters of people who interact very frequently with each other. Pass it on to each other, and that creates one wave. And when that group of people get herd immunity, that wave goes down, and then the slow transmission to another class of people, another set of people who interact with each other more frequently, they get infected.
Right.
And then that creates a second wave and so on. And in that whole process, the virus itself is changing its character.
Yes. You're right.
So unfortunately, I was not able to attend most of this meeting because, there's a critical design review of suit and VLC payloads happening this week. So it was meant to happen on Tuesday and Wednesday, but then it went on till yesterday.
Yes, you mentioned earlier. No, thanks that you got a time slot free, at least for this thing, because this is a national gathering and it's very nice to just listen from you about what's going on towards TMT. And
Sure. Yeah, I would have very much liked to give the other talk also. Unfortunately, this week ended up being so packed. Critical design review is such a major milestone for the payload that we were all very busy preparing for it. And and this committee was headed by Sri Kumar and very senior members, including Shyam Tandon and other deputy directors of ISRO and so on. So it's a very senior level review.
Right.
It's not an easy one.
Yes, I understand.
Yeah. The
board meeting was good, I believe.
Yeah, we have cleared most of the points. So there might be a closeout review after this because some actions have been identified. So once we close those actions, then there would be a small separate review to close those actions formally.
Yes. That CCD thing, I think we need to
move forward. Yes.
So, did you tell that engineer at your end to kind of prepare the draft MOU?
No, I have to do it. That is why it is taking time.
Okay.
I can't just because it is a MOU kind of document. It cannot be deputed in that sense.
Sure.
Some technical content can be got from engineers and so on, but other content has to be drafted by me. So I will get to this.
Sure, thanks.
this corona issue, a lot of people are not coming anymore to the office. Almost all outside people who are staying outside have been asked not to come to office.
Yeah.
And people who are in campus have been asked to come only on some rotation basis. Not everyone comes every day. So everything is going very slow these days. Hello, Dipankar. I see you have connected. Is that Dipankar or is it just your connection?
It's just we are using his account, so his name
okay.
is visible.
So we have 5 more minutes, so we can
Yes.
wait for some time. Yeah.
Hi, Dipankar.
Sure, it is not Dipankar. It is just Dipankar's account being used. for the Aries connection. So I also thought it was Dipankar connected.
Yeah. Good morning, Ishwar, and good morning all. Pratik, are you there?
Hello. Yes, I'm here.
Yeah.
Yes.
Yeah. Very good. Very good. So I think 1 or 2 more minutes we can wait, and then we can.
Sure.
Ishwar, you have a very nice background. You have become an adaptive optics person now.
Yeah. I don't know the adaptive optics.
He doesn't want anyone of us to use that background. He wants it to be unique.
Yeah, he doesn't give that to anybody. Is it?
Exactly.
Yeah, laser shooting off his head.
After a lot of hard work, I got that. So are there people attending from Aries Auditorium, Shashi, or
No, actually, we have 3 positive cases in the campus right here in just last 5 days.
Oh.
So first day on Monday itself, it was instructed to everybody that whosoever is interested, please join remotely. So there's a blank empty room where myself, my student, and 1 technical person, only 3 of them are rather allowed.
Okay.
So we are maintaining social distancing, but numbers are increasing.
Yeah.
And here it was not expected that cases will come, but now we have 1 engineer and 2 students.
Yeah.
And I think some 10 would be hidden, including myself. I don't know.
Yeah, very difficult times.
Yeah. Yeah, so I think.
Yeah, we can see the auditorium camera with empty seats.
Yes.
Yes.
Thank you.
Ah, that's very nice. It's kind of some warrior, tribal warrior. Pigeon or hawk by the side, and good.
Yeah, it's a photo is taken by one of our staff here.
Oh,
I mean, like Angchuk, this guy takes bird photographs. He's a very good photographer of birds. So this photo is taken by him. Angchuk takes amazing photographs.
Also, there is the option to change background quickly.
Yeah, it is just 1 minute. You go to video settings and you can change background.
Okay. Yeah, so now we are more than 15. Soon will be 20 and more. So I think let's stick to time. And good morning all, and I welcome you all here on the 5th day of this workshop. And the theme of today is dedicated for upcoming observational facilities and future plans. And under this theme, the first session would be chaired by one of the associate members, Pratik Majmudar. So I request Dr. Pratik Majmudar to now take care of the session and start with. Dr. Pratik, please.
Yeah, thank you very much, Dr. Pandey. And very good morning to all of you. And welcome to the morning session of the final day of the workshop. We have 3 talks in this session before tea break. And the first of that would be delivered by Professor Rama Prakash from IUCA on the 30-meter project. Professor Rama Prakash, please. I'll ping you. So it's a 40-minute talk, so I will ping you after 35 minutes.
Okay, thank you, Pratik. And can you hear me very well?
Yes, I can hear you. Yeah.
Hello. My video froze for a moment. Can you hear me very well?
Yes.
Yes.
Can you hear?
Oh,
Yes.
okay, thank you. Let me first of all thank the SOC of this meeting for giving me an opportunity to present the project status and update. I was not entirely sure about the audience, but assuming that there will be at least a fraction of the audience would be not very familiar with the project, I have a section which explains what this project is about and what we are trying to do with it in India and the overall global picture of where it is right now. So that is the overall structure of my talk. Of course, this project is a national effort in India. It is led by 3 institutions, ARIES, IAA, and IUCA, which forms a consortium, and then there are many other partners. And it's an international program. I will explain the details as we move forward. So this is a view of the Giant Magellan Telescope. So why am I showing Giant Magellan Telescope while we are talking about TMT? This is just to put the entire context of what the world we are living in terms of an astronomy. We are really approaching the golden period of astronomy in the sense that the facilities which are going to come up over the next 10, 20 years are so powerful and so technologically advanced that they are going to allow us to ask questions which it was not possible to do till now. Of course, the questions could have been asked, but there were no means to find or even make attempts to find answers to those questions till recently. Now, these new facilities are going to change that, and a lot of new discoveries are going to be made in the next several years. So one such facility which is going to come up is the Giant Magellan Telescope, which is a 25-meter telescope, effective diameter, and it is going to be built by an international partnership. The next one I've shown here is the 30-meter telescope. I will not spend much time here, but I will go into details after the next slide. The third telescope is the European Extremely Large Telescope. It's a 39-meter diameter telescope being built by a partnership in Europe mainly. And they are going to set this up in the Southern Hemisphere, like the Giant Magellan Telescope. And TMT most probably and almost certainly will go to the Northern Hemisphere. So among these 3 telescopes, there is enough light collecting capability, as illustrated in this slide, that would exceed what already exists in the world. For example, in this slide I've shown on the top row are telescopes which are roughly 4 meters in diameter. And then the next row are 8 meters in diameter, then 10 meters in diameter in the next row, and so on and so forth, 8 to 10 meters here. And then on the left side, the blue ones are in the Northern Hemisphere, and the yellow-orange ones are in the Southern Hemisphere. So if I look at just the Keck telescope, mark it with the circle here, with the 10-meter diameter circle, just the European Extremely Large Telescope is going to increase the collecting area, where we can kind of almost fit all the other existing telescopes within that area, at least in the northern hemisphere, if not probably in the southern hemisphere, or just the other way around. But so if you have three of such things coming up, the light collecting ability and also the sensitivity, because of the large size and advanced technologies like adaptive optics, these facilities are going to be really path-breaking, and they are going to provide unique new opportunities for astronomers to probe the mysteries of the universe. Now, let me just go back a little bit into the history of how India got involved in this program. Started in around 2006, 2007, 2008 kind of time frame. All these projects were interested in an Indian participation, and then India went through a very long evaluation process over a year in trying to understand what is the need for participation, if at all India should participate in these projects. What is if we were to participate, which is the best project to participate in, and what level of participation, do we have the human resources, and so on and so forth. So based on a very long process, which lasted more than a year, we arrived at the conclusion that this is a project which India cannot afford to not participate in, because a large fraction of the world astronomers would have access to one or the other of these telescopes eventually, and that's a situation where India should not miss. And then among the three projects, for various reasons, I'm not going to the details of which, but it was a very elaborate evaluation process. We decided that India should participate in TMT at a 10% level. Now, what is a TMT project partnership look like? It most probably is the observatory itself is going to come up on the Big Island on Mauna Kea, which is the best observatory site, arguably, but among the best observatory site, at least in the Northern Hemisphere. And then the partnerships include institutions in India, in China, in Japan, in Canada, and in California. And we are also expecting that the United States National Science Foundation would become a member. We are hoping that they will be willing to participate in this program and become a member in the near future. So that's what the membership looks like. And this is just a summary of what Mauna Kea is in terms of its observing capabilities, a very large number of usable nights, very dry site at a very high altitude, and it's very low temperature, because of which, average temperature, because of which it's extremely good for infrared observations, especially mid-infrared observations, and very, very good statistics in the atmospheric turbulence behavior, which reflects in the seeing performance of the site. So we can get really fine resolution images from that site. India's participation in the project itself is led by three institutions, as I mentioned in the beginning. ARIES, IAA, and IUCA are the three main institutions. These institutions have set up an India TMT Coordination Center, ITCC, which operates mainly from the Indian Institute of Astrophysics campus. We have a large number of staff, I shouldn't say large, a small number of staff compared to the size of the project, working out of that office. The project itself is funded by, jointly funded by the Department of Science and Technology and the Department of Atomic Energy of India under the Mega Facilities for Basic Science program. And a large number of other institutions are participating in one way or the other in this project. And in addition to the institutions, scientific and academic institutions, we have participation from a large cross-section of industries in India. I will come to that in a minute towards the end of the presentation. So as far as we are concerned, we had built indigenously a 2.3 meter telescope among the close to the largest, or pretty close up there in size in the 1980s. It was by no means a small facility in the world at that time. It was pretty impressive achievement. But since then, the world has moved on, building of 4 meter class, 6 meter class telescopes, 8 meter class telescopes, and now we are contemplating 25, 30 meter class telescopes and to come operational in the next decade. The only progress we have achieved within the country in terms of aperture size, of course, telescopes have come, but aperture size jump is 3.6 meter Devastar optical telescope. So this is a big jump in terms of technology and our ability to get to the forefront of the scenario in astronomy in the world at this point. It's a great opportunity. We need to match that with developing the required technology capabilities, both within our institutions as well as in the industry. And we need to back up with the right human and financial resources. And that's what this project is all about. I mentioned the early phase, the initial step of the project. And then since then, over 2007 to 2014, there was a very detailed review process which the project underwent. Once the community decided it is imperative to participate in the TMT program at the 10% level, we had to go back to the funding agencies. And it was not until 2014 that the fund approval came from the Indian Union Cabinet. And the formal signing of the agreements happened in December 2014. Roughly around the same time scale, all the other partners in the TMT signed the agreements. And in 2015, we started executing the construction of the project in terms of building components for the telescope, building the observatory, etc. But pretty soon we were our on-site construction, the building facility construction, got stalled. I will come to that a little more detail towards the end of my talk. But unfortunately, we faced some hiccups, and the on-site construction got stalled. But the building of the facilities, the building of the telescopes, etc., the partner locations around the world continue and still continues. We expect that the on-site construction will resume in 2023, and if that happens, we will expect to finish construction by 2032, 2033 time frame. In the meanwhile, the partners are executing their work shares. It has been slowed down a bit, but it's continuing. And this also gives us an opportunity to develop the human resources we need in India to make sure that when the facility eventually becomes operational, we have the right people with the right skills and the right readiness to use that facility to its full capabilities over its life cycle of more than 50 years. So this is just an artistic impression of how the TMT would look like if it is located at its proposed location in Hawaii. This is the main summit of the Hawaii, where there exists a large number of other facilities, including among the largest ones existing in the world, the Keck telescope, the Subaru telescope, the Gemini telescope, etc. TMT will be not on top of the main summit, but slightly below the main summit onto one side. And it's a big facility to be built up there. Comparing to structures which we are familiar with, it's an enormous structure to be built up there on top of a 4,200 meter altitude volcanic mountain in the middle of Pacific Ocean. So it's a very challenging program. As I said, it's a collaboration between Caltech, University of California, Canada, China, India, and Japan. the main mirror of the telescope is made of multiple segments, about 492 segments, because nobody can make a single mirror, a single glass piece of 30 meters in diameter and maintain its shape to the accuracy that we need. So the mirror itself is made in multiple pieces and put together with a very, very complicated control system, which aligns these individual pieces to form a single surface to very high precision. The telescope itself has 3 mirrors: the primary mirror, the secondary mirror, as usual, which those of you know about observatory telescopes know that the primary and secondary mirror, but this telescope also has a tertiary mirror, a flat mirror, which allows to steer the beam, the light beam, into a multitude of instruments mounted on 2 side foci stations on the telescope. So while the telescope is very big, it is also very, very fast, in the sense that it can react to changing atmospheric conditions and put new instruments into the field of view as and when required. So this is an artistic illustration of the telescope, what the telescope looks like. This is the primary mirror, the light secondary mirror. Light comes from the top, focuses on by the primary to the secondary, and then back to the tertiary. And this tertiary mirror can turn around 360 degrees to let the beam go into science instruments on the side platforms. To put this into scale, this is the largest existing telescope. It's a very old picture. I'm sorry to our colleagues in Aries to have used this very old picture, but this is a 3.6 meter telescope in construction. And if that is scaled to the TMT, it would be roughly the size of the tertiary mirror of the TMT, which is it's an elliptical mirror, but it is more than 3 meters in along one direction in size. So it's the tertiary mirror by itself is a whole telescope in its own merit. And then, in addition to this, the telescope will have a very advanced adaptive optic system, which would compensate for the effects of the atmospheric turbulence, so that the telescope can operate at its diffraction limit, whatever the 30-meter diameter is expected to deliver theoretically. It is this telescope will be able to work at that diffraction limit, and that would enhance its sensitivity enormously. What do we contribute to the project? About 30% of our contribution is in cash for common activities, such as building infrastructure, road, electricity, etc., which is pooled together by all partners to that level to meet the common expenses. But 70% of our contribution is in kind, that we build parts of the observatory, components of the observatory, in terms of various subsystems, including hardware and software, human resources, various kinds of services during the operational phase, and so on and so forth. So here is just a slide which shows in nutshell what our observatory parts are going to be built by who. For example, here, India's contribution is mainly around the primary mirror and its support and control systems. But there are many other aspects. I will come to that in a minute. Japan is involved in building the telescope structure itself, and they will provide the glass for producing the primary mirrors, and also produce some of the segments also, and so on and so forth. So the work is shared among the partners. Around 70% of the work of building the observatory is shared among the partners. And that work is progressing among the partner institutions, although the on-site construction has been stalled for a while. Here are some examples of parts which have been built in India. These are called edge sensors, which are brought at a company called General Optics Asia Limited in Pondicherry. They're very difficult parts to make. They look simple, but they're extremely difficult. The precisions required on this pattern, the gold coating, the way these edges are cut on the glass, etc., are so demanding that not many countries around the world can meet the requirements. General Optics Asia Limited has produced a set of these parts which are acceptable, which meet the requirements, but as a backup, as an alternative, we are also working with ARCI in Hyderabad in developing alternate methods of producing these edge sensors. These are some initial actuators which have been prototypes, which have been developed in various companies in India, including Avasarla Technologies. These are actuators under test in the US. These actuators are built in India and they have been tested for various performance and lifetime and life cycle behavior in the US. And we are very happy to say that they have also cleared the stringent requirements put forth by the TMT. And a large number of industries in India, in this case, 4 of them, were involved in manufacturing these prototypes and making sure they meet the requirements. Another part is this very complicated segment support assembly, which supports the primary mirror segments. You can see a metal equivalent of the primary mirror segment assembled on the segment support assembly. It's a very complicated optomechanical assembly. And these were also manufactured in India. And right now we have a contract with Larsen & Toubro to build the initial lot of these segment support assemblies. And on and on. There are many components which are built and manufactured in India and under test and qualification program. So in summary, as I mentioned before, the main contribution to India is in parts which are forming the primary mirrors of the telescope and its control system. So in this illustration, the gray part at the top is one of the hexagonal segments, one of the 492 hexagonal segments which form the primary mirror of the telescope. So India's contribution would be, as I mentioned, about 3,000 of these edge sensors, which detect tiny relative motions between these segments of the primary mirror and then provide that input to these 3 actuators under each of those segments so that those relative movements can be compensated in real time. So in total, TMT requires about 3,000 edge sensors and about 1,500 actuators. Then this entire optomechanical assembly, which supports the primary mirror segment in a gravity independent way, so that none of these support structures impact is felt on the top surface of the mirror, so that it does not affect its optical performance. That complicated optomechanical assembly, about 500 of them are required, and they are all being built in India. And we are also going to make a fraction of the primary mirror segment, maybe about 80 to 90 of the mirror segments themselves are going to be fabricated in India. So in a nutshell, almost everything which is related to the heart of the telescope, which is the primary mirror, is being built under various contracts with industries in India. In addition to that, I mentioned a few of the primary mirror segments, not all of them. A few of them would be manufactured in India. There are a total of 574 segments are required. There are 82 types of segments because the surface of the primary mirror is not spherical. It has an elliptical element included in it, or a spherical element included in it, because of which, as you move away from the center, the shape changes. So there are about 82 types of segments divided into these 6 sectors. And some of these segments are going to be built in India. So as I said, these are all spheric off-axis segments, very difficult to manufacture because of very fast F1 parabola. And those such fast mirrors are, even one piece is very difficult to make now, let alone speak about making 574 of them. And about 80 of them are going to be built in India to very, very tough specifications. So here is a photo which shows, so it's a slightly dated photo, which shows our facility which has been built in IAS Crest campus. We call it the ITOF, India TMT Optics Fabrication Facility. Here is this facility is where we would be fabricating these 80 segments. Unfortunately, I forgot to include the photographs, but very recently, the Honorable Vice President of India visited this facility and inaugurated it formally. So we are ready to go. Yeah, anyway, I'll skip this. So here we can see that glass pieces from Japan already started arriving there. They have been stacked in the clean areas. And then we will be pretty soon getting machinery in there. Some of those machinery has already started arriving. And then we would get people to work on building these segments. In addition to this hardware, India is also involved in building the primary mirror control system, which in addition to this hardware of mechanical hardware, there's a whole lot of electronics and cabling, so on, which goes under each of those mirror segments. They are all being built in India. The primary, secondary, and tertiary mirror have to be periodically re-aluminized. Their coating, aluminum coating, has to be removed periodically and re-aluminized. The coating plants which will do those activities, which are also being built in India, the early design work for building these coating plants have been initiated. Then in addition to the hardware, in terms of mechanical hardware, electronics, coating plants, cryogenic systems, etc., we are also working on a lot of software through industrial participations. A substantial chunk of the observatory control software is being built in India. This controls the entire observatory. It provides the backbone for the different components of the telescope and the observatory to communicate with each other, coordinate, including the science instruments. And these have been all making extremely good progress. The telescope control system is another piece of software which is very crucial for the observatory to work properly. We had engaged Honeywell in Pune to build the preliminary design of this telescope control system. When it is clear, the preliminary design review. I should also mention that among the first pieces of construction components which have been delivered to the telescope is a common software, which forms the backbone of all the communication system that was developed in ThoughtWorks, industry called ThoughtWorks. And that has already been developed in operation at the TMT office. And then various other kinds of contributions. For lack of time, I will skip through them. In addition to just hardware, software, etc., there's a lot of involvement in IUCA, in Indian astronomers, in more scientific activities of the observatory, because ultimately this is a scientific instrument. It's meant to make scientific discoveries. So we are not neglecting that aspect of it. There's a lot of scientific involvement of Indian astronomers, for example, developing guide star catalog for the telescope, polarimetric modeling, how well will the observatory or the telescope behave in terms of measuring polarization of astronomical sources, etc., etc. And also actual development of science instrument is a major activity which India has undertaken. And I should mention here that this high resolution optical spectrograph has been identified as among the first of the instruments which would be built after the telescope becomes operational. And because of extremely high interest in India of high resolution optical spectroscopy, India is currently leading this effort to develop the initial designs and initial concepts for high resolution optical spectrograph for the TMT instrument. I think I'm running out of time, so I will skip this slide. As I mentioned, it's an international partnership, and the science for this telescope itself has to go through periodic review, because as I said, India's involvement in this program itself had started in 2007, 2008. The initial science cases were developed at that time, but as you know, we are all well aware that as science progresses, the scenarios change, the thrust areas for science moves on. Certain fundamental questions continue to remain, and they need to be addressed, but the global picture of science keeps evolving. So there's an ongoing process to keep watch of how the science evolves over a period of time, and where TMT should emphasize its scientific goals, so that it becomes, it maximizes or optimizes its scientific productivity. So in each of these science areas, I've indicated here Indian participation. So you can see a broad range of science cases, and in all of which there are participations from India through membership in the international science development teams and the different science categories. And these international science development teams developed, the most recent activity was the development of a detailed science case in 2015. That's a document available in public, so anybody can read it. And there's a major Indian contribution to that activity. And then we are also contributing to the TMT science legacy programs. One of the TMT science fora was held in India in 2017. Gosh, it's 4 years ago now, time flies. But you can see enormous participation of members from all around the world in the various sessions. It was a grand success. And I just wanted to highlight that the science instruments we are talking about for TMT by no means is not a small effort. Each of these science instruments are major projects in themselves to build. They require international collaboration to build. For example, each of these science instruments have been built. You can see indicatively how a partnership forms in each of these instruments, like IRIS in Canada. In IRIS, you look at it, it is in Japan. There is IRIS contribution in UC. There is IRIS contribution from India, and so on and so forth. So each of these instruments you take, it has to be built across a partnership. They are complicated. The right know-how and technology has to be sourced from everywhere. Now, let me change track a little bit to update you on where the on-site construction of TMT is currently. There's the last few slides. Here is a graph put forward, prepared, I think, by Ishwar at some point. Just borrowed from him. I did not make this graph. But what it shows is the development of astronomy facilities as a function of time. So this vertical axis is the diameter of the facility, and the horizontal axis is time in years. And you can see that it kind of follows a linear regime, except that when you come to TMT, ELT class facilities, you can see that maybe we are a little ahead of time to build this class of facilities. So maybe when we started for this work in 2000-ish, it was a jump ahead of the progression which we had historically been seen. So maybe what we has seen in the phase of this project is a direct result of that being too ambitious too soon, but it never harms to be ambitious. In fact, when next generation facilities were being planned in the US and in Europe, they were initially thinking of building 80 and 100 meter class telescopes, and pretty soon the realization came that that's not even feasible in your imagination, because the technology is nowhere near realizable. So eventually realism hit, and people decided to limit their ambitions to about 20-30 meter class telescopes, or maybe 30-40 meter class telescopes. But that itself is kind of ahead of the time in this graph. So what is going on site? We had a groundbreaking ceremony after all the partners agreed. We had a groundbreaking ceremony, but that ceremony was disrupted to some extent by native Hawaiians who live in the Hawaiian island. They felt that they strongly feel that Mauna Kea is a sacred site according to their culture and beliefs, and setting observatories on the summit of Mauna Kea is a desecration of their mountain, and they very strongly believe that this should not be allowed to continue. But mind you, observatories have been built on that mountain from the 1960s onwards, but even from that time, there had been opposition for each of those observatories being built there. But now that opposition is growing, as the size of the facilities are growing, as the number of observatories on the mountain is also growing, the native Hawaiians are worried that it is no more allowable to get new facilities built there. But this also is kind of tightly coupled with certain political situation in Hawaii in terms of the native Hawaiians' right for self-determination, in terms of how much say they have in usage of their land and facilities and so on and so forth. So soon after the groundbreaking ceremony, our on-site construction paused because it's this opposition, and the opponents went to court. A long legal battle followed, and by late 2018, early 2019, the legal cases went all the way to Supreme Court of Hawaii, and in all cases, the Supreme Court of Hawaii gave verdicts in favor of TMT, because TMT had followed all due processes in terms of amendment, in terms of taking adequate precautions to avoid affecting cultural practices, etc., etc. All the statutory requirements and beyond were met by TMT, so we cleared the legal cases. But in spite of that, the native Hawaiians have mounted a sustained civil disobedience, and you can see that one of our this is a road.
You have 5 more minutes.
Sure, I'm done. Thank you. This is a road which is leading to the summit of Mauna Kea. This is the summit of Mauna Kea off this highway, and you can see once in 2019, mid-2019, when we tried to take construction equipments up the mountain, there were a lot of people who came and blocked the road and said, you cannot start construction of TMT there, despite us having all the legal permissions and the support of the state machinery. So law enforcement has been unable to contain the protesters. It's a delicate confrontation, and that standoff is continuing till date. And we are working hard to resolve this by communicating to these protesters and trying to understand their concerns and see how we can come to a win-win solution. In the meanwhile, TMT has also worked hard to identify a backup site in case things do not work out in Hawaii. There is a backup site has been identified at this island off the shore of Spain, the ORM observatory. So if Mauna Kea does not work out, we can potentially go to ORM in Tenerife. We have all the permits we worked through the government in Spain to obtain all the permits, the building, the land lease, the building permits, all the legal processes and statutory and administrative processes have been completed. So in principle, we have permission to build the observatory in either of these sites. Our preference is to go to Hawaii. The partnership itself has a preference to go to Hawaii for various reasons. But over time, if that does not materialize, we may go to La Palma as a backup option. So I'm concluding my presentation here by saying that TMT is one, but TMT is but one among many, many new facilities which are coming up across the world, both from space and from ground. And so this is really a remarkable time to be an astronomer, because especially for the youngsters who are getting into the stream of astronomy now, or those who are looking at astronomy as a possible career option. Some of the most fundamental questions which we can ask will be addressed by these facilities which are coming into being. And I cannot guarantee that we'll find answers to those questions, all of them, but we will have at least better understanding towards answers to those questions, and that would be fantastic. And of course, these facilities are going to create enormous amount of data. So if you want to utilize your data handling skills, data manipulation or data crunching skills, it is an enormous opportunity for those people also to participate in this facility, which is a new, unique opportunity, and then that would be of enormous importance for bringing far-reaching results, path-breaking results from these facilities. Thank you very much.
Thank you, Professor Rama Prakash, for a very exciting talk. So we have time for one or two quick questions. Let me just quickly see if there is some raised hands. Yes, Gopu, yes, please go ahead.
Okay, so Ram, so when do you expect the decision to continue Mauna Kea will happen, or is that the process they have to call at some point of time saying that okay, this may not be possible? Is there a timeline for that? Or?
Sorry, I muted my microphone. Can you hear me?
Yeah.
Yeah. So that's a very interesting question, Gopu. It's not just a scientific constraint. There are many factors which come into play for that decision. For example, if we are expecting the National Science Foundation to participate in the project, they may have a specific interest in one of these sites. So if we are trying to say, okay, we would like USS National Foundation to be part of the program, we might have to wait till we give them an opportunity to have their say in the program. For example, as an example, we want to make a concerted effort in Hawaii. There have been very recent efforts in Hawaii put in place by the state missionary, because a state missionary in Hawaii understands the importance of a project like TMT in bringing in opportunities for the Hawaiian communities, not just native Hawaiian communities, the entire Hawaiian communities in terms of economy. Such a big facility being built there provides a lot of job opportunities. Astronomy is not an industry kind of activity which can potentially degrade the environment. So it is a balance between contribution to economy, alternate contribution to economy. Hawaii is a very tourism dependent country, so they want to diversify their economy through other economic means. So they look at astronomy as a very good balance between protect their environment versus providing job opportunities and so on. So the state machinery has a lot of interest in enabling TMT in Hawaii. So they are working towards it. So we are closely working with a lot of external partners, both in Hawaii and outside. So while I cannot put a specific date for taking that decision, we need to take that decision in the next year, maybe a year and a half, that kind of time scale. I can't see how we can prolong this decision beyond that kind of time scale.
Thank you. So by the time then the GMT and EELT should be fully operational, is that, I mean, in your time scale even now, like 2032 or something like that?
As I'm not very aware of how much progress they have made, all I can say is these are all very complicated projects with a lot of demand on resources, human resources, technology capabilities, and the financial resources. So it is not clear when what is going to be, producing science reliably and stably with a whole set of instruments at the back end. As you can see, as you know, it's a very complicated facility. So it's you can say, okay, I got first light. That doesn't mean that it's operating stably and reliably, producing good science. So I don't know when the other facilities are currently planning to complete. And when you say complete, it is not clear what that means. Is it just first light? Does it mean a suite of instruments producing science reliably? What does that mean? Also, it comes into question, right? So I'm not aware of the details of those.
Okay. Thank you.
There was one more question on the chat by Sri Kumar, and that's how long can India TMT team wait for this to get resolved, and if there is a plan B on that?
Yes, so India at the moment is very emphatically been taking the position, both formally and informally, in all forums, that what is most important is to build the facility as quickly as possible and produce the scientific results. So in that sense, with that, if we put that as the primary goal, it is very important that we decide to move to La Palma as soon as possible and start construction there. That has been our formal position in the project. But as I said, this is a very large program with a large number of partners, a lot of external players, etc. And therefore, one partner's opinion cannot overrule everyone else. We need to work together with the partnership to make this a successful program. So while we continue to put pressure on the partnership to say, let us move to La Palma as soon as possible. We have all the permits there. Let's start construction there. We also need to be sensitive to the compulsions of other partners. So, as for a plan B, if you are asking about participating in one of the other facilities, I think we have not looked at that as a major possibility now. We evaluated that a long time ago. But as I said, how the other partnership is evolving, where their current status is, and if India participates in one of them, will we be able to meaningfully contribute to the construction activities, even at this stage, or we will be just a paying partner, which is not the desirable option. Those things are not, they are not obvious, and it may be very difficult. It may be too late to participate in one of the existing facilities or the upcoming facilities, existing projects which are for upcoming facilities, the large ones. But as you would hear from the next speaker, India has plans to build a national large optical telescope, a 10-meter class telescope. So a lot of resources and know-how and industrial capability developments, which we have achieved over the past few years, would be very, very useful and extremely useful. And I'm sure without those development, we couldn't have potentially considered building 10-meter class telescopes on our own. So they would be of enormous use for India when we get the approval for building a national large optical telescope in India. So these efforts are very useful. If both projects have to run concurrently, we will need to develop the resources for both of them. But if TMT at some point is, we decide is not moving sufficiently forward, we can always reuse these resources for our own programs, and that would be a major benefit.
Okay, thank you very much. I think we should move on in order not to fall too much behind time. So let us thank Professor Ramaprakash again for a very nice talk. And the next speaker is Professor G.C. Anupama, and she will be talking about the NLOT project. Professor Anupama, please.
You're seeing my screen?
Yes, yes.
Okay.
Yes.
Okay. So as Ram said in his response to Shri Kumar's question, so here is what could be a plan B if we are not very successful with the TMT, which is something which we don't want to happen. We want to have the TMT and this. So let me give you some kind of an update and the status of this particular proposal. So just a brief on what are the current facilities and what is our immediate future plans in terms of optical astronomy. We have heard yesterday from some of the facilities the results already. So currently we have 6 telescopes of 1 to 2 meter size, which is, these are distributed all over India. We now have the 3.6 meter DOT, which is giving excellent results. And very soon there'll be another 2.5 meter telescope by PRL at Guru Shikhar. India is one of the partners of the TMT project. You've just heard Ram explain all about it. But I would like to emphasize here that currently we do not have direct access to 8 to 10 meter class telescopes. There is limited access to the SALT telescope through IUCA. And of course, we can collaborate and get some time on the 8 to 10 meter class telescopes, which people are doing. But that doesn't really satisfy all the scientific needs of our community. So there is a need for a 10 meter class telescope in the country. And this has been very strongly realized by the astronomy community. And this 10 meter class telescope is what we are referring to as a National Large Optical IR Telescope, or NLOT. So the motivation for the project, again, thanks to Ram, he has already covered quite a bit of this motivation. And science, of course, is always there. I should also say historical, some kind of a historical background, that the idea of building a large optical telescope in the country has been recurring since 1984. Essentially, when the 2.3 meter Vainu telescope was more or less getting completed. And so far, it has not yielded any result, I would say. There was a fresh revival in the 1990s with a proposal to have a 6.5 meter telescope by IAA. This proposal, although it did not result in the 6.5 meter telescope, it resulted in the identification of Hanley, the setting up of IAO, and the 2 meter HCT. So it actually helped in identifying an excellent site in the country. A renewed effort for the 8 to 10 meter class telescope began in IAA in 2006-2008, as Ram pointed out. And this effort sort of led towards our participation in the TMT project. So an important thing to remember here is that India's in-kind contribution to the TMT is bringing in segmented mirror technology to the country, and the best way to put it to good use is to build our own 10 meter class telescope. And needless to say that such a project will benefit all of STEM and the industries. Science goals, I've just listed them out. I'll not go into great detail. We have heard Sri Anand talking about science from 8 to 10 meter class telescopes. Of course, we can do a variety of science all the way from the solar system objects to the early universe. And in between, there are these studies of formation of stars and planets, the formation and evolution of galaxies. Cosmic chemistry is an important area where we have a significant contribution from this country. Then transient science, that is stellar explosions and extreme physics, is obviously an area where we have made a remarkable mark in the international community, and we should certainly continue in that. So is there a national consensus for NLOT? Obviously that is. And this was reiterated in a national workshop, which was held during ASI 2019. We had about 90 participants, and at the end of the workshop and the end of the discussions, there was a unanimous opinion that we certainly need to have a 10 meter class telescope in the country. The telescope is to be sited at Hanley, and we should start working towards the development of a detailed project report. So what has happened post that? The efforts have been going on at IAA, although maybe a little on the slow burning, but definitely it has been going on and it's picking up now. So there was a summary proposal which was finalized with a few key science cases, a concept design, and a list of possible first light instruments. A cost estimate was made based on the Mauna Kea spectroscopic explorer cost estimate. And we also put in a management structure. And this summary proposal was submitted to the Mega Science Division of the Department of Science and Technology in July 2019 with a request for initial funding of about 13 crores for the preparation of the detailed project report. Unfortunately, we have not had a formal response from DST, but there's a lot of activity going on within the DST, and we hope something will come as a result of that. But nevertheless, as I said, the activities within IAA have been continuing, and some of these are continuing with the detailed site characterization of Hanley, working on the optics and the optomechanical design, trying to develop the technology for the M1 control systems through the development of a prototype segmented mirror telescope. I'll just go a little more detailed into these activities. So The realization of NLOT, as Ram also mentioned, we are gaining a lot of technology and expertise with our participation in the 30-meter telescope. IAA has been also working with the Mauna Kea Spectroscopic Explorer project on a small scale, but that has helped us in coming up with the optics design for the primary mirror. The Mauna Kea Spectroscopic Explorer is also a 10-meter class telescope, and by working on the design of the primary mirror for that, we are in fact actually working on the NLOT primary mirror itself. So all these contributions that are there towards the TMT is certainly going to help us. And in addition, we'll have to have other national and international efforts towards realizing the entire telescope itself. So what are the steps towards the DPR itself? The science justification, of course, it is available, but it certainly needs to be updated. The identification of the site, yes, we have that, but we certainly need a detailed characterization at the actual location where we would like to locate the NLOT. Then we have to work on the various concepts and the preliminary designs for the telescope, the optics of the telescopes, and we need to have the mechanical, electrical, electronic specifications drawn out, specifications of the instruments, some preliminary design for the first light instruments, talk about the operations of the telescope, the various modes of operations, do a lot of prototype development. So all this exercise requires interaction and not just the activity within the country, but also interaction with other groups and that are building or have built similar large facilities. And of course, another important aspect is we have to study the logistics and the available infrastructure at the potential site. And a feasibility study has to be undertaken for this. Maybe we should have a consulting firm to do this. So the schedule itself, we have looked at a schedule of about 15 years, right from, which includes the detailed proposal preparation. And this proposal will contain the detailed design, and we need to have a ready to build design. So right from the proposal preparation to the first slide, we are envisaging about 15 years. The management structure, some sort of a management structure has been drawn up, and our estimate is that we need to have at least 40 dedicated personnel, in addition to several of the scientists and engineers who would be contributing part-time from the various organizations that would be involved with the build of this facility. Okay, so what are the other efforts? The efforts towards the continued site characterization at Hanle. This is just to give a very brief summary of the Hanle site to show that it is not a bad site compared to Keck. What is slightly poor in a site in like Hanle is the seeing, which is about 1 arcsecond. But for a 10-meter class telescope, we can kind of make do with this seeing. A major advantage with a site like Hanle is the accessibility and the availability of nights throughout the year. And of course, its ability to use the site for the infrared and the mid-infrared wavelength regions. So various site survey instruments have been developed, and they're all located at Hanle for measuring various parameters, the extinction and the seeing measurements. There are weather stations which monitor the weather on a daily and an hourly basis. mass dim to measure the seeing at different heights. So these are some of the activities which are going on towards the site characterization. What is it that is being done towards the optical design and the mechanical conceptualization? The baseline specifications of the telescope have been drawn. The diameter will be, the primary will be a 10 to 12 meter segmented primary. Of course, the telescope should cater to a diversity of observational programs. We want this to be an observatory class telescope. And we are looking at something which will have a high throughput in both in the blue region as well as the IR regions, taking advantage of the high altitude site that has been identified. There are some other parameters that have been drawn up with respect to the actual performance, the optics performance, and then the tracking and the pointing of the telescope, and the kind of operations availability and the capability that needs to be there. So coming to the optical design. Sorry?
It is a straight talk, Anupama. Somebody is not muted.
Yeah, can somebody, I don't know, I just saw something.
Can you please mute all your mics, please?
Thank you. Yeah. So the primary mirror, we are looking at a design currently. The design which we have been working with is one which has a clear aperture of 10 meters, a Nasmith focus of f ratio f15. We're looking at an unlimited field of view of 10 arc minutes. The image quality diffraction limited beyond 1 micron. And we want the telescope to be kind of compact to reduce the overall cost on the civil construction and other aspects. So we have worked on the primary mirror segmentation, looked at possible design configurations, worked on the primary mirror error budget. So these are some of the design considerations for the selection of the primary. Keep the segmentation similar to the TMT, that is a segment size of 1.44 meters, 45 mm thickness, and have an intersegment gap of 2.5 meters. Choose the primary so that the segment can be fabricated and tested by the facility at the ITOF facility. Keep the primary as fast as possible so that the overall telescope size can be low. Keep the asphericity as low as possible. So these are some of the various considerations that have gone into the selection of the design. Once again, we have also looked at the overall telescope optics design, having some considerations for that, keeping in mind that we are interested in using this telescope in the IR and the mid-IR region also. So the M1 segmentation, as I said, these are the specifications which has been considered. So the segmentation has been done, and it's a 6-fold symmetry. The total diameter is 11.3. That's this outer circle. However, the clear aperture is a little, it's around 10 or slightly above 10 meters. As I mentioned, the design is such that the warping loads while using the polishing equipment should be less than 400 newtons, so that we can use the same SMP fixture that we are getting for the TMT. And the asphericity is also worked out so that the SMP fixture that will be used for the TMT project can straightaway be used for polishing the NLOT segments also. So the primary mirror will have 60 segments, and the primary mirror shape error budget has been carried out, taking into consideration all various parameters which can give rise to deviation from the expected the expected waveform. Here is an example of the different F ratios that we have looked at for the primary in comparison with a few other 10-meter class telescope, like the MSC, which is coming up, the Chinese Large Optical Telescope, which is again been designed, Keck, which we know has already been existing for several years, and the TMT design. We have just looked at this to compare and see which would be an optimal F ratio to arrive at. So the entire telescope optics design itself, there are three different designs that were looked at. A two-mirror Ritchie-Chrétien design with a Nasmyth focus, or a Ritchie-Chrétien design with Nasmyth and Cassegrain foci. We have also looked at a two-mirror aspheric Gregorian design and a three-mirror anastigmatic design, which is what the Chinese Large Optical Telescope design was. We have studied all the three designs, considering the primary F ratio varying from 1 to 1.75, but not changing the M1 segmentation that we had worked on earlier, keeping at that and looking at the field of view of 10 arcmin. So these slides, I'll not go into too much detail into any of these slides. This is just to give you an idea of the kind of design that has been worked out, the activity that has been done. For the Ritchie-Chrétien design, this is an example. As an example, I'm showing the F1 primary. So all these factors have been looked at. What is the Nasmyth focus, the field aperture diameter, what is the amount of secondary obscuration, the total focal length, the field of view, the plate scale, the vignetting which would be there, and what is the image quality over this field of view. And we have also looked at the aspherity and what would be the warping function to see its compatibility with the TMT, not just for polishing, also the TMT segment support assembly. So for each of these designs, the advantages and the disadvantages have been worked out, and also we have made an assessment of the various risk factors which would be there for, particularly with respect to the manufacturing. So this has been worked out for each of these designs. These are the advantages and the disadvantages if we have an RC design. Likewise, this is for the Gregorian design. And again, the advantages and the disadvantages and the risks have all been looked at. And the TMA configuration has also been looked at. And once again, we have looked at the advantages and the disadvantages in this. And from the studies that we have done, the TMA design has more disadvantages as compared to the other two designs. So we are more inclined towards looking more towards the RC and the Gregorian, but more likely we will go towards the RC for the following reason. If you look at the total telescope throughput, and this is assuming the Gemini coating, definitely we see that the RC performs much better over the other designs. And particularly having a Cassegrain focus would be very useful if, for instruments which need to have a better performance in the UV, ground UV region. So this is the summary of the various optical layout design work that has been done. So yeah, I'll not go into detail into each of these, but all these aspects have been looked into for each of the designs. The segment support assembly itself, we worked out and we studied in great detail whether we can use the TMT segment support assembly, whether that design can be used. And the major driving factor to look at that design is because we are producing all the segment support assemblies for the TMT project. And so it just makes sense if you can use that design straight away for the NLOT. So that work was done, and our conclusion is that we can certainly use that design, although there will be some minor modifications, minimal modifications that are required, but the basic design can be used, which is, I think, an advantage considering the industries would have already developed the required technology for producing these segment support assembly components. So coming to the instruments, we have considered the following requirements: that we would like to have a focus on blue sensitivity, taking advantage of the site. We would like to also focus on mid-IR because of the low thermal emissivity at Hanley. Of course, it's a huge challenge to have a coating which would be optimized for both the UV and IR. This is for the telescope optics. It's going to be a huge challenge, but we have to see. And for all we know that, by the time we actually get around to the build of this telescopes, the technology, the coating technology would have improved for us to have a coating which will have a good performance all the way from the UV to the IR. And since we are looking at this telescope today, we should take advantage of newer technology. So probably we should be looking at whether we can have an adaptive secondary right from the beginning. Of course, right now the designs have been worked out with a conventional secondary, but it's probably a good thing to start looking at an adaptive secondary design. We should look at using curve detectors, using aspheric optics and photonic lanterns. And essentially, we should look at a design which can take advantage of new technologies that are developing. Here are some of the possible science instruments based on some, the existing instruments and what is also proposed for the TMT. Of course, this is like, a suite of instruments which will allow us to do a variety of science cases. So here are some of these instruments listed out as the possible science instruments. So the technology development itself, as I mentioned earlier, we are looking at developing the technology for a segmented mirror telescope, which is not completely standardized as of today. In particular, we require the technology to control the primary, its alignment and phasing. So it is extremely important to understand this technology prior to embarking on the development of the larger telescope itself. So towards this, a 7-segment prototype segmented mirror telescope with an effective diameter of 1.6 meter is under development at IAA. In the first phase, a 7-segment lab testbed will be developed. And in the second phase, a full-fledged telescope will be realized, which after detailed tests in our IAA campus, either in Bangalore or in Hoskote, will be installed at Hanley so that we can study the performance at the location of the 10-meter telescope itself. The update on the PSMT activities, the single segment testbed is ready. This is for checking the basic function of the segment support and actuators. This is almost ready, it is more or less there. The segment support system design and analysis is completed. The first prototype has been fabricated and assembled and is being tested now. The design for the 7-segment test bed is ready, and the fabrication will begin soon. The actuators and the edge sensors for the PSMT, the P2 version of the actuator is developed and is going through the test. The performance has been found to be satisfactory. P1 of the edge sensor has been developed, and the P2 development is going on right now. The alignment and phasing tool for the PSMT, the optical design and analysis is completed. Mechanical design is under progress. So the summary of the ongoing activities at IIA towards NLOT is the technology development in the form of PSMT. Telescope design is being worked out. And of course, all this is leading to the development of a detailed project report for submission to the funding agencies. This is the team at IIA that is looking at various aspects, the science and instruments, the site characterization, the development of the DPR. This is our engineering team, which is working on M1 and M1CS, PSMT, site characterization instruments. And also now this group has started looking at the telescope structure design and requirements. This is the PSMT team. Students are involved in this. Several of them have already got their PhDs. 3-4 of them working in this group have already got their PhDs. Anu has submitted a thesis, and Radhika is working already towards a PhD. So obviously this cannot be the effort of a single institute. While all this activity is going on at IIA, we would certainly like other institutes to start collaborating with us, and we are going to reach out. In fact, we wanted to do this, but with the pandemic, there has been some amount of delay in our activities, and very soon we will be reaching out to our colleagues in other organizations, and we would like to form various national groups that will, we'll have a concerted effort towards the NLOT. So with that, I will stop. Thank you.
Thank you very much, Professor Anupama. We have time for a few questions. Please. I do not see at this moment any hands raised. Okay, it doesn't seem that there are any questions. So let us thank Professor Anupama again for this nice update on the NLOT project. And we move on to the final talk before the tea break, and to be delivered by Professor Shomak Rai Chaudhuri on the LIGO India project. Professor Rai Chaudhuri, please.
Thank you very much. Thank you, Pratik. Thank you, everybody. It's a great talk on the TNT and lot. Let me share my screen. Am I audible fully?
Yes, yes.
So since we've been for the whole week listening about compact objects, high energy astrophysics, black holes, neutron stars, I thought I'd emphasize that this is not just about LIGO India, but about the science that it's going to do. And so I'm going to talk about both the aspect of what science I think we expect from going forward from now, from the LIGO observatories and LIGO India, to where we are with LIGO India. And thanks again for the organizers putting this together, an overview of all the various facilities. Just to give a background, we know that what we are detecting here are ripples in space-time, which for a long time was believed not very easy to detect. And even Einstein himself thought it would be very difficult to detect gravitational waves. And that's because these gravitational waves can, with very small amplitude, which is very difficult to detect, carry a huge amount of energy because of the nature of the relation between the two sides of Einstein's equation relating the deformation of space-time and the stress-energy tensor. And space-time is very stiff, and so the amount of amplitude that even the most extreme sources can produce is extremely small. The basic idea then is that there is an event which could be the, as we detect most of the time, mergers of black holes or mergers of neutron stars, and then that propagates through space-time in certain modes, which are to do with compression and rarefaction in different directions. And this would then be detected in a configuration of a simple interferometer. But of course, the setup is not very simple, but it would affect the two perpendicular arms of a Michelson-like interferometer in two different ways. And as a result, the detection would occur. So in a LIGO facility, it's basically a 4-kilometer long two arms in a Michelson configuration with lots of other things put together. The arms themselves are not just 4 kilometers, but there are cavities, Fabry Perot cavities in which the signal builds up and is amplified, and the difference between the two arms is then effectively detected as not a 4-kilometer, but hundreds of kilometers effectively arm length. But even for 4-kilometer arms, the expected deformation, the difference between the two arms, due to this, the amplitude of the gravitational wave is expected to be about 10 to the power 18, minus 18 meters. And that's the for merging black holes, merging neutron stars, given certain configurations. And this is what was detected to begin with, and this is what we continue to detect, and this is what we will improve upon. So that's the basic idea. And so this being smaller than the size of an atomic nucleus provides extreme requirement in terms of the signal in the presence of noise that can come from all kinds of, these are at frequencies of a hertz or so. The noise can come from various sources, which I'm not going to talk about today, but we'll show how complicated the instrumentation can get in order to mitigate the various kinds of noise. So if you remember, just going back, the two current LIGO observatories in the US, which are two ends of the US, one in Washington State and one in Louisiana, then detected the first ever gravitational wave, which caused a lot of sensation 5-6 years ago. And the detection was in September 2015, announced in February 2016, was the merger of two black holes, which caused, and this, everybody knows here, the entire merger sequence that was actually detected was about 1/5 of a second long and identical in almost at the two observatories, 3,000 kilometers apart. And it led to a signal which is known as a chirp, which means the frequency of the gravitational wave detected increases in a very short period of time because the two black holes are coming close together to merge, and as a result, the frequency goes up. Now, this was interpreted as a merger of two black holes of pretty high mass compared to the black holes that used to be found from other sources at that time. So the very first one was a merger of two black holes of 36 and 29 times the mass of the sun, getting together to form a 62 solar mass black hole with a deficit of 3 solar masses that would go into essentially gravitational waves. The radiation, this wonderful depiction of by Anirban, one of our IUCAA students, of the Schwarzschild radii of the black holes involved in this particular, the first one. And the first one caused so much sensation. Actually, the second one that was discovered was a merger of 8 solar mass and 14 solar mass black holes into 21 solar mass. The fact that that was too normal, and this was pretty abnormal in terms of masses, the second one got eclipsed. But by the time we went forward and the media sensation subsided, Amul's cartoons, etc., India had already signed an MOU with NSF to build a third detector in India. And this was already in March 2016, a year after, a month after this was announced. Shekhar Boshu, and then director of, then the Secretary Atomic Energy, who's no longer with us, unfortunately. Within a few months, we detected 2 or 3, and already people had put together a plot like this. And this is very interesting, given that over the week, we have heard about so many talks from the Indian community on X-ray research on binary black holes and binaries in black holes in binaries, studied from X-rays and associated electromagnetic radiation. So already it was found that the black holes in the mass range that was being probed is very different from what we get from X-ray studies. This is going to be one of the most interesting things in this whole story. Now, of course, this has come to within 5 years, with an abrupt end to the third run of LIGO and Virgo together. About 50 sources are confirmed. There are many being considered. People are analyzing the record and coming up with more and more candidates. But essentially, the 50 in the catalog that sources that have been confirmed, and these, of course, include black hole mergers, neutron star mergers, and black hole neutron star mergers. If you look at the timeline, Virgo, which is the European observatory, which is 3 kilometers long, joined the collaboration in 2017, and ever since has detected all of the detections that, almost all of the detections that have when it's been up, all of the ones that LIGO has detected. And Kagra joined from Japan, joined the collaboration just about the time when the shutdown happened for COVID last year, and so really hasn't detected any yet. The third observing run started in November 2019 and was abruptly ended in March last year. This is where we are now. And so this is the status of that. Each of these mergers that are detected from LIGO give 3 black holes or 2 neutron stars, 1 black hole, 3 objects. And here they are, and you can see how the mass range that is being probed is so different from the electromagnetic detections of black holes from X-rays, and on the same plot, and I'll come back to it in a minute, on our neutron stars from LMXBs and various other detections from radio and things like that. And so, and of course, neutron stars are found in LIGO Virgo mergers as well, and they are put on here as well. So we also know that the famous neutron star binary merger, 170817, opened up the doors to multi-messenger astronomy, and this is why it's also very important in this conference to talk about such sources, which are going to be very, very common, I hope. This one opened up the door, these 2 neutron stars merging opened up the door to electromagnetic follow-up, because it was very rapidly identified as a kilonova. And so the optical identification was found And this led to an amazing follow-up observing in all kinds of electromagnetic waves, in which, of course, Aries played an important role, as well as various other Indian observatories, including the ones in Hanle and JMRT and things like that. So, and so very interestingly, a lot of interest comes from the electromagnetic community as well in following this up. And with LIGO India, this is going to be one of the targets. One of the major things that will happen is that the sensitivity to such mergers is going to be very important. This moving on in the story, of course, in our community, in the high energy astrophysics community, electromagnetic community, people have been talking about intermediate mass black holes for a long time. And every time that comes up in the context of a ULX or something like that, there is always a controversy about whether it can actually be established completely from an ULX that it's an IMPH. Now, from LIGO, we have 3 black holes that have been detected that are more than 100 solar mass. The most massive being 190521, 85 plus 66 gives rise to 142. And this is really pushing the envelope in terms of intermediate, we starting to call this an intermediate mass black hole. If you're thinking of supermassive black holes being generated hierarchically through mergers of smaller black holes, or even the whole problem has been that in the mass gap between the stellar mass black holes and the supermassive black holes, there haven't been any that have been found, but now we are starting to detect them. And this makes it, for people who study compact objects and the formation of these things, very important. So this is the picture now with the error bars, and it's beautiful to see the fact that in the masses, the entire mass spectrum of black holes and neutron stars, we are slowly filling up and moving upwards. Now, where do these the black holes that are detected in gravitational waves any different from the ones that we find in binaries from X-rays and things like that? So this is something that's a very important subject of research right now. People are talking about different ways of forming these binaries. Of course, to form a black hole binary, very likely formation in clusters, and so you can have an X-ray binary can form an isolation, and one star can then evolve into a black hole. So in situ, you can form, but to have 2 black holes in the same binary system is probably due to the fact that they form in different systems and come together to form a black hole binary. And so those, they pair up into binaries, and so you need dense environments and clusters. People are doing quite a lot of amazing simulations to figure out how these things can form. And you can look at and so this is a wonderful area of research that and we can all get into. The early papers actually show that in the kinds of globular clusters and the kinds of formation that can happen from simulations, they have a mass distribution that kind of peaks around 50 solar masses or so, which is quite, and here there are different kinds of simulations along with the observation or current observation superposed on the same plot to show that already with the small numbers of detected by LIGO, we are actually getting there. Contrast this with the study of X-ray binaries in our galaxy and the mass distribution, classic paper from Ramesh Narayan and McClintock and collaborators. You can see that those essentially peak around 5, 6, 7 solar masses. So this is essentially what this picture is telling us about, and the picture is telling us that with the 2 approaches, we are looking at different populations of black holes, and this will, of course, all kinds of compact objects will enhance our understanding, particularly when we get into a position where we can follow up detections, LIGO detections, with electromagnetic detections. I'll come to the questions that are coming in the chat box in a minute. So gravitational waves not only detect mergers of black holes, but various other things. And in principle, and there can be a gravitational wave background, a stochastic background. A supernovae can be found in gravitational waves, and even in the frequency range that's been now probed, such things can be detected. So this has now led to this huge scientific collaboration. And the idea is that in addition to the two in the US, GEO in Germany was already there. That's the 600-meter interferometer, where a lot of the technology was first tested and is now also being tested. In fact, squeezed light is now implemented first in GEO 600. Virgo is now operational in Italy, in Pisa, and Kagra in Germany, in Japan, and now then we expect LIGO India to be up in the target is 2027, even though we are tantalizingly close to the full cabinet approval of the full expense. It's not been, and so currently the work that's been going on with LIGO India is with 5% of the money that it is going to finally be spent on LIGO India, which is being channelized through various sources to us now. The biggest advantage of LIGO India is the fact that it's not just two LIGO detectors 3,000 kilometers apart, but one on the other side of the world. And the baseline triangulation means that that localization of sources go from being hundreds of square degrees to a few square degrees on the sky, and this is where localization can lead to an enhancement of the probability of finding them electromagnetic follow-up, and that just, as I was trying to say, changes our way of looking at these things and studying populations. So this is what LIGO India might look like. This is from DCSEN, who is essentially building the blueprint of the observatory, their colorful map. So the four institutions in India who are nominally in charge of this effort currently, along with a very large number of associated institutions who are doing quite a lot of research, are these four, and the site is going to be in Hingoli district in Maharashtra. So the responsibilities of the different institutions, DCSEM, which is in Mumbai, which is the civil arm of the DAE, is developing the site and the civil infrastructure. IUCA has already contributed to identifying the site and we are characterizing various aspects of the site, but data handling, etc., and the human resource development, and eventually the science rounds of LIGO supposed to be conducted by IUCA. The IPR Gandhinagar is in charge of the vacuum system, and RRCAT is in charge of the optics and the detectors, essentially. So here's where we are right now. Site acquisition has happened, and it is a place called Aundha, Nagnath, which is a pilgrim site, very near a pilgrim site, very close to the town of Hingoli, district town of Hingoli, about 80 kilometers from Nanded. And we now have acquired the whole the site that will be required for the 4-kilometer arms with 300 meters across, and the associated land for the various the stations. And we now also have land acquired for staff housing in Hingoli and a guest house and another little housing complex and science center, etc. at Nanded, right? This is what it looks like now. Weather station's been put up. A small construction site office is being built. and fencing has been put around. Of course, anywhere in India requires fencing. The two US observatories do not have fencing around them. At IUCA, one of IUCA's jobs, as I said, was to characterize the site. So one of the things that's been going on in association with the NGRI Hyderabad is a year-long monitoring of the seismic activity at various frequencies. Wonderful reduction going on now with here in IUCA. One of the things that we have established already is that the median, level of seismic amplitude, essentially in the microseism, within the 0.1 hertz to 100 hertz, this kind of window is already a factor of 10 better than anywhere in the US. So the noise due to a seismograph activity, you might think it's so close to Latur where a huge earthquake happened, but we're talking of day to day. The vibration of the Deccan Plateau is one of the most stable places in the world. And this kind of work is going on. And I'm not going to go into any detail, but we have a team here along with people in BITS Hyderabad and analyzing this kind of data. The computational facilities entirely being set up at IUCA right now. And of course, there'll be a corresponding thing on site. The cluster is one of the largest clusters in the world, reducing LIGO data. And one of 5 big clusters of existing LIGO data is being reduced on them. And as LIGO India comes in, the data center here is going to expand. Already it's started to be installed. It's up to 2 petabytes now, and all the old archival data has been now moved. Copies have been moved here, and as LIGO and will acquire more data, this will already go in, and then this will become the computation center for LIGO. So IPR is already building the basic vacuum infrastructure. If you look at the interferometer itself, it is full of optical elements that are in vacuum, which are essentially of nanotor level. And so these are various vacuum chambers, and these are the most important parts of essentially this layout. And so there are 2 kinds of chambers, and both prototypes are being built now. The basic symmetric chamber is the vertical one. The horizontal ham is these 2 are the different kinds of chambers here, as you can see. And these chambers, there are 5 BSCs and 8 hams that will be built. Eventually, the one of each are being built as prototypes. Now, this is what it looks like. It's being built in Bangalore, Vacuum Technologies. And this is recent pictures from last month. Right now is being built in Bangalore. The ham is slightly modified from what's in the US, working with the LIGO team. This is what the picture looks like now of parts of the ham chamber that are being built. And these are the 2 prototypes to be built here, will be transferred to Indore, the RRCAT lab. And then this will then lead to the manufacture of the other ones. At RRCAT, a lot of stuff is going on. They're building a 10-meter prototype, 10-meter in which a lot of training and experimentation will happen. It will have its own scaled ham and BSC chambers, but it'll be a 10-meter prototype. And this is going to be built in this separate building that has been built on the RRCAT campus for LIGO India, which is the training and testing laboratory. Is almost complete, but 95% complete, seriously hit by the pandemic. But this houses the 10-meter class interferometer setup, plus when these prototypes are going to be finished in Bangalore, they will move there and things like that. So this is one of the places where a lot of the training for LIGO operations will happen. A lot of the project students from various parts of India can go and work there. And so it's being conceived as a set of experiments that will go on as part of the training facilities for LIGO India. Ararat's building a lot of the other various elements for LIGO that have to be done in India. Not everything. Some of the detectors and the laser are coming from the US to be assembled, but a lot of things need to be updated. A lot of things need to be rebuilt in India, and Ararat is preparing to do all that, particularly the suspension systems, as well as the upgraded lasers and things like that. We are not neglecting the population near the site. We've started very early on, even before we started acquiring the land. IUCA's one of the major activities has been to go and work with the population in Hingoli district, as well as nearby districts, Palwani and Latur. We are currently working with more than 100 schools and the parents of the children in the schools, as well as the villagers. And we have teams before the pandemic shut down in phases. In between, we started way ahead in 2018 to talk to people there and get people involved in what's going on there. And we're very active on social media. Please look up what's going on on Twitter, Facebook, Instagram, things like that. I'll stop here and look at questions. Thank you.
Thank you very much for exciting talk on the update on the LIGO India project. So we have time for a few questions. So let me, yeah. So Gopu, please go ahead.
Yes, go.
Thank you very much for the very nice talk. I have a couple of questions. So this is about the optical elements. I mean, the initial agreement, the US will provide optical elements and all that, but that was supposed to be for the, the regular LIGO, but the one we will be building will be A+ kind of a category, right? So the optical elements are going to be very different. What are we going to do on that?
Yeah, so thank you very much. That's a very important question. I didn't go into these details. What will happen is that by the time LIGO India will come into operation 2027, it's going to be what's known as the A+ configuration, which is, but there are some of the basic, much of the basic electronics control systems, etc., will be unchanged, and those are coming from the US. There are some key elements that are going to be different. For example, the mirrors are going to be different. The mirror coating is going to be different. In the laser system, squeezed light, which has been developed at MIT and is being tested out, etc. So for that, in the DPR, which is, as I said, on the verge of approval, the upgrade from what we have now to the A+ configuration, whatever expense is needed, is built into the what's been asked for from the government. And whether the mirror is going to be built in India or they're going to be built as part of the order that will go for A+ in LIGO US has not been decided yet. It could be built in either place. But the research that goes on for this upgrade from now till A+, there's quite a lot of things that are undecided now. For example, mirror coatings are undecided now. What coating will go on the mirror? There are various teams all over India that are taking part in this research. These include ICERs, IITs, several campuses of BITS Pilani, and other labs. And some are quite heavily involved in the research that's going on now. So eventually, the $100 million worth of equipment that LIGO is going to give us, the detectors as well as the equipment that's going to come, will arrive, and only, as I said, some parts of them will be upgraded. The mirror, for example, is a big element of it, and there are plans now of how that will be done. And that's been all budgeted for
so that the amount might have been much higher than what we talked about in 2016.
Yes, absolutely. Yeah, and so in 2016, the cabinet approval and the amount that has been asked for from the cabinet now is probably a factor of 2.5 more than what we estimated.
Yeah, that's the problem, right? Yeah. So
yeah,
thanks.
Yeah.
More questions? I don't see.
Hi, Somak.
Yeah.
You said you are working with schools, more than 100 schools. What kind of the work that involves? Because 100 schools means you require a lot of human resources, or I don't know what kind of work.
So we actually our plan is to work with many hundreds of schools, but we started with about 100. We have an outreach team that has been recruited with very little money, both IUCA pulling together as well as from LIGO resources, of local people who actually are educators in the region, who go around schools. The people you see in these pictures are actually a team from IUCA, with one person there who's local. But we have people there, and we have star parties. We have people going to schools and giving lectures on basic physics, science. And for example, if you look at the bottom picture of the people raising the hand, the question that was asked to all these kids was, who wants to be a scientist? And then everybody says, me, after a whole day's worth of nice talks on various aspects of astronomy. So this is the kind of engagement that this team has done. And we have now about 24 people who are involved in this. But this team will grow because we have plans of doing this in 3 different districts.
So these 24 people, basically, you are paying the project, is it?
That's right. At various, I mean, not at the 24 people who have been involved, haven't been involved for 3 years, but this has grown and then now shrunk during the pandemic. A lot of these activities had not happened, but these are all hired on a monthly basis, 3-month basis, small project appointments, and they are trained by. We've had people who are recruited locally in Hingoli and as well as Nanded, and they've been brought here. They've been given training in Pune, and they've gone back to do work with the schools there. And this will expand. This was
that's a very good initiative from the start itself. So you are making the entire neighborhood as the stakeholders of the LIGO project.
That's right. That's very, very important. And we have a very good relationship with the local MP, the local divisional commissioner, the 3 divisional commissioners we've had in the last 5 years. All have been extremely interested. The IS officer who's the district magistrate now actually has a scrapbook in his office of cuttings of LIGO news from all over the world. He's so interested in it. And so he has, so that kind of stuff. And we work with people in the administrative level as well as the local people, because I mean, of course, we have examples from many other projects, as you know, where the local people are very important. They can easily turn against such a alien thing coming to their environment. So this works. We figured that in IUCA's science outreach, we work very well with schools, and often the population, the village population, are very interested in what their children learn. And so that is a place where we started to focus on the children. And then I think this is going to expand, because there are in the plans of LIGO, both on the site as well as in Hingoli, there are 2 science centers that are already in the plans. And this will have a small planetarium, science center, where people will come and visit and things like that, which will all include local people.
Okay, I don't see any more hands raised. Gopu, is this the one from your earlier one, or do you have any other question here?
I see that the chat box question has been answered very well by Anupama. Thank you very much, Anupama.
I have already asked. Thank you.
Okay. So I don't see any more hands raised. So if not, then let's thank the speaker again. And that brings us to the end of the first half of the morning session. And let us thank all the speakers for their wonderful talks. And I hand over the mic back to Shashi for any announcement. I guess.
No, I don't have Pratik. Thank you very much. And let us meet after the tea break at the decided time. That's 11:50.
Meet at 11:50.
Yes.
Okay. Okay. Thank you.
Yeah. Thanks.
Hello, Shashi. Are you there? This is Yashwant. I just joined.
Yes, sir.
Do you want to just test the screen?
In case, yes, please do that. Yeah.
Okay, just give me a minute to set this so that. Is it advancing?
Yes.
Okay, fine. Then I think we are all set.
Yeah. Okay.
I can easily unshare it now.
Yes.
Yeah. Okay.
Yeah. Thanks.
All right, good. So I'm ready whenever you all are.
Maybe in another few minutes.
Yashwant, Ram here. Can you hear
Hi.
me? Hi, I have a question before your talk.
Hi. My goodness. Like you saw my talk somewhere already.
No.
Go ahead.
Is that background real or is it a Zoom version?
You have a supplementary or accessory question. Okay.
Yes, yes.
Yeah, no, I leave that for you to. I mean, I wish I could have a view from my window like that, but it's part of what Zoom allows you to set up.
Yeah.
Except that it's been combined with a little bit of a trick to put it over there.
That's right.
Oh,
So
I was also wondering how you managed to get it done, a side view like a window.
There's a way to do that. So what happens if you set a background in Zoom?
Right.
Normally it requires a complete green or bluish background to show it properly. But there's an option there where you can select some part of your background which you want most favorably to map onto your picture. So this, for example, if you have something very white, which is what the view of the sunlight from the window is, then you can ask the Zoom background to optimize it for that.
Oh.
So the background image is there actually even across my face, but since it is optimized for the white background, it shows up predominantly over there.
Oh, I see. Okay.
But if you don't have that contrast in the background lighting, then it's hard to make it happen.
But this is very nice, actually.
It's fantastic.
yeah, it's very, very deceiving. I mean, the last time you gave a talk, I wanted to ask, then I thought this is not an appropriate question for the end of the talk. But now I have a chance. I thought, okay, maybe beginning
I
of talk.
actually thought you had got, this sunscreen made with this image.
No.
Yeah. Very
so
nice.
it does interesting things. If you're sitting there as it gets dark, when the light starts fading, then that picture will sort of not come through that nicely.
Oh, okay.
So it is just, so if you look in the Zoom background, at the bottom, there is an option where you can select which part of your background you want the image to sort of best match to.
Oh, I see. Okay.
Studio effects.
Hello. I guess it's past 11:50 and we should start. But Shashi, are you around? Should I go ahead and start?
Please go ahead.
Okay. So welcome back after the tea break. And we have now 3 talks before the lunch break. And the first of that would be delivered by Professor Yashwant Gupta. And he will be talking about the Square Kilometer Array project. Yashwant, please.
Yeah, okay. Thank you. And let me just share my screen. Okay, can you see my screen?
Yes.
Yeah, okay. And I'm sure you can all hear me. So let me start. Thank you very much for giving me this opportunity to give an update on what's happening with the Square Kilometer Array project, and specifically about what's happening with Indian participation in the SKA. So my talk actually will naturally split into 2 parts. First is just an overall update about the project, and the second part, I'll talk more about what is going on in India vis-a-vis the SKA. So the SKA, as most of you would know, is the next generation facility in radio astronomy. And so if you just look at the history of radio astronomy facilities over the years, you will see that the steady increase in the sensitivity is like, if you want, the Moore's law of radio astronomy. And the GMRT, when it was originally built and conceived, the legacy GMRT sat there. Today, the upgraded GMRT is further up on this scale. But what the SKA promises is, way outside of the current scale, which means something which is at least 30 to 50 times better than anything that exists today. That's the full SKA. And that requires a square kilometer of collecting area, and hence the name Square Kilometer Array, which would be made up with a very large number of antennas, relatively smaller size compared to the 45 meters of GMRT, but with much higher resolution spreading out to thousands of kilometers in the final configuration, and with a very large frequency coverage, which then requires it to be split into separate instruments, because no single radio astronomy receiver can really, or antenna can cover this kind of a range. And so it naturally ended up being split into two telescopes, one located in Australia to cover the low frequency part of this, and the other in South Africa to cover the upper end of this frequency range. And I'll show that in a minute. And I'll also talk about the kind of cutting edge science that this promises. And just to, in a nutshell, it has completed the design for SKA phase 1, and I'll explain what is phase 1 in a moment. And the construction is expected to start by the end of this year and to be completed by around 2027. And so that would put it in the league of all the major 21st century observatories, some of which are already operational, some which are going to come up, and some in which India is a major partner, like, for example, on the optical side, the TMT, and on the LIGO side with the LIGO in India. And so in that sense, the SKA will form a facility which complements this, this setup. So I'll talk briefly about the science with the SKA, and it goes all the way from the formation of the first stars and galaxies in the universe to all the way to searching for extraterrestrial intelligence or life in general, but also extraterrestrial intelligence. And so that the range of science is probably one of the broadest amongst all these next generation facilities. And I'll just go through some of them. I probably won't have enough time to dwell in detail. But the summary is like this, all the way, like I said, from the epoch of ionization and cosmic dawn through all other aspects of cosmology, dark energy, evolution of galaxies, cosmic magnetism, transients, of which there are plenty now that we know about, strong field test of gravity with pulsars and black holes, and cradle of life, astrobiology, detecting protoplanetary disks and searching for extraterrestrial intelligence. And then, of course, if you build something which is an order of magnitude better than whatever exists, you're going to find new, unexpected, hidden surprises from the universe. So serendipity will always be there. And so just an example of what SKA promises. So at this 10 to 15 gigahertz upper end of the SKA, should be able to start seeing some of these kind of protoplanetary disks in great detail. From there, just another example, the claim that the SKA makes is that it will detect all pulsars in the Milky Way. That probably is true, but we will have to, it'll take a while to get there. Because there are of the order of 10 to the 5 that need to be found. But the point is that it will significantly increase the number of pulsars, especially of the order of thousands of millisecond pulsars and relativistic binaries. So all kinds of strong field tests of gravity and those kind of things will be possible. And the additional thing is the potential to detect gravitational waves, the low frequency end of the gravitational wave spectrum, which is done with pulsar timing and with the issues or aspects related to the CMB. And all of this will be accessible to the SK, and it's being designed to definitely cover some of these science goals. Moving from there to talk just briefly about magnetism in the universe, there are various kinds of things that the SK will allow to be done in much, much greater detail and accuracy than what has been possible with any of the existing facilities. And again, this is something very exciting and promising. And this one that we all know that the early universe, the EOR, and detecting the first stars and galaxies, of which a lot of work is being done with the precursors and the pathfinders, but it's expected that the SKA will have sensitivity to actually detect individual objects in the early universe. So what is it that is being planned? It's a telescope that's spread over 3 continents, in the sense that there are 2 sites, one in Australia and one in South Africa, where the telescopes will be located, and a headquarters which will be in the UK at the Jodrell Observatory. And the design phase, which, like I said, is completed, which involved a large number of countries coming together and working for the different design packages, which I'll talk about a bit more in detail. And the phase 1, which I'll describe what exactly the phase 1 is in terms of quantitative numbers. But like I said, to start by end of this year, with a 6 to 7 year timeline for building. It will also integrate Meerkat, which is one of the precursor facilities in South Africa, which antennas you see in the background, into the SKA mid, which is the part of the SKA to be located in South Africa. And then there is plans for a phase 2, which is the full SKA, likely to be launched in early 2030s, based on how phase 1 progresses, which would really meet that initial target that I talked about, that 1 square kilometer collecting area with many more dishes and dipoles. And so that then brings me to define what is phase 1. So phase 1 is basically a subset. It's a bit more than 10% of the full SKA in terms of capability and sensitivity, and with a slightly reduced coverage, which is compared to the frequency coverage of the full SKA, and reduced baselines compared to the full extent of the SKA. But all designs and construction to be done, keeping in mind that there will be a phase 2, which will expand on this. So infrastructure, facilities, and all of that to be built, keeping that in mind. And like I mentioned, the 3 locations in terms of the 2 sites in the HQ, and this was the design phase that formally concluded in early 2020, and the construction phase that I have been talking about, with the total cost estimate, which is of the order of 1.8 billion euros. And so this is what the SKA mid in South Africa will look like. Will be located in the northern part of the country, what is called the Northern Cape, which is a sort of a semi-desert area with very little population density. And this will have, in this phase 1, 200 dishes of 15 meters spread over 150 kilometers, and will integrate the Meerkat into it. And the SKA low will be located on the edge of the Great Australian Desert, but again, not too far away that you can't get resources out there to build things, but still reasonably far away to block man-made interference. And this is a different design. It's not dishes. It is actually stations of dipoles. So each station will have the order of 512 or 1024 dipoles. And you can think of a station as a rough equivalent of 1 dish or antenna, and there will be a few hundred such stations spread out over the array. So in the end, there's basically a large number of dipoles which will finally need to be combined to give the final signal. And the headquarters is now in a brand new building that was just completed about a couple of years ago. It's sitting under the watchful eyes of the giant Lowell telescope, which is where the entire project will be run from. And in terms of technology, the SKA will be as challenging as it will be interesting from the point of view of science. And the technology frontiers that it will be pushing will be large and varied, all the way from, advanced and diversified antenna designs to cryogenically cooled low noise electronics, to extensive fiber networks of petabits per second, and supercomputing capability of the order of petaflops, which is required to process the data both in real time and then quasi real time for the processing and getting the final images and the data products. And to manage all of this, sophisticated management and control software, which can manage this distributed observatory spread out over these 2 continents. And finally, to make sense of the data, which will be humongous in volume, I'll show that in a minute, all kinds of modern techniques from machine learning, AI, and others that will be required in order to get the best out of the data. And I'll just now show you some of these examples of the kind of technology barriers that we'll be pushing. So this is just to give you an idea about the various technical aspects ranging from number of antennas or number of dipoles in the structure for both for the phase 1 and the full SKA, to the total signal transport requirements for bringing the data for the processing, and the signal processing requirements, and the software and related challenges, and the high performance computing requirements to finally analyze the data and get the results, and the final data storage requirements, which are again in the range of exabytes. And last but not the least, the requirements on just basic power required in order to run this, which goes into megawatts kind of a scale even at SKA phase 1. And so all of these are significant, and I'll just briefly touch on some of them. This is an example of what is required in terms of antennas and electronics. These are the different bands of SKA. The SKA low has this band 50 to 350 megahertz with 300 megahertz bandwidth, and SKA mid has different distinct bands which will be supported at the secondary focus, which again have significant bandwidths. The bandwidths at each of them is of the order of gigahertz, which is stupendous in terms of what is required for the processing, not to mention the quality of the electronics needed to achieve that. And when it actually comes to getting this data from each of the two telescopes, these are the numbers. So you can see petabits per second required to get the data from the antennas over optical fiber to for SKA low, there's a local processing at each station. And then the data from the station, beamformed data from the station, then goes to the central signal processing, which you can see is of the order of 50 petaflops for each of the two telescopes. And from there to the final image making or post-processing, for example, for pulsars, it may be pulsar search software and timing software and so on, which computing is again 130 petaflops kind of a requirement. And all of this yields data which is at least 300 petabytes per year, which will go into the final archival systems. And so all of this, each of these steps is a major challenge in terms of building stuff that can do this. And just again, to give you the scale, this is what the SKA archive, and we are now talking 2028 kind of timeline for this kind of a thing to be ready, compared to some of the largest data archives that are used in other areas of human activity today. And so, as you can see again, that's at that scale where it is right there up with the largest things in the world. And finally, this data, though generated at the two sites in Australia and South Africa, has to be accessible to all the users in the global community. And therefore, it needs to be transported from there. And the plan is to have regional centers distributed amongst the member countries, where this large parts, if not all, of the data is available. So all of it will be available across all the regional centers, and maybe individual countries may focus on things that are of more specific importance to their community. And this then entails all of this business as to where are the data links available in the world, the global optical fiber links, and will they be able to support this? What will be the cost? How do you prepare for it? And so all of this study is ongoing right now in order to be ready to have this data stream out and be available to different locations amongst the user community. And then, as I said, to manage this as a end-to-end functioning observatory, all the way from users putting in proposals to the screening and approval of the proposals, to the proposal getting scheduled on the telescope, to it actually being executed in real time, and to interfacing it with the engineer or the operator or the astronomer. to making sure that that data that comes out of it is made available to the PIs, and that the result or outcome from that. So all of that end-to-end management is a complicated task here, which is called the telescope manager, which was something which I'll talk about in more detail a bit later. And this was the aspects of the power challenge. As I said, we are talking tens of megawatts of requirement. And so already the SK is looking for green options, which would be possible where you may not need to draw that from the regular grid. And some of this is being already tried out in the Australia site, where there is a large solar array running, which promises to power a good part of the existing systems and some of the future ones as they come up. And so that brings me to who are the people who are working together on this. It's a global partnership, and you can see a large number of countries that have been working from the beginning of the design phase. And there are others who are interested. Some of them have moved over from being interested to joining, like Portugal, and Switzerland is close to joining. And so this is a large collaboration, and we've been there in the project since the early days, and I'll come to that in a minute. In terms of how it's being managed, the governance structure, the phases up to now were managed by a not-for-profit company that was registered in the UK. It was called the SK organization, and we were all members of that via an agreement that was signed. But now it's transitioning to an intergovernmental treaty organization bound by an international treaty, which is going to be called the SK Observatory. And that's the entity that will now manage the project from the construction phase onwards for its entire lifetime. And these treaty documents were worked out in negotiations which involved all the interested countries, including India. We also participated. And these, the main treaty documents have now been opened for formal signature and ratification. It's now almost 2 years since that has happened. And in that period, 6 countries have completed the process of ratification and have now formally joined the SK Observatory Council. These are the ones that are listed here. And some of the others, which includes us, are in the process of completing this process of final approval from the government and joining the treaty to become full members. Meanwhile, with the minimum number of countries already signed up, the SK Observatory actually came into being formally, 2 months ago now, and the first meeting was held in February, where those who had not yet joined participated as observer countries, and the council has now started looking into the plans for the construction phase. And so that brings me to the broad timeline. The design, like I said, was completed in March 2020, and that defined the design baseline. That is, what is it that is aimed to be built? And the construction proposal for building this has now been prepared and is ready, and it's expected to be approved by the new council by July of this year. And the funding commitments from different member countries expected to be firmed up again by the middle of this year, which will allow the council to decide the scope of the project and then decide what is called the deployment baseline. That is, what can be built with the available money to get going. And that difference will hopefully be made up over time with additional countries joining and committing more funds. And that's one good thing about interferometry array, that you can scale it and build it in phases. If you don't have the full 100% funds required, you can still start and keep adding to the array as more and more funds come without affecting the functional availability of the working of the part that's already been built. And so this is expected to kick off in terms of actual activity on the ground by the end of this year and go on till 2027 with phased releases of, again, you release the growing array in consequent in incremental phases from 2024 onwards. And so that will allow early science to be possible as early as 2026 kind of time frame. And the full operations phase expected to start by around 2028. So with that, I'll just move over to what's been happening in India. And, as we know, India has traditionally a good base for radio astronomy going all the way back to 1960s. And today, in addition to NCRA, RRI, there are several other institutions in the country that are actively involved in radio astronomy at the global level, be it in technology or in science. And we have world-class facilities like the GMRT, where we have cutting-edge experiments in radio astronomy happening, which are very good preparatory ground for preparing for the SKA. And in that sense, the GMRT formally enjoys the status of a SKA Pathfinder facility, which is applicable both for science and technology development aspects. And you heard a fair bit about what's currently happening with the GMRT a couple of days ago from Jairam. And so I won't dwell too much on that, except to just show that the role that the GMRT plays after the upgrade vis-a-vis the targets of the SKA phase 1 and the full SKA, it shows that this is an ideal stepping stone for the phase 1 SKA in terms of the quality of the science that can be done given the sensitivity that it affords. And in addition, there is other experience in India. For example, RRI has been part of the MWA international project, which is also a precursor for the SKA. It's located at the SKA low site in Western Australia, and that's something that's been going on there for some time. And that's been very good participation with a lot of hardware built in India and supplied to the MWA, working wonderfully for the last several years. And there's a very strong and vibrant community that I have in India, been actively using the various SKA precursors and pathfinders for carrying out interesting research. And in terms of being part of the SKA, we've been there since the early days, 2010 onwards, when we started the first work in contributing to the design of the SKA monitor control system, which then gave us the motivation to join the SKA organization as a formal member in 2012, which translated to a full membership of the Government of India with the DAE representing us in 2015. And that then has gone on to allow us to contribute actively during the design phase with significant contributions to some of the design work packages. All of the activities in India are coordinated by the SK India Consortium, which we set up in 2015. And now you can see here that over the years, we now have more than 20 plus institutions in the country that are members spread out all over the country. And the SKIC really coordinates everything, both the science and technical activities via two subcommittees, which look after the individual facets of this work. And this has worked out very well in terms of bringing together the community in the entire country to work in a coordinated manner towards the towards SKA. And here's an example. The first science case document was produced by the community in 2016. This was about the time when we held the international SKA International Science Meeting in Goa. And from there on, it's been worked on and refined, and there was an updated version in 2018. And now there's a further updated version that has been produced as part of the final DPR that has been submitted to the government for approval. And already we have more than 100 faculty, postdoc students involved from these institutions, and we are expecting that to be more than doubled by the time we are ready for early science with the SKA. And so these members, we have our own science working groups in the country, but the members also participate in the international SKA science working groups, and some of them have leader roles in some of those. Okay, this, if you want to see more details, the full detailed document of the SKA science is available on our website. This is just a snapshot from this meeting, which really made the SKA science case much more popular within the community in India. I'll move on then to describe a bit about what's been happening on the technical side of things. As I said, we've been involved in the design phase. We worked in 3 different work packages: the telescope manager, where we were the lead country, and central signal processing, and the signal and data transport. And so the one where we were the lead, we worked with partners from software research groups and industry in order to come up with a design for the telescope manager. And as I explained earlier, the telescope manager is one of the critical systems because it does the end-to-end management of the entire observatory. And this was an activity that we led with collaboration from 6 other member countries of the SKA. And we were, in fact, the first to complete our design. So there's an example of the collaboration that this was interesting because this really, brought out the international nature and how you need to work with members from different countries, each of them having their own industry partners coupled into the process, as did we. And that is something that has really helped to build up a model of how to involve partners, including industry, for doing some of these things. And one of the aspects of this was there's a direct synergy with our own in-house activities. So, for example, the design that was done for the SKA telescope manager was then aligned with the upgrade of the GMRT for producing a next generation monitor control system for the GMRT, which is now in place and is being used as the default monitor control system for the GMRT. And that again provides valuable experience on how to do this, exactly what a Pathfinder facility is meant to facilitate. And this is something that now has been agreed that India will be leading this work packages for the construction phase. And in addition to that, so this was when we finished the actual design work in 2018. We were one of the first consortia to finish the work, and this was very highly appreciated both by the SKO and by local and within the country. We also participated in the central signal processing and signal and data transport, and we now have been also contributing after design phase was over in the early prototyping activities. And we have also now entered into the SKLO digital signal processing activity post the design phase, and we will be part of this work packages during the construction phase. In addition, the SKA puts out what they call the SKA data challenges, where they aim is to put out data sets, either real or simulated, which would challenge people to get ready for what data analysis in the SKA regime would look like. And we've had good participation from India in the data challenges. In fact, the one that's going on right now, Data Challenge 2, has as many as 9 teams from India participating, which is really encouraging in terms of what our community should be able to do going forward. So coming towards the construction phase, we've now identified the work packages that India will be participating in, and that forms the basis of the DPR that we have prepared and is now under the final stages of approval. So we will be the lead country for the telescope manager work package, which will be done largely with industry partnership in the country. We are also one of the major contributors to the SKLO digital signal processing work package, where Italy is the lead country. And this work will be led from RRI with other SKIC members contributing. And again, a large fraction of this will be done in industry. We are also part of the SKA mid, one of those bands. I showed you the multiple bands for SKA, the lowest frequency band, which is the one that will have the antenna as the feed antenna and the receiver work package built in India, along with Sweden as the lead country. And we are also part of the science data processing team in contributing to the Pulsar search processing system, where both RI and CRA have interest and have participated in the even in the ongoing prototyping phase. Overall, our contribution adds up to about 6 to 7% of the total of the SKA. In addition to this, the plan is to have a in-country regional data center, which will house a good fraction of the data relevant for teams from India. A significant amount of human resource development is also included in our proposal, as well as in-house, in-country R&D program to supplement what we build and contribute to the SKA. And so that then brings me to a summary, which I'll put here, and I'll leave it open for questions.
Thank you very much for this interesting talk on the update on the SKA project. So it's time for a few questions. I do not see any raised hand at this moment. Are there any questions on the chat box? Let me quickly have a look.
Sir, can you?
Yes, please go ahead.
Can you give some outline of the data analysis? Because, like you said, it's the largest data that will be flowing, and of course, a lot of machine learning. But is there some special plan that is there in the making? Like,
I'm not sure if you are asking for the plan for how the data will be shared and housed, or plans for how the data will be analyzed.
sir, analysis point of view.
Yeah. So this analysis point of view is exactly exemplified by what I talked about, the data challenges, where actually the SKA is preparing the community for what kinds of data analysis challenges and techniques will be there by putting out these data sets, some of which are from the existing facilities, some of them are simulated. And this is something that is really helping the community to get accustomed to this, in addition to the fact that the precursors and pathfinders, though smaller than the SKA, offer similar kinds of challenges, though on a smaller scale. And in that sense, if you've become a black belt for analyzing, say, UGMRT data, then you're already, well on your way to being able to handle SKA data, though there is still another step there. So these are the ways in which we're getting prepared for doing that. In addition to that, there is, of course, when you say what is inside those, that is a matter of detail. It could be things which allow you to meaningfully extract the signal from the noise or even unwanted RFI, to techniques which allow you to be able to classify the kind of sources that you are detecting, which could, all of these could use machine learning and other techniques, which already people are working on to show that. And then finally, there is that aspect where, the aspect of mining the data, which is already archived. And then, so there are all of these that go into the analysis techniques. I don't know if that gives you a feel for the things. But if you would really like more details, it would be useful to join one of these data challenge groups from India that are participating right now.
Okay, sir. Yeah.
I can put you in touch with them.
Yes.
Yeah, Professor Rama Prakash, please go ahead.
Ashwant, you mentioned that one of the regional data centers, there's an intention to set that up in India. Does it need any kind of, are you looking at any kind of exotic or plans for it? For example, I'm asking things like Microsoft is setting up data centers under the sea because the enormous heat management problem. I mean, does any of that kind of challenges involved in setting up some data center like this, or in 10 years from now, this is all going to be routine and it's not going to be a major issue?
Now, that's an interesting question. So we did grapple with all this when we put the things in our proposal. And what we've done is, of course, the proposal is based on extrapolation of the more conventional ideas or techniques right now. But then it does allow for a prototype one to be done in the next 2-3 years in order to, gain a feel and understanding of what may be the challenges for the full-scale one. And, and it's possible that the full-scale one may end up looking for some of these other innovative ideas. I don't know whether we can go under the sea, but there may be other things that one may want to look at. But I would say that that's still a bit up in the air, open question as to what you would want to build in 2025, 26 onwards, which is when the serious thing for assembling the SK India Regional Center will start. But there will be a prototype that on a much smaller scale that we will, in fact, we are going to start some of the initial procurement for it from this year onwards.
Okay, thank you.
Are there any more questions or raised hands? I don't see any. Okay, so if not, let's thank the speaker again, and we move on. Our next talk would be by Professor Abhijit Chakraborty from PRL, and he would be talking about the 2.5 meter PRL telescope project. Professor Chakraborty.
Yeah, let me just share the screen first. Can you see it?
Yes.
Okay. Yeah. So the PRL 2.5 meter project, I will be giving a very description about this project. So let's start with the timeline. So this was initiated around April 2014, and then the contract was signed with Amos, Belgium in early 2016. And by 2017, end of 2017, most of the important parameters through PDR, CDR, and NDR were fixed. And then in 2019, we had for 3 months, 4 of our engineers had spent 3 months at Amos facility to get complete telescope operational training, maintenance, and they also participate in the telescope assembly. So today we have the complete SolidWorks model of the telescope, which tells us which parts goes where. Actually, that's very essential, for long-term, like maintenance of the telescope. Then the factory acceptance test happened in October 2020 via online because of the ongoing pandemic. And the telescope data was transferred to us with various images. I will briefly describe those things in the following slides. Meanwhile, the observatory building was built by ISRO through SAC-CMG, the Civil Department of Space Application Center, and it was handed over to PRL in January 2021. So basically, we designed and the building parameters and everything, and then it was cross-checked by ISRO, and then based on our requirements and suggestions, the building was made. And the telescope boxes have arrived at the site in February 2021. Okay, so this is how the new building looks like beside the 1.2 meter building. So now I come to the factory acceptance test that happened in October 2020. So here we see the telescope being completely assembled at the factory, and then we'll be doing the sky test. So basically, as you see that, the measured performance in terms of, jitters, pointing accuracy, and both sidereal and non-sidereal tracking seems very good and well within our requirements. Then we also did, the open loop and closed loop parameters of the telescope, and which again are well within the, our requirements. So, for 1 hour tests were done, almost up to 1 hour tests were done. Here I want to say that the Amos facility in Belgium is as far as like telescope sites are concerned, is a very bad place to do any of these tests. Because most of the time it remains cloudy, and then large temperature difference, turbulence. But however, after like this, we kept on trying this for almost a month or so. So So we got some few lucky nights where we were able to, get the proof that the telescope is actually working. Okay, so these are the mirror polishing parameters. As you see that the surface quality of the mirror is pretty good. Perhaps one of the best in the country, 26 nanometers RMS surface polishing area of the M1 mirror, and the M2 mirror is 11 nanometers. Our requirement was that the complete optics, that is M1 and M2 together, we should have about 70 nanometers wavefront error. So that forced AMOS to do this kind of critical polishing. Okay, so here what is the budget is actually that after active optics correction, what we require is about 70 nanometers on the both on the main port and the side port, and they are within error budget. And of course, the peak to value is around 100 nanometers. So considering the site characteristics to be about median seeing of 1 to 1.4 arc seconds, something around. So this kind of telescope characteristics is considered to be very good. Okay, so we did the lucky imaging on that because the atmosphere is very turbulent. So we had to give 10 millisecond exposures, several 10 millisecond exposures to do the to check the actual telescope mirror function with respect to active optics and various other control systems. And so the first thing is that we did is that that we asked AMOS to give something around, I believe, around 8,000 10 millisecond exposures on a bright star, and then look out for the best 10 millisecond. The atmosphere is supposed to be partially frozen. So even if the seeing is about 2 arc second or 2 to 3 arc second, one has to, when at 10 milliseconds, the seeing should be significantly better. Even though it may not be very ideal, but still in that we were looking for, out of 8,000 frames, looking for frames that are pretty good, and see in those good frames what are the the FWHMs. So we could identify about first 100 out of 8,000, about 100 best frames, and from 100 good frames, and from that 32 best frames were identified. And in those 32 best frames, if we do shift and co-adding, that is matching the centers of the stars, then we get about 0.66 arc second. And then if we look at the statistics of those 32 best frames, you can see about 10 of them have actually 0.3 arc second FWHM, and you can see this is the distribution of the 32 FWHM of the 32 best individual 10 millisecond frames, and the best ones gives about 0.31 arc seconds. So that shows about this was necessary for us to determine whether the active optics is how good the active optics is working, because one of the stringent conditions we had was that under good seeing conditions, we should be able to get down, the active optics should be able to get down to a correction up to a level of 70 nanometers or less than 100 nanometers at least. Okay, and the technical evolution committee, which was composed mostly from ISRO, and they were very particular that unless we get some proof that the system is working, because it is going online, so we have to have this kind of proof before we can say that the factory acceptance test has been passed successfully. So so therefore this kind of exercise was necessary to do. And so for 0.31 arc second, let us see where is that? Okay, I think I have missed one slide. So 0.31 arc second slide FWHM actually corresponds to about wavefront error of about 110 nanometers, and 0.25 arc-second corresponds to about, I think, 70 nanometers, what is we required. So since we were very close to what is to be achieved, and even though the under very bad seeing conditions, so it was considered exemplary good, because it's we all astronomers, particularly optical astronomers, know that achieving FWHM of 0.31 arc-second even with the lucky imaging is not an easy task, and it was achieved. So we are pretty happy about this result. Okay, so here actually you can see the total the cumulative FWHM in terms of exposure times of all the data, that is without actually shift and coordinating, simply stacking the images without matching the centers. So you can actually see it tends to go towards 2 arc-second, whereas the individual frames, it shows actually close to 0.35 arc-second. Okay, so now this was about the telescope. So as I said, the telescope has been deassembled from Belgium, and it has come to the site. Building is complete. So now we are actually waiting for the people to come here and install the telescope. So because of the ongoing pandemic, looks like there is some delay in their arrival. So we are working with them as to the best time for them to come here and install the telescope. Okay, now regarding the first light instruments. So as many of you must know that one of the main program for the 2.5 meter telescope is exoplanets. And so first light instrument, one of these PARIS-2, which goal is to achieve 50 centimeter or better with spectrograph around 100,000 between 380 to 690 nanometers. Okay, and the vacuum stability is about 10 to the minus 3 millibar, and temperature stability of roughly 0.0011 millikelvin at 24 degrees Celsius. That's the whole idea. So since we already have enough experience building PARIS-1, so we have certain confidence that we will be able to achieve this without much, with some minimal experimentation. The wavelength calibration, we like as you all know that usually people use thorium argon or laser frequency comb or the Fabry-Perot frequency comb. Right now, like we are having thorium argon and uranium argon lamps, and we are actually, because thorium argon lamps, pure thorium argon lamps are no longer available in the market. By pure thorium argon lamps, we mean that the thorium content should be at least 95% pure or more, whereas in the market currently what is available is about 60% thorium, and rest is only thorium oxide, because of which you get a lot of thorium bands, and they actually reduce the precision of the wavelength calibration. So that is actually a major setback for the exoplanet community. So therefore what we are now doing is we are looking into the other atomic lines which are similar to thorium, which is uranium-238. And fortunately, these lamps are easily available from Photonics, for Photon holocathode lamp company in Australia, and they actually we are working on their calibration technique, new technique, which very people have actually attempted, and we have got with PARIS-1, we have already shown that with uranium argon lamps you get the same precision what we got with thorium argon using PARIS-1. So that is one work that is ongoing work, and so we plan to use the uranium argon lamp specifically with PARIS-2, and in future laser comb frequency may be considered, but like considering the budget constraint these days, because laser frequency comb is very costly, it's almost €1 million cost, and currently we don't have enough budget to work on laser frequency comb, but we in future, if budget is available, we may consider that. Okay, so along with the the telescope, we are also having for the first time in the country a tip facility for first order seeing atmospheric seeing corrections, and it will be dedicated for the PARAS-2 fiber input. That is, like the PARAS-2 fiber is 75 micron core, and so it corresponds to about 1.5 arcsecond on the sky, and that is the telescope is f8, so we convert it to f4, and then it is pumped into the fiber, and so the idea is that the stability, if one wants to go sub 1 meter, the stability of the star on the fiber tube should be very stable. So additional to the very good tracking accuracy of the star, this tip tilt arrangement is done so that the partial seeing corrections are made. So even if the C is about 2 arcsecond, so after working at 20 hertz or so, this can be corrected to down to like between 1 and 1.5 arcseconds, so that most of the light is injected on the 1.5 arcsecond fiber. So, and this is the optical layout of the spectrograph, and so the spectrograph has already been made in the in Thaltes campus. We had a special facility, clean room facility, where you can see that the spectrograph being assembled inside the vacuum chamber, and here you can see we took the solar light spectra at 100,000 resolution. So this is I believe it's for the first time in the country we are having 100,000 resolution initial spectrograph working. And so this is a sample of I think initial order number 103, where like you can see nicely the solar spectra. And here is another shot of the inside spectrograph, where you can actually see the eshell, very nicely eshell, then the fiber launcher, the grism, and the camera lens barrel, and the detector with the shutter. And especially so this is about the PARAS-2. So we have another CCD instrument that will also come up with the telescope along with PARAS-2, which is the simple CCD imager. It's a PRL 4K imager with a field of view of 10 arc minute, and you can see that we have used in PARAS-2 we actually build the whole camera ourselves, buying different individual parts, and we have built this thing. So but whereas in this case we decided to buy an off-the-shelf and/or camera because there are simply too many things in our hand to do, and we didn't have enough people to build another camera. So anyway, here what we wanted is that the camera should have very good efficiency all through, and you can see actual measured efficiency here. You can see that it is pretty good all the way from 350 nanometers to 1000 nanometers, and the BX2DT, this yellow curve, or rather the green curve, is what is actually the quantum efficiency of the CCD detector, and it can work at 100 kilohertz readout speed of 100 kilohertz, 500 kilohertz, 1 megahertz, and 3 megahertz. And the numbers are written too small. I will just read out. So at 100 kilohertz, the speed read noise is 2.1, 500 3.4, 4.6 at 1 megahertz, and 3 megahertz is around 10 read noise, 10 electrons read noise. So these are the standard thing. And when we received the camera, we actually measured it. These are pretty close to what numbers they have actually quoted in the pamphlet. And so the CCD will have new SGSS filter set for with high transmission for the PRL 2.5 meter telescope, and you can see that these are the new SDSS filter sets. This was first defined by Hypercam for William Herschel telescope and GTC. So we decided to buy the same filter set, and you can see that you get great advantage in the U band, particularly where like the earlier SGSS had a pretty much lower transmissions here, you can see. This is the earlier SGSS filters, and this is the new district. We got these filters already installed actually. So this camera will be coming up. So in principle, like by the time telescope gets functional end of this year, hopefully without much delay because of Corona, then both these instruments will be ready to be put onto the telescope. And the science targets for this is basically science of target opportunity to say that is nova, supernova, GRBs, and precision differential photometry for like many of the exoplanet candidates which are coming up from tests. They require ground-based verification, and for those work, this CCD camera will be extremely useful. Apart from, as you know, that PRL has a very strong team on Novae. And so this camera will be also used to follow up Novae and Supernovae work. So I think that's all I have to say.
Okay, thank you very much, Professor Chakraborty. So we have time for a few questions. Yeah, yes, Professor Ram Prakash, please go ahead.
Vijit, the image, excellent talk and really impressive progress with the facility coming up.
Thank you.
Very nice to see this. This image, the slide where you had shown a coordinate PSF with lucky imaging, it looked a bit elliptical. Is this just a display effect or?
No, that's the display.
So condors looked elliptical on that.
No, it is just like a I copied it from a PDF file, and those things by the time it was slightly.
It's just a display distortion.
Yeah.
Okay, great.
Okay, more questions? I don't see any more raised hands, and I don't see any questions asked on the chat either. So
yeah, I wanted to add one comment to Ram Prakash this thing. You see, we were pretty much concerned about because as I said that the atmospheric conditions were bad. So when we were doing the active optics corrections, they some of the astigmatic term was not completely going away. So we were pretty much concerned, and then we pushed Amos to make sure that work out on that. So and then after they did that, so we were able to get nearly circular.
Yeah, good to hear that.
But I guess that those issues probably will go away, at the site, because the site does not have such a bad
seeing, yeah.
Because the seeing was it used to come like 3 arcsecond and 4 arcsecond. When you see, you can actually see the star getting stretched like this. So,
yeah.
So, okay.
I don't see any more hands raised. So if not, so let us thank the speaker again. And we move to the final talk of the session. And it will be delivered by Dr. Brajesh Kumar. And he will be talking about present status of the upcoming 4-meter ILMT and science cases. Please, Dr. Kumar.
Am I audible?
Yes.
Hello?
Yes.
Okay. Thanks. So, hello, everyone. Good afternoon. I am presenting this talk on behalf of the LMT team and collaborators. And title of my talk is Present Status of Upcoming 4-meter International Liquid Mirror Telescope and Science Cases. So the history of liquid mirrors is more than around 100 years, and Robert Wood built first liquid mirror in 1909, and in meantime there have been several liquid mirror telescopes were built, but majority of them were for the technological demonstrations or suffered due to bad sites. So in context of today's talk, this is the outline. Mainly I will be discussing the basic principles of the liquid mirror telescope and what are the observing technique. Then status of the LMT project, various science cases in brief, and what are the major preparations for the first light. And the right side you can see the ILMT mirror, which was tested in AMOS a few years back. So these are the basic slide of for the demonstration of the basic principles. So if you see the right side, this is if a liquid fuel container is rotated along the rotation axis with the angular velocity omega, then due to action of gravity and centrifugal acceleration leads to parabolic shape with the focal length given by this formula. And here omega is the angular velocity of the container and g is the acceleration of gravity. And the liquid automatically compensates for thermal and mechanical deformation of the substrate, and we are able to get a good parabolic shape for the in context of the mirror. There are several advantages of the liquid mirror telescopes. So these are inexpensive and very simple design. Their maintenance is very easy in comparison to traditional telescopes. They are very good for imaging pointing toward the zenith direction, and continuous data acquisition can be obtained. And these are also appropriate for various scientific goals. So mercury used as a reflecting surface to form the mirror, and you can see in the right side. So in the optical wavelength, its reflectivity is more than 75%. And in the starting, we generally use 2 to 3 millimeter thickness of the mercury to form the mirror, and quantity around 500 kilograms. But it should be noted that since mercury vapors are toxic in nature, so we use less here while dealing with the mercury. Since liquid mirror telescopes are zenithal and they can't track the objects like traditional telescopes, so a specific technique that is called the time delay integration technique. So we use this technique for securing the images with liquid mirror telescopes. So basically in this technique, images are secured by shifting the CCD charges electronically. So that means that CCD charge transfer rate is kept equal to the local sidereal rate of the observatory. So but the exposure time is limited because the integration time is the time taken for an stellar object to cross the CCD image. In this picture, you can see that as the star is moving, so the charges are accumulated and finally we get the final image. So but the sidereal motion of the stellar objects are not uniform over the CCD, and this is called the TDI distortion. But this can be compensated with proper corrector before the CCD. So this is all about the general introduction, and this is the view of the 4-meter International Liquid Mirror Telescope. And the tall building, you can see this is the enclosure of the this telescope, and in the middle is the data room, and the leftmost is the air compressor room. some more details about this facility. It is located at the Devasthal, where there are already two telescopes, 1.3 meter Devasthal fast optical telescope and a 3.6 meter Devasthal optical telescope. This is a collaborative project between various institutions of India, Belgium, Canada, and Poland. The diameter is 4 meter with focal length 8 meter, and the field of view is around 30 arc minute by 30 arc minute, and we will use a 4K by 4K pixel CCD. Total accessible area of this facility will be around 50 degree square degree, and we will be using the GRI prime filters. The total integration time for single scan is around 102 seconds, and the right side is the sketch of the facility. So the base is, sorry, this is the air bearing and motor, and the container is sitting over here, and this is the vertical metallic structure, and the top one is the place for the corrector and the CCD. Okay, so here I am displaying the limiting magnitude of the LMT. So we have estimated the limiting magnitude in different filters. So for this, we have used these various parameters listed in the right side table. And you can see that this x-axis is the limiting magnitude, and the y-axis is signal to noise ratio. And for different filters, we can see that for single scan, we are able to reach around 22.8 magnitude in G prime. In R prime, it's 22.3, and I prime 21.4 magnitude, up to the signal to noise ratio of around 10. But the good thing is that we can co-add the images, because the sky is passing over each night is the same. So we can, if we co-add the images for 3 nights, then we are able to get a gain of around 0.5 magnitude. So this is good in the that context. From different regions, this telescope operation has been delayed, and however, since last several years, many instruments have been tested and installed at the Vestal site, and here you can see the left side is the compressor, two compressors for continuous air supply to the air bearing, and right side, this both images, these are showing the various pneumatic system and sensors of the telescope. And the top left is the corrector installed already on the top of the this structure, and then CCD and filter units are also installed. And the right side is the air bearing of the telescope. This is the present inside view, leftmost, and the top view in the right side. So you can see that this is the corrector and CCD unit, and the bottom is the container of the telescope. As I said previously, that mercury vapors are toxic in nature, so we must take proper care. So in ILMT, we will be using air pump to evacuate air from the beneath of the mylar cover, and which extract the mercury vapors by help of activated carbon filter. And there are 3 highly sensitive mercury vapor monitors for continuous monitoring of the mercury vapors. And since we are going to use mylar film, which will trap the mercury vapor, so it will be an addition to prevent the mercury vapors to spread in the environment. We will also use a high-grade PPE kit and various other safety equipments, including the mercury mask and cartridges for the safe handling. So in this picture, you can see this is the container and covered with mylar film. And this is the hose pipe. It is going through the activated carbon filter, and then finally it is going through the exhaust to the outside. So now briefly I will discuss about the science cases with the ILMT. So last year, 3-day online workshop was organized at ARIES to discuss various science aspects of the ILMT, and details can be found at this link. And here I have listed some of the major points. So it is the ILMT is unique instrument allowing deep survey of strip of the sky, and it will be useful to study the variability of the various sources, and wide diversity of the objects can be studied. We can also use this facility for search and monitoring of different types of supernovae, study of gravitational lensing, detection of quasars, and study of various other variable sources. It will be also useful to provide target for the larger facilities like DOT or VLT, ELT, etc. We are very keen interested in tangent science with the ILMT, and we have performed a detailed study of how supernovae detection can be performed and what could be the rate with the ILMT. So for this, we have considered various parameters, and average, we consider that an average observable sky is around 8 hours, and photometric nights are around 160 nights. So in this table, you can see that for different filters, different types of supernovae we have listed here. For so in a year, we should be able to detect this much of supernovae in different filters, and these are the list for core collapse supernovae of all types what we have listed. And if we co-add images and increase the signal to noise ratio, then for different nights, you can see that the number of supernovae detection can be increased. And this is showing the our scheme for the discovery and follow-up the supernovae. So new images each night will be obtained, and with help of reference images, we can perform image subtraction. And if there are some peculiar objects by inspection, if we have interest in a particular object, then spectroscopic trigger can be performed, and then if it is confirmed, then further monitoring can be done with ARIES facility or other bigger facilities for the follow-up of supernovae. So now these are some of the final slides. So I would like to say that ILMT first light was first attempted in around 2 years back, and after various precautions and various tests, but the mirror was found, but soon after the surface broke. You can see in this area, the surface has been broken, and therefore the mirror was not able to be completely formed. Later it was found that since we had slightly less amount of mercury, so it was not possible to prepare a 3 millimeter thick layer. So we later we procured around 15 liters of mercury, and we were expecting first light around a year back or so, but due to COVID situation, it has been delayed further. So to get ready with the ILMT upcoming data, we are presently using a 14-inch Celestan telescope that is installed in 1.3 meter the fast optical telescope floor, and we are using a big camera with 2K pixels, and images are obtained in TDI mode, where I mean, since ILMT will also work in TDI mode, so we are using this mode since this CCD can do both type of imaging, normal and so till now we have obtained around 60 nights in R-band observations have been performed this between October 2020 to February 2021, and observations are still we are continuing these observations. So testing of the pop line is under progress, and this is the setup of the telescope. So this is all about the present status and what we are planning for the upcoming facility, and these are the summary. So we are expecting that we will have the first light in post monsoon 2021, and yeah, so this is all about my presentation. Thank you.
Thank you very much for giving us an update on the ILMT project. So we have time for a couple of questions. Yes, Abhay, please.
Sir, I just want to check my understanding. Do we need to continuously keep the mirror rotating to maintain the parabolic skew?
Yes, that is right. Yeah, we have to, I mean, continuously rotate the mirror, a container. Yeah.
Okay.
More questions?
Yeah, it's lunchtime, so participants might be hungry.
Yes. So I don't see any other raised hand. So let me thank the speaker again. And then I think this brings us to the end of the morning session. So we go for lunch now, and let us thank all the speakers of the session of the morning session, pre-tea and post-tea sessions for wonderful talks. And I hand over back to Shashi for any other announcement that he may want to make. Thank you.
Yes, Pratik, thank you very much. I don't have any further announcements, and I request all of you to disperse for lunch, and let us meet again in post-lunch session around 2:30. Thank you.
Thank you. Bye.
Sri Kumar, are you around?
Ishwar, shall I try?
Sri Kumar, good to
Shall
see
I
you.
try? Okay, so
I can't hear you.
I was in another meeting.
Okay.
Meeting going on expo set. So
That meeting
Vishwajit
same
was always
terminal
there. Now, can I try the sharing? If you could take
Yes. Just want to check it.
If you get the current slide off, I can share.
I can't do that. Oh, this is.
They've left it shared.
Oh, no. You can't share it because Ceci has to
unshare.
Unshare and then provide you a permission.
Yeah, I also tried to share, but then it didn't permit me. So
yeah, Napuni. Sri Kumar, you said you had another meeting. This is on the same terminal or meeting somewhere?
I just got off that. We got some issues with Exposat. So Vishwajit's team, we have reviewed that. And so that discussion is continuing. So I just on that for some time. Yeah. Every time we solve one problem, that gets solved, then a new problem comes up.
Now the launching date is fixed, no? For all of this.
For what? Exposat.
No, yeah, Aditya won something I saw in Facebook, but I didn't.
Facebooks will give dates, etc., but we don't know. It's a complex mission, and we have to see. We just had some critical design reviews the last few days, and there's a lot of things to be done. And, it takes some time, but we should certainly launch in 22. Yeah.
22, yeah.
Right now we think of January, but that we can do in January is the only question.
Yeah, it's not too far away anyway. So. C is not there. I don't know. Is there anyone, Aries Nainital, C or
auditorium? I don't see any movement.
Someone organizers?
Yeah.
I think they're not back from lunch.
Yeah, I think so. Just calling Shashi. Hello. Hello. I've asked Shashi to unshare. He'll do it.
Okay.
Yes, sir, we did it.
Yeah. Thank you, Shashi. That's good.
Is that full screen or is it only
still? Yes, it is. It is in full screen mode.
Good. So
yeah,
all set.
Yes.
Arranging talks and then conducting these talks also now becoming quite easy in the sense there are very few technical problems as well.
Yeah. It's very handy.
Oh yeah.
With the Zoom. 7.
But I don't know for how long these YouTubes keeps these all talks with them. They store them. Because these are multiple talks and then sometimes most of them are very similar talks or same talks. So, across all over the world. Sure.
Storage is cheap.
If you have a YouTube channel, you can put up all the institute YouTube channel, you can put it there. That will remain visual.
Oh, okay. You can put some pockets like this. So it doesn't need to go to YouTube headquarters.
It is under YouTube, but it is under whatever. You can have a personal account or you can have an institutional account. Under that, it will be there.
But whatever now, these all talks are there in the YouTube. Where are they? They are all in YouTube only, no?
There are two things. One is live streaming. This could be different or it could be through YouTube. And you can also have an option of saving it and putting it. So depending upon what are the options you're using, it will stay there or not stay there.
Yeah. No, I was wondering about storing of all of these things. If it is their own disk space. But these are millions of talks, all over the world. So
no, this is only talks at a very small fraction. What about other things? There are a lot of media things are there, right? Videos.
Oh yeah, but these also might have increased enormously, across the fields and across everything.
So Amazon is selling storage space, making money on that.
Oh yes, yes.
YouTube also makes money on that through advertisement. So when you watch a video, you have to visit. You have to see the ad, right? So ads make money on it. The YouTube makes money on it, yeah.
But they rent out storage from Amazon.
Yeah.
So everybody's happy.
Yeah. Mm-hmm. And also internet provider is also happy.
Sissy, are you around?
So welcome back to this afternoon session post-lunch. And now I hand over the session to Professor Ishwar Reddy to please chair the session and proceed ahead with the scheduled talks. Professor Reddy, please.
Thank you, Sissy. Good afternoon and welcome to this last session of this 5-day long program. And this session is all about future space-based astronomy. The first talk is by Professor Sri Kumar from Indian Space Research Organization. He's going to tell about future plans of space-based astronomy in the country. Professor Sri Kumar.
Thank you. Thank you, Ishwar. Can you hear me?
Yeah, we can hear you well.
I must thank the organizers of this meeting, which is an extensive meeting. Though focus was on astrophysical jets and observations, it's nice to see a fair amount of time dedicated to the facilities that are coming up. This morning, that have been coming up on ground, and these are exciting opportunities for astronomy in the country. So now I will spend a little time talking about the space element, which is often always complementary. And as time goes, I see the boundary between these dramatically reducing, and the need to really have coordinated observations will certainly be increasing. So let me just begin with a short background on space astronomy. Of course, space astronomy in India began only with, as our space program matured. These began even at the earliest satellites that we launched, Aryabhatta and Bhaskara. There were experiments, TFR, etc., were involved in. But from a serious science perspective, the SROS series of satellites, which were released early on as part of the gamma ray burst, discoveries in the early 70s, and the effort to triangulate the positions, because of those times we did not know where it's coming from. The need to have multiple satellites observe a gamma ray burst was critical, and so we had a series of such experiments. So that was the starting of trying to send up gamma ray satellite experiments on satellites. A very dedicated piggyback experiment, IRSP-3, jointly with TIFR and ISRO centers, was launched on a very short time scale, but was critical in actually showing that we can pursue very good science, X-ray astronomy research in using X-ray detectors. These were primarily proportional counter detectors. And it became the primary success on which the argument for a large astronomy satellite or AstroSat was actually built upon. And while AstroSat and discussions for AstroSat were continuing in the mid-90s, the idea of a slew of or a broad range of X-ray experiments to cover a broad energy range, and complementarity and a new capability in UV astronomy coming on from other colleagues in the country. There was also small experiments going on in parallel. For one of them, which was actually this solar X-ray spectrometer experiment, SOX, which included PRL, TIFR, and ISRO, which was a piggyback on the second of the geostationary satellites we launched. And this is the first time we actually used solid-state X-ray detectors on board, and used primarily to study flares, broadband spectrum of flares. A similar experiment was attempted on the Russian Photon Coronis mission, where they also attempted to include technologies like frontal zone plate imaging. Unfortunately, the mission was a short-lived mission, and so we couldn't really demonstrate in full strength the frontal zone plate imaging capability. 2015, we had, of course, AstroSat. After many years, nearly 20 years from the time they started the discussion to realization and launch, which is the dedicated astronomy project, which you heard yesterday, and is continuing to observe, and we hope will be up there for many years to come. But clearly, this is the first dedicated broadband astronomy multi-wavelength satellite that we currently have. And then since then, we've had smaller missions. I mean, Chandrayaan-1 in 2008-9 timeframe, when there was a small solar X-ray monitor. This was actually developed by Finland as part of an European Space Agency contribution to our first lunar mission. And its objective was to study the solar spectrum continuously, because that was critical to deconvolve the lunar reflectance X-ray fluorescence spectra to study composition of the lunar surface. But this solar monitor actually provided very useful data that was used largely to study first ionization potential effects, and in particular asking, is FIP very dynamically changing during the evolution of a flare? And these small detectors could actually do that. We have a very similar experiment right now, but fully built indigenously at PRL by Santosh Vatavale and his team on Chandrayaan-2. And AstroSat, as I mentioned, continues to be there. You heard yesterday already the fact that we broadened our space experiment reach from X-rays to soft X-rays to ultraviolet detector systems. And so that has been a great success. We have a wider set of institutions participating in this AstroSat. And we've also had these involvement of a very large community of astronomers in the country through the regular calls for proposals. People are involved in reviewing proposals and of course in pursuing research with the data that comes from it. So establishment of science working groups, establishment of time allocation committee for review of proposals, and technical committees to really look at feasibility of achieving these observations, etc., which are all very critical and common to many space missions in the future, have all been largely established with AstroSat operating as a large observatory. We also centralized the data center with ISRO's Indian Space Science Data Center. A lot of growing pains with regard to how we interface with the user community, etc. But these are all getting ironed out substantially with, again, a substantial contribution and collaboration with academic institutions in the country. And on the user side, we can actually see fairly large international involvement with a big chunk from India itself. But this is certainly part of the approach we need to take with regard to future science missions as well, where we certainly believe science is international, and we've been using, as users of other mission data, it is very important that we also release data as early as possible to a wider user community and pursue science sort of more globally. So AstroSat has actually set a fantastic foundation for us to build upon. Now, when you look at the future space astronomy missions, in near term, these are ones that have already been approved, but later this year, we hope to have this X-ray polarimetry mission. Initially, with which only had this POLIX experiment called the polarimetry experiment, which Vishwajit Paul from RRI has been spearheading, and he is going to give you a detailed discussion on it. I also want to indicate that there's a second experiment on board, which is a spectrometer. Since for polarization, this is going to stare at a particular source for very long periods of time, this spectrometer actually also offers fairly good spectra nearly continuously for long periods of time. This is a unique opportunity to get long duration spectra of a limited set of X-ray sources in the sky. And so Vishwajit will discuss quite a bit of it. But this is actually this has emerged from the fact that we are pretty much using the same technology that was used to fly a spectrometer on Chandrayaan-2 called CLASS, but simply split into two parts and put on XPOSAT. So allowed us to very quickly build in a spectroscopic capability onto the same platform. So Vishwajit will talk much more about this, and so I will refrain from saying anything further on that. Just to emphasize, we also have to, the polarimetry has been long ignored area of X-ray astronomy studies. But today, there is also the expectation that there is another mission coming up, IXPE, later this year, which also covers soft X-rays 2 to 8, while POLIX is covering the broader band. We had to make a case for the justification for this mission in the context of delays, etc., over the many years. And so there's a slide was prepared in that context to suggest that there is complementarity with the other global missions that are coming up in the same time frame. Again, Vishwajit will talk more about this. The other immediate mission coming up in space astronomy is Aditya L1, the first observatory dedicated to solar studies. And from the Lagrange point 1, the Sun-Earth Lagrange point 1, This is mission life of 5 years. Hopefully it will go much longer. Disturbance the minimum, and we hope it will survive a very long period of time. And together with the Parker Solar Probe and the Solar Orbiter, we hope this provides an important observatory for solar physics. As usual, arguments about understanding corona. We have a very important coronagraph coming from led by the Indigenous of Astrophysics, a big UV imager coming from IUCAA, and then complementary experiments that looks at the particles and fields, which are primarily in situ measurements. So I think that's listed in the next slide. And so some are remote sensing, some are in situ, and with a broader range of participants. And it is currently, we are looking at trying to merge or connect the various data that would be captured by each of these instruments into an integrated solar science and space weather science that is of importance to both Indian users as well as outside users. We're hoping this would be launched in 2022. Yesterday, last few days, we were having the last of the critical design reviews of in particular, these two major payloads, and a lot of progress is there. Of course, there's a lot more challenges with regard to integration, calibration, elements of it, testing it, alignment issues, cleanliness issues, which are all really, really pushing the state-of-the-art technology at ISRO. We're forced to really do these things as driven by demands from the science experiments. But it is a promising mission coming up, and we hope this will be the start of a series of dedicated heliophysics missions that is of interest to the science community here. Now, going beyond that, we don't have anything that is an approved science space astronomy mission. So in 2018, there was an announcement of opportunity call, and there were many who responded, roughly about 20 proposals from various groups in the country. So a few had international partners in this. Many had excellent science. Some were, of course, technically very challenging, demanded both high cost, long duration development issues, limited capacity building in the country. By that, I mean, when there are proposals where a lot of the technology comes from elsewhere, we also need to balance that with how we build capacity in the country as well. But these were reviewed in July 2018 by a group of by committee, and they shortlisted a few for seed funding this. And this is an area we thought we should do to really make sure that the maturity of proposals in terms of realization, in terms of sensitivities that have been talked about are assessed a bit better, and such that, or in the terminology that is often used, in high technology readiness levels, TRL levels of 4 or something, we all achieve it. So with that in mind, a few have been shortlisted for seed funding, and those activities, those seed funding activities are regularly reviewed by a committee to sort of see if progress is being made. And the belief and the hope is that at some critical stage very soon, when the committee feels as adequate progress has been made, we take it up to the next level for formally seeking creation of a project and seeking government approval for an assessment of actual costs of such a mission, and then asking the government for funding these programs. There were solar proposals also as part of this 20, and what has been suggested to the community of proposers is to really combine them in a consolidated proposal and bring it out as a follow-up mission for Aditya L1. And what is, of course, most satisfying to see is the fact that the user community for space astronomy programs and willingness to really get involved in the design and development of such missions has actually grown quite a bit. And we hope to sustain this enthusiasm and interest in the years to come. Now, of these, so as of now, we don't have any that is sort of completely approved and ready to go. But we have many that are fairly mature. In the area of ultraviolet astronomy, there's a proposal that the committee felt is very promising, that pushes spectroscopy, in other words, complements the UVIT on AstroSat with spectroscopy capabilities, and also attempts to pursue high resolution imaging in ultraviolet. And because Annapurni will be discussing that, so I will not say anything further on that. There was a proposal that has emerged from the colleagues at the Indian Institute of Space Science and Technology, IIST in Trivandrum, to look at the spectroscopy of exoplanet atmospheres. And then there was a proposal from IIT, led by IIT Bombay, on looking at the electromagnetic counterparts of gravitational wave merger events with nearly full sky coverage, and a proposal from Raman Research Institute on looking at the few hundred, 70 to 100 megahertz signature of the EOR, and looking at the early and the cosmic dawn signatures. And of course, in X-ray astronomy, having built up certain strength in the community, as initially at least put together a proposal that is for a very broadband X-ray polarimetry mission. So these are some of the ones that are now under consideration, but not yet in a position that we have actually put it up for approval by the Space Commission. A few quick words on each of these. ExoWorlds, as I mentioned, is an exoplanet proposal that has been suggested by or proposed by, led by the Institute of Space Science and Technology. There's a large collaboration within the country, I understand, that's involved, is interested in the science of these things. It's a very challenging mission. It was initially a 2-meter class aperture, which is pretty, really much bigger than anything we built so far. But right now, based on the largest rocket that we have and a few other considerations, it's now come down to a 1.7-meter aperture with the capability for spectroscopy in infrared, optical, and ultraviolet, and positioned at Lagrange point 2. So that also would involve in trying to ensure that, given the fact that there are infrared instruments on board, that really may do appropriate thermal management of the environment on the spacecraft as well. So this is a proposal. There is a small study team now looking into it and so trying to configure it. Groups at the Space Application Center trying to get the optics into a manner we can actually have it stored into the fairing of a rocket. And we hope in the next few months we'll have some visibility on what is viable given the constraints that we have. But this is an important mission that is being looked at. Varun, I couldn't participate in many of the talks in the last few days because of some other set of parallel meetings. But I presume in Varun's talk on gravitational wave events, he may have discussed the fact that there is an interest in actually looking at the prompt emission during a gravitational merger event. So in that context, he had actually proposed a set of twin satellites that can actually cover nearly the full sky to derive better positions, as well as X-ray spectroscopy over broadband. This had a narrow window of opportunity to really fly it, given the fact that gravitational astronomy is emerging and gravitational wave the merger events were slowly picking up. LIGO operation phases. Now, in the next operation phase, and with Virgo in place as well as Kagra coming in, there is great hope that these error boxes and the number of events is just going to be larger. And in that context, there was a lot of value in actually having this mission that is proposed up there in the sky as early as possible. We have not moved as far as we would have liked to. So we're now continuing to examine how best to tackle this in the context of this opportune window within which we need to work. But it's, though experimentally not very complex, realization of the full sky coverage, etc., demands a lot of activities, and our ability to do that is indeed the question. And clearly last year we lost a lot of time, but we are continuing to review what is best with regard to addressing this EM counterpart of GW events. The experiment that was proposed by RRI, which is to look at the low frequency signature of epoch of reionization, demands a very clean radio environment because of RFI concerns. And of course, as you all know, the cleanest environment that could come could be from the far side of the moon. And so, but that's not easy to get there. And so the question that we have to really address is how to really get this extreme low noise environment of 70 dB or better to look for these signals, and they have done these ground experiments with Saras, and then we had a short window of opportunity to explore possibility of accommodating this on the Chandrayaan-3. As you know, because the lander and rover on Moon, Chandrayaan-2 was not successful, there is a Chandrayaan-3 mission which attempts to complete that total program. And that has, and does not have an orbiter, but it has a propulsion module that actually carries the lander and rover. And once the lander rover system is released, the propulsion module stays in lunar orbit for some period of time. And they had a small payload capacity, and we tried during a year ago, just as the pandemic was starting and the lockdowns are there, to see if we could actually push or compress or somehow accommodate Pratyush into this Chandrayaan-3 program. After many months of effort, both at RRI as well as at ISRO, we sort of had to give up because of the containment of the antenna on that system. And so right now that is not being planned on Chandrayaan-3. And then we now need to really seek new flight opportunities, because lunar missions are not cheap. They don't come easily. And so that's the timing of this is not very obvious at this stage, but clearly a lot of good progress has been made by our team with regard to development and design and significant demonstration on the ground. So that's something sort of waiting in the pipeline, waiting for an opportunity to actually fly. On the X-ray side, clearly there's a lot of, it is natural to see that the community that has grown quite a bit with AstroSat would desire a follow-up mission. This requires, of course, we had optics built up with the soft telescope that KP Singh had led, which was a fantastic development. But we need to extend that into hard X-rays, and that's is an area that we need to get going. We've had lots of discussions amongst colleagues at ISRO, at PRL, and at RRI. We had meetings at IUCAA many years ago, and in between multiple discussions. But even today, we haven't really gelled on a program to actually build that would give us clear visibility on the development of the hard X-ray optics. The detector systems, of course, also have to be now different, and there is interest in actually going for large area solid-state devices, and this will also demand improved performance and resolution, noise, background, etc. But the most important thing that is being looked at by the community appears to be to address the polarimetric capability, which is we're building up with Polix and XPOSat, which is a start, but to really extend that into soft X-rays and hard X-rays demands design considerations, and I think we're sort of waiting for the community to come back with a viable mission that can be achieved in about a 7-year time frame. There are other areas in space astronomy under consideration. These are not really formal missions, but there's some interest in sub-millimeter terahertz astronomy capability we built in the country. Clearly, from astronomy perspective, with ALMA, a lot of interesting results are emerging. But clearly, cold gas and astrochemistry are important topics of interest to astronomers, both here as elsewhere. Molecular hydrogen mapping with CO continues to be important. But how do we get there? And that one of the activities we are looking at is, so that we created there is a small group in Space Application Center, Ahmedabad, that is actually involved in the development of detector systems and antennas for sub-millimeter, at this in the early phase going up to about 350 gigahertz. In that context, we have, I think January 2020, I can't remember now. We had a meeting at RRI that actually created a consortium called the Indian Sub-Millimeter Astronomy Consortium. And what is being looked at is to really interface this user community with the technical group at SAC towards setting up a facility in the Ladakh region of the country where the water vapor content is very little and hence allows useful terahertz observations. I think there's some discussions going on with the University of Astrophysics on the possibility of setting up a 6-meter telescope there. We're looking at a second phase development of SIS junction detectors for really pushing it to 500 gigahertz. This is maybe most likely in collaboration with the Center for Astrophysics in Harvard, Smithsonian Center for Astrophysics in the US. And clearly there are interests in actually looking at the EHT network and to be part of that. And in the long run, the idea of a terahertz mission, space mission is what is being conceived. So putting a dot here would really make this network look very different. And I think there are discussions in the astronomy community in India for even a bigger telescope in the Ladakh region. But these are all exciting opportunities, and so the emergence of terahertz is a very important possibility of terahertz astronomy in the next decade is an interesting development. Another area of astronomy, as I said, is only currently just simple thoughts at present, but nevertheless, these are long-term missions. So this idea of actually a space-based gravitational astronomy program. We all know LISA exists, and there are limitations from the ground-based interferometers that Somak spoke about this morning, and the idea of going into space to avoid some of the seismic noise and address different science. Clearly, these are technically very challenging, going to be absurdly expensive, and will have to be collaborative international efforts. And so currently, there's a small group trying to drive and plan of action towards considering such a future mission, 10, 15 years from now. But it's something we need to start now if we need to do it. So the themes for the next 10 years largely addresses many areas, including planets, habitability, solar physics, stellar physics, AGN studies, transient astronomy, and sky surveys, and of course also the early universe, provided we get a window for Patush. And space GW is maybe way beyond that. In terms of opportunities from space to do astronomy, from India, we need to really explore astronomy to some small satellite platforms. The kind of large missions that we used to must always be there, but they're time-consuming. They take a long turn. They have a long turnaround time to go from concept to approval to realization, and it's very important that a lot of young people participate in this, for which a shorter turnaround time is required. One way would be to really consider small satellite platforms. We're now drafting an announcement opportunity for a small satellite, call for a small satellite platform, experiments on a small satellite platform where we can do fairly decent science. I mean, CubeSats, many CubeSats have shown fantastic capability. And that is something we want to exploit. Collaborative programs, external agencies, we've had, on AstroSat, we collaborated with other countries. It's very useful. And that's something we need to continue to do to really both bring costs down, shorter development time, and overall yield more with limited investment. And the piggyback experiments that we used to do earlier continues to be an opportunity that we must utilize, and so that you don't have to have a custom-made satellite for astronomy, but use the existing missions for both low Earth and geostationary platforms may be useful. These are things that we probably need to also explore. This is a picture that we have always put together, but it really shows the fact that both from ground and space, we have a fair number of exciting things coming up. And that's critical in the context of all the mega projects that we discussed this morning. And it's a nice window for youngsters to really get going. And finally, I just want to really give you a feel for the space missions, just taking the exoplanet research area globally. When you look at TESS, which has been launched in 2018, is now doing a sky survey of exoplanets. It's doing what Kepler did in a small part of the sky is now doing nearly full sky. It's a very beautifully designed experiment, and it's going to reveal many things. And this morning, Abhijit mentioned how some of the targets for the 2.5 meter PRL telescope would be test targets, test discovered exoplanets. GEOPS is a small mission that is the European Space Agency have put in, looking at for exoplanets around bright nearby stars. JWST, after much delay, is expected launch later this year. Large optics, large capability. It's going to be there for many years. Absurdly expensive, $10 billion or more. And just look at the time scale it takes. 1996, when it used to be called the New Generation Space Telescope, in GST to JWST now. but these are long-term programs. Plato, again, a European Space Agency mission planned for 2026, began discussions in 2011. ExoWorlds, they started discussions in 2018. We hope we'll be able to achieve it in the 2026-27 timeframe. One has to see how the project can be managed. And there is a European mission, Ariel, planned for 29. It's only a 1 meter class mission. But I forgot to put down here when these discussions started. But typically a 10-year time scale is indeed there. So, and if you look at the collaborations involved, it's a substantial number of people involved in these collaborations. So this suggests the need for a very large involvement in the community for us to really successfully and quickly achieve many of the objects that we've actually put out. So finally, let me close with a few points to note that, as I already mentioned it, exploring the CubeSat option is something we need to do. Short turnaround time to allow masters and PhD students to pursue research problems. I think, as I have repeatedly emphasized in many of our earlier meetings also, the number of students, PhD students in particular, involved, then their involvement in such projects is really, really way below par, because, and we are not able to exploit the fact that there is a lot of bright talent out there, and who could help us actually build, calibrate, and do science at a very accelerated pace. And we all collectively need to find ways to really enhance this number of PhD students in all future programs that are coming up. And I think with that, I'll stop, answer any questions you might have. Thank you.
Thank you, Sri Kumar. That was a wonderful summary of the space plans, and then what we have done earlier as well. So are there any comments or suggestions from, just looking at anybody raise their hands? I can see. No.
Can I ask a question?
Yes, Annapurna, please.
Yeah. Yes, regarding the very interesting thing of new AO for small missions you mentioned, right? So any details on it, like how small?
There is a bit of noise from
I think I got what Annapurna was asking. Details on what how small is small for small missions, correct?
Yeah.
Like,
and also, like it might require, the mission may be small, but it might require some more data to be collected or something like that. I mean, it also has requirements regarding power or data collected and time scale to which it can be supported.
Able to very clearly.
A lot of noise, Annapurna.
But I think I sort of heard that. But Annapurna, maybe I would say we are hoping to have at least a draft outline that we can send it to some of you in about 45 days. We've been working on it for a little bit. We're trying to look at we have a platform called the INS bus system, which is very small, gives you only 5 kg capacity, which may be very, very challenging. But we're also looking at the IMS bus series, but that is, or something in between. So we haven't completed our discussion with all the related people to sort of see what is the window that we should really pursue. Clearly, a CubeSat type model is what we thought would be useful, but all of it will only emerge in about a month and a half to 2 months. So maybe I can give you better answers after that.
Thank you.
I don't see many here. Yeah, we have time for any further comments. One thing, Sri Kumar, you alluded into this students' participation. You were right, because we have a large number of student pool across the institutes. You were right, because many of these the students look at completing PhD, but then it doesn't necessarily be a part of the PhD, but then it should be a kind of, for them of the getting involved and then getting certain experience. Maybe that kind of thing should be even make it mandatory at the institutional level, spend some year or something or part-time, while doing their own PhDs. see, this is not imposed right now. I don't know if any institute is doing that, but then certainly in IAO, we are not doing it.
Correct. Certainly, I think it's extremely valuable experience, even if it's not part of the PhD. And that value, whether you're a theorist, whether you're an observer, whether you're an experimentalist, this is incredibly valuable. And I think that is the model that we want to work towards. We've had, there was a human resource enhancement, or I forgot what exactly was the term of the committee, but we had a committee that had many colleagues from the academic side as well, people at universities, to sort of see how we will go about organizing such a thing. We've made a report under which what ISRO can do or should do with regard to generating such or stimulating such activities, some of which has certain suggestions, but we now have to see how much of that we can practically get it done given various levels of constraints. But at every institution level, I think this needs to be addressed. The second point is to also, as a community, we need to really appreciate the fact that when people are involved in such things, the publications may not come as fast. As students, I think the pressure on them to really have to publish so many and so quickly, etc., may have to be relaxed a little bit so that there is time for them to really explore such avenues, which are not necessarily going to lead to specific activities under their project. So it's a combination of these things that has to be addressed, I would say. But I am absolutely convinced that there are a tremendous number of young students who would be very eager to be part of many of these issues. And to do that, we will have to actually break the problem down into modules that are doable given an individual student's availability of time. And so that's an exercise we may not have done as much as we could have, but in future programs, I think we should really do that.
Yeah, there should be some way of making that as a mandatory for some of the students at least, because a lot of people won't take it up, but then they can do their own problems, but still they have to participate the developmental activities. I think that's a very key. So without that, I think developing astronomy or any science becomes extremely difficult. Otherwise, it becomes a paper-oriented research.
Well, this morning's talk where, when Ram was presenting, we saw so many students who are now part of that program.
Yeah.
That's a very nice model, and we really need to expand that model.
Thank you.
Thank you.
If there are no more questions, and then we thank Professor Srikumar for that wonderful summary.
Thank you.
So,
share.
And is Biswajit around? Biswajit?
It should be.
Yes, can you hear me?
Yes, I can hear you. So somebody can unshare Srikumar.
I did, right?
Oh, Sissy?
No, I already unshared.
Biswajit, can you put up your slides? Okay, that's great.
Yes.
Yeah. So the next talk is by Biswajit Paul from Raman Research Institute. Is going to talk about X-ray polarimeter satellite. So, Biswajit, please go ahead.
Yeah. Hello. Good afternoon, everybody. Thanks to the SOC and Shashi in particular for inviting me to talk about this upcoming emission ExpoSat. So I will be talking mostly about the X-ray polarimeter instrument on board ExpoSat, and would also briefly mention one other instrument which will simultaneously be making spectroscopic and timing measurements of the same set of sources, thereby enhancing the scientific output of the whole instrument, the whole satellite. So I would briefly give an introduction to the various methods for X-ray polarization measurement and what and how it has been adopted in this instrument colleagues, and then give a broad idea about the status of the instrument. Currently, we are looking forward to possibly launch later this year, and then also give a little bit of the context of this instrument over. Along with other instruments which are going to be launched in the near future for X-ray polarization measurement. So the satellite is called ExpoSat, X-ray polarimetry satellite. The X-ray polarization measurement instrument is this blue color box shown at the center. It's made of X-ray proportional counter detectors with a collimator in front. and the satellite is dedicated for extrapolation measurement. And there is another instrument called XPEC, which is side by side, but pointed in the same direction as POLIX to make, along with polarization measurement, timing and spectroscopy in a somewhat lower energy band compared to POLIX. This is a unique satellite which is dedicated for this polarization measurement. The polarization measurement requires a spinning platform. So this satellite, while looking at the sources, would be spinning at a modest rate of about one rotation every 5 minutes. And the spinning platform is rather complicated, so that has puts in a lot of limitations in terms of availability of power generation. So therefore, POLIX would effectively be looking at cosmic sources mostly when it is in Earth's shadow, and rest of the orbit, the satellite will be powered, will be used for recharging the battery. We will probably get a slightly lower exposure duration per day for cosmic sources compared to what is possible with AstroSat. And POLIX being a modest sensitivity instrument, it would require very, very long exposure, even for the brightest of X-ray sources, about a week to few weeks. So POLIX would be targeting a few dozen of the brightest X-ray sources in the sky. Primarily, the plan would be to look at the persistent sources, but occasionally, whenever interesting transient source becomes bright in the sky, you would be looking at the transient sources as well. Now, why X-ray polarization? First of all, polarization is relatively unexplored in high-energy astrophysics. There hasn't been any dedicated polarization mission all these years. AstroSat, along with some other instruments, produced some result of polarization from the brightest of sources as a byproduct. Most of these instruments were not designed to be polarimeter, and there are experiments going on for decades, very serious effort to measure X-ray polarization in very high energy band using balloon platform, and they have had some success because balloon platforms again are work at extremely high energy band, and there are very few sources which are so bright at that energy band.
Vishwajit, could you come closer to the mic?
Can you hear me now? Hello?
Yeah, he's good.
Okay.
Hello, it was very little.
So,
your volume was less. So
okay.
Can you come closer to the mic?
Okay. Is it okay now?
Yeah, it's better. It is better.
Okay, so you would expect X-ray radiation to be polarized whenever the emission or transmission of X-ray involves magnetic field. If the emission is from a magnetized region, or if the transmission of X-rays is through a strongly magnetized plasma, that would introduce polarization. If you have emission or scattering from any non-spherical plasma, for example, an accretion disk, if you see AGN, that is expected to be polarized. And cyclotron radiation or synchrotron radiation would also be polarized. Non-thermal Bremsstrahlung, if that is happening in with the net, non-thermal X-rays, if they are interacting with magnetic field, would also produce polarization. Now, there are very few X-ray sources actually where you do not expect any polarization. For most X-ray sources, you would expect polarization of varying degree: accretion powered pulsars, rotation powered pulsars, magnetars, pulsar wind nebula, non-thermal supernova remnants, black holes and microquasars. If there is jet emission or if there is radiation is scattered from accretion disk, even in AGNs, you would expect polarization. In low mass X-ray binaries, which are very much like the black hole accretion powered pulsars, even the neutron star low mass systems may give polarization. Solar X-rays are to be polarized, gamma ray bursts are to be polarized. In spite of all that, Crab nebula is the only source for which high signal to noise ratio X-ray polarization exists at different energy bands, and Cygnus X1 is one other source in which some measurements exist. And these measurements were done mostly long time ago, more than 40 years ago, and very recently with, for example, AstroSat and Integral and some other experiments, but only for the brightest of X-ray sources. So X-ray polarization is therefore a very potential area, rich area, but quite unexplored. So the various techniques for which by which X-ray polarization can be done is, one is Bragg reflection. If you reflect the incident X-ray photons from a crystal at 45 degrees, then only photons which are polarized, okay, perpendicular to that plane, would be perpendicular to the line of reflection, would be reflected. And if you then rotate this whole system around the beam axis, you would have very clear measurement of polarization. But a given set of crystal would be effective only in a narrow energy band. So therefore, even though this measurement is, this kind of measurement would be very definite, very clear, its sensitivity would be rather low. And this is what was adopted in OSO 8, with which the crab polarization was measured. Other method is Compton scattering. Compton scattering works at very high energy band, let's say about 30 keV or so. And the way it is implemented in AstroSat with the cadmium zinc telluride detectors, it is effective at energies about 150 keV or so. And therefore, you have very limited number of sources. The two areas where polarization measurement would work in such a way that you can measure polarization for a large number of sources are implemented in these two instruments. One is the photoelectron polarimeter, the IXPE mission, which is about to be launched, I think later this year. It's a NASA mission. There you have photoelectron polarimeter. So how it is done is an incident photon is absorbed in a gas and by photoelectric process, and the photoelectron tends to go along the direction of the electric field vector, and it will produce a small ionization track. If you can image that track, you can measure polarization. What we adopted, so the first technique, photoelectron polarimeter, works in energy band of less than about 8 keV. And what we are adopting is Thomson scattering. Here the incident X-rays are scattered from a low atomic mass scatterer, beryllium in our case. And because it is Thomson scattering, the photon would tend to be scattered preferably in a direction perpendicular to the electric field vector. So if there is a net polarization, if you spin this instrument, any of the detected element then effectively works as a polarimeter. Okay, it is sampling the scattered X-rays in the azimuthal direction. So on the XPOSat satellite, along with this POLIX instrument, there is also one other instrument called X-ray spectroscopy and timing. This payload is being developed in the SAG group in URSC. This is based on these swept charge devices, works in the energy band of about 8 to 15 keV and has a moderate surface area of 64 square centimeter. But the instrument has good spectral resolution. Plus, because this works in low energy band, it will detect much larger number of photons compared to POLIX. So this would be useful for simultaneous timing and low energy spectroscopic studies of the same set of sources that would be observed with POLIX, and that has a very interesting science outcome. So it's very rare in X-ray astronomy to be looking at the same source for several weeks at a time. So sources which show small time scale variation and many interesting properties of the sources changes with time, expect would provide a new perspective for this set of sources, mostly low mass X-ray binaries and high mass X-ray binary. The expect instrument, these are the parameters. It works in the energy range of 0.8 to 15 keV, has an energy resolution of about 200 AV, like almost in the ballpark of CCTs. Its effective area is more than 30 square centimeter at 6 keV, which is almost as good as many X-ray telescopes. It has two halves with a field of view of 3 degree by 3 degree and 2 degree by 2 degree. With this implementation of the collimator, hopefully there will be a very good estimate of the sky background and instrument background as well simultaneously, and that should give good handle on background subtraction. Operation wise, this should be looking at the same sources as POLIX, and yeah, more or less that's all. These are the hardware for this instrument. It's almost ready. Now coming to POLIX, as I said, the X-ray polarization measurement techniques below about 3 keV, like 2.6 keV, you can use graphite crystal in Bragg reflection pattern. In photoelectron track polarimeters, that's where the NASA mission uses. You can cover an energy band of about 2 to 8 keV. Thomson scattering polarimeter, which is ours, you can effectively work between about 5 to 30 keV. But because you are using beryllium as a scatterer, we couldn't use lithium. Our since effective area range is 8 to 30 keV. Above 30 keV, you can use Compton scattering. And Compton scattering, if that can be combined with hard X-ray focusing optics, okay, or at least hard X-ray concentrator, That would give very good sensitivity in the Compton band of above 20 to above 30 keV, and that's our future goal. What Shikumar alluded to earlier in his talk. In energy band higher than few hundred keV, that is MEV, GeV, band, polarimetry, possible polarimetry is being explored in multiple labs. Similar to all other X-ray instruments, in polarimetry instruments also, we need to keep in mind that instruments are quite different depending on what we want to look at. If you want to target point sources, pointed observation of known X-ray sources, then the instrument design is something. If you are looking at transient events like GRBs, then the polarimetry instrument has to be wide field. So given that, even though both instruments would measure X-ray polarization, the instrument for point sources and instrument for GRBs ought to be quite different in design. So in our instrument, we use Thomson scattering, the principle of Thomson scattering. Basically, the incident X-rays, if they have a net electric field vector, then the scattered photons would tend to go mostly in the perpendicular direction. So if you have a detector, and if you rotate this whole system around the direction of the incident X-rays, you expect to measure some azimuthal distribution of photons, azimuthal pattern, and from that you would be able to measure the degree and the angle of polarization. The instrument that we have adopted put some special requirement on the satellite. The satellite needs to have an absolute pointing accuracy of better than 0.1 degree. It needs to be spinning around its viewing axis at a rate of about 0.2 rpm. We would require very long observations of sources going from 1 to 4 weeks. And of course, like any other space-bound instrument, you want to have a maximum possible duty cycle. So this is how the instrument Polix was adopted on the top deck of the satellite. We have a collimator on top. Just right below the collimator, there is a scatterer. And surrounding the scatterer are 4 proportional counter detectors. Behind each of these detector boxes, there is detector drive electronics. And on the sides of it, we have the signal processing electronics. Polix, we need to keep in mind that since we are using beryllium scatterer, any scattering polarimeter has low scattering efficiency, mainly because scattering is from the electrons, and this competes with the photoelectric absorption process, and absorption process wins over at lower energy. And the scattered photons tend to go in all directions. To catch them, you want to put detectors surrounding the scatterer, and that also requires then large detector system, and therefore introduces a large background counted. So even though it's a dedicated instrument, its sensitivity is determined by these two factors: low scattering efficiency and large background. So you would be sensitive to about few dozen of the brightest X-ray sources. The Polix system is somewhat like this. We have 4 independent detectors. Each detector is operated by its own front-end electronics, which has the high voltage control, and amplifiers, etc. Then data from each of these front-end electronics goes to the respective processing electronics. Up to this, each one of these lines are independent. And after this, the data from the 4 processing electronics is collected to a common electronics. And there is a common telemetry telecommand which interfaces with the processing electronics for setting various thresholds and so on. And also the front-end electronics for controlling the high voltage that is applied onto the detector. Plus, each of these units have separate housekeeping, and the housekeeping data is passed on to the telemetry unit. Now, telemetry and the common electronics, these are the common points for all the 4 payloads, and therefore we have kept a redundancy for the common electronics and redundancy for the telemetry telecommand unit as well. So there is a twofold redundancy as far as communication for telemetry and data is concerned, and each of the detectors are independent. And any one of these, if a source is bright enough, is an independent polarimeter. Overall specifications of Polix is this: the photon collection area, the sum of the areas of the holes into the collimator through which photons should fall is 640 square centimeter. The field of view is about 3 degree by 3 degree. Energy range is 8 to 30 kV. The lower energy is decided by the scatterer, low energy threshold. The detectors are proportional counter. The scatterer element is beryllium. This is the overall dimension of the central instrument, 650 by 650 by 600 millimeter. Overall mass of the payload, including electronics, is about 125 kg. Power, this has actually come down after we have realized the qualification model. It has modest data rate, and the instrument by its design has a modulation factor of about 40 to 44%. If you remove one of the detectors, this is how it would look like. There is a collimator, below that is scatterer, and on all four sides you have the four detectors. The detectors themselves have a window through which X-rays will go in, but that will keep the gas inside, a Mylar window, and inside you have the standard proportional counter wires. The high voltage is applied onto those wires, and the detector volume is filled with xenon gas. These are details of how each of the detectors are. These are photographs of the wire frame. This is how the principle of charge division works. If you have a photon falling in an area, the signal is carried onto two sides of this network of resistive wires, and the division of the pulse amplitudes at the two ends is used to find out the location of the photon interaction. And what you need for polarization measurement is the identification of the anode cell in which the photon has interacted. The collimator of Polix has somewhat unique design because we will be measuring polarization by looking at modulation in the count rate in azimuthal direction. Any small pointing offset of a satellite would itself introduce some modulation in count rate. So to mitigate that effect, what we have done is we have made this collimator where the holes are hexagonal and the hole size on the front side is slightly larger than the hole size at the back side. So as a result of this, we are compromising the effective area of the collimator a little bit, about 10%, but at the same time we are achieving a flat topped response, which means the instrument is insensitive to small pointing jitter of up to plus minus 0.2 degree, and this decides the pointing requirement of about plus minus 0.1 degree for the whole satellite. We had demonstrated polarization measurement by this technique with a smaller laboratory unit earlier, where X-rays were shined onto a beryllium disk, and the scattered photons were detected with two proportional counters on two sides. And if you rotate this whole system, you get if the X-rays are from a radioactive source, which is monochromatic and unpolarized, you get a flat distribution. But if X-rays are from a polarized source, then you get this beautiful modulation. The amplitude of this modulation is a measure of the degree of polarization, and the phase of this modulation is a measure of the angle of polarization. The signal is very clean. If you take a Fourier transform it, what you find is narrow peaks and their multiples, no other artificial signal anywhere. So Polix detector system, these are photographs of Polix, the qualification model of Polix, which has gone through vibration successfully a couple of months ago. And on the right hand side is the same thing shown without the shield and the collimator to show you the scatterer. The scatterer is made of pure beryllium made at BRC. Each of the detectors on the backside, there is this front-end electronics, and the data that comes out from each of the detectors through the front-end electronics is then taken to the main electronics units, which has multiple subsystems. So these are photographs of the PCBs of the qualification model, and this is a photograph of two qualification model detectors along with the two processing electronics units in final configuration. During electronics test of the qualification model. So we were just discussing about going and taking this unit for, these have been vibrated. Now next step is thermobag test. So with this, we expect to achieve about 5% minimum detectable polarization for sources which are about 100 milliCrab or so. And among the class of sources that I mentioned, in many of them, you would actually expect to have quite large degree of polarization. For example, in accretion powered pulsars, you may as well have one upward of 40% polarization. So you should be able to measure not only measure polarization, you will also be able to measure the polarization as a function of pulse phases and so on. However, in spite of the instrument being so large, I need to tell you that Polix effective area for photons is actually quite small, because when you have Thomson scattering of photons along with photoelectric absorption, a good fraction of the photons are either forward scattered, side scattered, and then multiply scattered, or get absorbed by photoelectric absorption. And then a small fraction will arrive at the detectors. And if it goes through the window and the window support structure, then only it's detected. So detailed simulations of this have been done, and we have arrived at what is our eventual effective area, which is about 10 square centimeter in the energy band of up to 35 keV, and increases slightly higher. But at higher energy band, you will have larger background also. So Polix nominal effective instrument sensitivity is up to 30 keV, but for a few of the brightest sources, we will get slightly larger will be able to go to slightly higher energy. Some of the simulation results, I think I will skip this for sake of time. I would end with a couple of slides on some of the key signs that we intend to pursue. Even though I understand, this conference is for the jet sources, which would mean microquasars and blazars. Now, blazars, we wouldn't have much sensitivity because, as I said, POLIX is primarily for the brightest of X-ray sources like 50 milligrams and above. However, during the lifetime of POLIX, if we are fortunate to catch a blazar at during a very high state, we would make sure to look at it if feasible as long as possible, because those will be unique. Otherwise, POLIX's key science is around accretion powered pulsars and black hole sources. So in accretion powered pulsars, for example, where the X-rays are radiated from a neutron star, but the accretion is happening onto the magnetic poles, we clearly do not know, for example, whether the beaming is in the forward direction like a pencil beam, or the beaming is on the equatorial side like a fan beam. This could be established very well by measuring pulse phase dependence of the polarization. If it's a pencil beam emission, then at the peak of the pulse, we are looking close to the magnetic pole along the magnetic axis, and you would expect very low degree of polarization. On the other hand, if the emission is in the form of a fan beam, then at the peak of the pulse, we would be looking more towards the equator, which means perpendicular to the magnetic field line, and you would expect very large degree of polarization. So, pulse phase measurement of polarization would be the first thing to look at to establish the beaming patterns in accretion powered pulsars, and different pulsars at different luminosity ranges. Do we see them to be, some fan beam time, some pencil beam time, whether there is a luminosity as a demarcator in that. And there are some sources which themselves go through large variation in X-ray flux. So do you see changes from pencil beam to fan beam, etc.? Would be subsequent studies to do. So some of the key goals with POLIX are detection of X-ray polarization in accretion powered pulsars, which is the key signature of strong magnetic field in accretion powered pulsars. Next is pulse phase dependence of X-ray polarization in accretion powered pulsars, which would help determine the beaming pattern, whether it is accretion, pencil beam type or fan beam type. Energy dependence of X-ray polarization in accretion powered pulsars, because one expects enhanced polarization near the cyclotron line area. Luminosity dependence of X-ray polarization in accretion powered pulsars, because you would expect changes in the accretion column structure, and polarization would clearly then show you going from a fan beam to pencil beam or vice versa. And then luminosity dependence of the pulse phase dependence of X-ray polarization, and so on. In black hole X-ray binaries, you would expect polarization, in different ways, depending on whether it's a soft state emission, where most of the emission is coming from an accretion disk. And if you happen to see a source, close to the edge of the accretion disk, that is the large orientation angle between the spin axis and our line of sight, then you may see large degree of polarization. However, no matter which way are you looking at a black hole source, the X-ray polarization, its angle and its degree is expected to have significant variation over the X-ray band, going from like 1 keV to 20-30 keV. One expects to see very large variation in X-ray degree of polarization. Okay, so the soft X-ray polarimeter that is being launched by NASA and the POLIX polarimeter, which are somewhat complementary, would help us cover this energy band well. So black hole sources, either it is disk emission, or if it is reflected emission from the accretion disk in hard state. In hard state, you have most of the emission coming from a corona. So part of that emission also comes after the deflection from the accretion disk, and the reflected component ought to be polarized. In which case, you would expect to see large degree of polarization in the reflected component of the spectrum. So this is where simultaneous spectroscopic measurement would be useful with the expect instrument. So I would end with this slide where I show POLIX, which works in the energy band of 8 to 30 keV in the same time frame as this NASA mission IXP would be launched, which would work with a different technique, working in a slightly different energy band, lower energy band, 2 to 8 keV. So these two instruments are contemporary and complementary. And in some fortunate cases, you would also have polarization measurement covered in much higher energy band with from some balloon-bound platform. So we probably have a good days in polarimetry ahead, with more than one dedicated instrument being launched in the same time frame. Thank you. I would end there.
Thank you, Vishwajit. Thank you very much. It's well within time. And then we have time for any queries, comments. Trying to see. There are no hands raised. So Vishwajit, this IXP is it is in the space now, no?
No. IXP is yet to be launched. This was initial plan was to launch, I think 2017 or so. Then there were delays and so on. So after coronavirus, there was further delay. And as last I heard, I think it's to be launched in October.
Okay, so that nicely covers the entire.
So this is made of focusing X-ray optics in the low energy band, like less than 10 kV, and then this photoelectron polarimeter at the focal plane.
Yeah, that's good.
So Vishwajit, what is the energy resolution you have?
This instrument is not designed for in a good energy resolution. It's not a spectroscopic device, but the typically we have about 20-22% kind of energy resolution. So the 8 to 30 kV band for those sources where you have good sensitivity, like if you have more than 5 sigma measurements, we'll be able to break it down into multiple energies. So 4 to 6 energy bands easily.
Okay, and how do you do that?
No, for each photon, the pulse amplitude is also measured.
Okay,
First of all, we find the position by taking ratio of the pulse amplitude at the two ends. That's the first goal, and that summed amplitude is also a measure of the energy of the incident photon, accurate to about 20% level. So,
okay, that calibration you do it on the ground before.
Since you are covering an energy range of like factor of 4, 20% resolution is good enough for us to divide it into several energy bands, provided there is good signal to noise ratio over the entire band.
Okay, did you know this a priori from ground?
Yes.
Yeah, okay.
The instrument is calibrated on ground. However, we do not have onboard source calibration like what is there on AstroSat. But when you use xenon gas, like the way we use here, similar to LAXPC onboard AstroSat, what happens is xenon gas, sometimes multiple events are produced. One of them is a K fluorescence event. So if you only pick up the double events and produce a spectrum of either of those two events, that would give us a measurement of the 30 kV. That is one thing. And second thing is the low energy threshold is decided by the beryllium scatterer. Okay, so that also gives us a measurement of the low energy in flight.
Yeah, okay, thanks.
There's one more question, I think, from Pankaj. Pankaj, can you?
Yeah, can you hear me?
Yeah, we can hear you.
Yes.
Yeah, okay. So, Biswajit, I have a very nice question. So, does this capability of detecting the X-ray polarization depends on the spectral state of the source as well? I mean, like the
instrument's capability does not depend on the source. Instrument's capability depends on
number counts.
Two factors: brightness of the source and what is the degree of polarization you have.
Okay.
So the polarimeter is usually characterized by what is called minimum detectable polarization, and the numbers that go into minimum detectable polarization is duration of the observation, the modulation factor of your instrument for 100% polarized source, the background rate in the instrument, and then of course luminosity of the source. The brighter the source, the smaller will be the minimum detectable polarization. Now, accretion for pulsars, even though have large luminosity fluctuation, probably the polarization, degree of polarization would remain more or less same. Whereas, or we know very little about that. Whereas for black hole sources or low mass X-ray binaries, where in different states you have very different emission mechanism itself. Like low mass state, high state, probably most of the emission is from accretion disk. Then the degree of polarization would depend on whether you are looking at the disk edge on or face on. So our detectability will depend on brightness of the source and what is the degree of polarization from the source. And since in low mass X-ray binaries the degree of polarization depends on the state. So your question, one answer is yes.
Okay. I got it. Basically, so as long as you have counts, we are okay probably in the concerned energy band.
As long as we have counts, we have a minimum detectable polarization. If the source polarization is above that level, we would.
Okay. Yeah. Thanks.
Okay. Thank you. If there are no questions, and let us thank Biswajit. Thank you, Biswajit.
Thank you. Thank you, sir.
Yeah, we move on to the next one. Annapurni, you have your presentation ready?
I have. Can I share?
Yes, please. Yeah, we can see that. So the next talk is by Professor Annapurni Subramanian. This is on INSIST, that is Indian Space Telescope for UV astronomy.
Just give me a second. I have a call from PSA's office. Just give me a second.
Okay.
Yeah, I'll just go ahead with the talk, but I may have an urgent call coming, which is unexpected, but in which case I'll have to stop this, rather take a break. It has to call from ministry.
Okay.
So
I think it should be okay.
Sorry, I don't know, something urgent. So now is a call from Vijay Raghavan. He himself called.
Okay.
So I'm expecting a call from minister. So I'll just go ahead till the call comes. I don't know when they will actually call.
Sure,
So
please
yeah.
go.
Okay. So this is regarding the Indian Spectroscopic and Imaging Space Telescope. This is a proposed mission as mentioned by Dr. Sri Kumar in the previous talk on future astronomy missions. And this is a collaborative proposal led by IAA, and the collaborating partners are within the country as well as CSA, CASTA team. So we have TIFR, PRL, IUCA, CHRIST, ARIES, and several centers of ISRO. And this is named as Indian Spectroscopic and Imaging Space Telescope, the short form being INSIST. So giving you a brief outline of how it all originated, the start of the proposal can be traced to the first science meeting of UVIT, which was held in 6 to 7 July 2017. So that was it was launched in the UVIT, sorry, AstroSat was launched in September 2015, and UVIT doors were opened by end of November 2015, and it took some time to complete the PV phase was completed by March of 2016, and then the AO proposals were carried out later, and it took a while to get all the data out and start processing and get the science out of it. First the calibration got completed, and then the science coming out of it. So in the science meeting, there were several good images and initial results getting started presenting, and obviously it was obvious to everyone that the UVIT, which is a kind of a moderately sized telescope, is capable of producing excellent science in the UV, and much better than GALAX, in fact. So obviously towards the end of the meeting, the question that will be coming will be, what is next? Now we have set up our stamp in this area, and to basically take advantage of the lessons learned and the experience gained. What is the next thing? So within IAA, there was a team which was working on cases for what we can do next. So obviously it will be like there are two science cases I present here, which is like Able 2256 is a galaxy cluster, where in the UV you can actually clearly see the kind of demographics of patterns in star formation, because UV it picks up the regions where the recent star formation has happened, and then the morphology changes, and it is very nicely picked up as the variety you can see very easily. If we can resolve this better and also do spectroscopy, it will be great to understand the dynamical as well as the chemical evolution of these systems. So this is for the
the distant universe. But if you look at the stellar systems as well, this is the optical image of a nearby globular cluster within our own galaxy. This is NGC 1851. This was studied as part of the performance verification phase. And this is the far UV image of this cluster. And you can see that the central regions, the crowding is very much lifted in the UV, but basically because sun-like stars which do not emit in the far UV much become undetectable, so that only the hot stars you get to detect. And for the first time, you don't need to worry about crowding in the UV. And this is only with the 1.5 arcsecond resolution, which is available from UVIT. So much better resolution can clearly resolve the very, very central cause of this these clusters. And you can see in comparison the galaxy far UV image of the same cluster, you can see very well that the UVIT is performing much better than the galaxy and able to resolve the central region very well. And the kind of stars you see in the internal regions of these clusters are of the horizontal branch type, as well as the products of stellar crashes, basically the blue straggler stars, the production of which is basically due to collision of stars in the central regions, crowded regions of the cluster. And in the case of horizontal branch stars, we can see that we are able to identify their properties just by utilizing the filters in the UV, because it is actually sampling a different part of the spectrum. This is the blue horizontal branch, this is the red horizontal branch. The colors, we are able to separate them, but we also know that within the horizontal branch, there is a chemical anomaly, including the population differences, as well as chemistry differences, as well as helium abundance differences. In order to understand that, it will be ideal to get spectrum of these stars. So ideally, one would be able to resolve these stars into individual objects, and not only that, take spectra of them, so that we can actually understand what is actually the evolutionary status of these stars. Not only that, how the atmospheric parameters change as a function of blue to H, and why clusters are producing different types of horizontal branch morphology. So that is of paramount interest. Still, people do not have enough instrument or enough data to understand this particular evolutionary status. And with respect to blue straggler stars, we still do not understand the formation mechanism. And these are the BASS spectra from IUE of the nearby open cluster M67. So you can see that there are different lines present. Number one, the chemistry of the atmosphere of these blue straggler stars also could reveal the formation mechanisms, which could be collisions, which could be accretion from a binary, or a merger of spiraling in merger of two stars. So they are expected to have some differences, but so far we haven't been able to trace these differences. And we think that in the UV, it will be much easier to identify the formation mechanisms. And moving on, this is another, this image was also shown by Shyamtanan in his talk. So this is the image of UVIT, far UV and near UV together of the atoms for Peace galaxy, which is actually merged. It's a merger remnant. Actually, this galaxy is supposed to have merged, two galaxies have merged together a few 100 million years ago, and this is a merger remnant. But then you can see the tidal tails, and then there are knots on these tidal tails which are forming stars. So we could identify these knots, and we could actually name them and get their fluxes and predict the star formation going on in there. But we could not go beyond that. So it will be ideal to see the kinematics, ideal to see the chemistry of these systems which are forming much outside the galaxy, to understand how these systems can survive, or in what kind of environments these systems are getting formed. So spectroscopy is important, and resolution is also important. And with coming to resolution, the central region of this cluster is shown here. And this is another paper where we realized that there is a star formation thanks to the far UV, near UV minus NUV color actually. You can see that the star formation is going on as a ring, but the central region lacks star formation. Though there's an HST observation of this central region, the HST observations could not reveal the absence of star formation in the central region, because it is a combination of we are not able to say from the flux you get is coming from which kind of stars. But UV, we can clearly say that the flux coming over here in the central region is not from young stars, but from old stars. So we could actually say that there is a suppression of star formation in the central region of this galaxy, which could be due to an AGN effect or AGN negative feedback, or something else. But this is a good correlation to show that there is a negative feedback suppressing the star formation in the central region. So there were some more results were also presented later by Koshy et al. George Koshy et al. So regarding suppression of star formation in the central regions, for which UV is of paramount necessity. Imaging in UV is important. Coming to young stars, we know that the topic of this particular conference is also astrophysical jets. And one of the kind of stars which show a jet phenomena is the young stellar objects. And one of the reasons is that their magnetospheric presence of magnetosphere, and then the material which is coming from the accretion disk goes on to this magnetosphere and then falls onto the star. There could also be some material ejected out through this lines and resulting in the jet phenomena. But in the UV, you will be able to see the magnetospheric accretion, as well as the material, ionized material, as well as shock. So these could be, several things could be modeled here. So if you look at the spectrum, the stellar photosphere gradually falls down and becomes absolutely nil. But in the UV, there is an excess emission coming from heated photosphere. There could also be pre-shock and several other things. So one needs to understand this by looking at several young stellar objects, and then one can actually model it. We did observe some of this T-Tauri stars using UVIT, but using the filter, but we could actually recreate the spectral distribution in the UV and compare it with the stellar spectrum to clearly state that there is an excess, but we are unable to actually say what is the kind of things because we don't have any line information or the exact continuum information. So it is important to have spectral information. So this is very much required, including the emission at 2800, which is the MG2 line emission. So the motivation is to study the LOMAS YSOs to actually model their inner magnetospheric region, which is also paramount interest to understand how the disk get dissipated and the central region very close to the star gets evacuated of the material, an implication to planet formation as well. There are also other science cases, but this one looking at the detection of Lyman continuum at the cosmic noon. And this result was also presented by Shamton in his talk. So this is one of the major results which is coming from UVIT. With moderate resolution and moderate sensitivity, we are able to detect them. With better sensitivity and better resolution, there are a lot more systems like this we'll be able to see, and we'll be able to map the cosmic noon and the star formation history at that period. So what is the landscape of instruments which are going to be available in the next decade to come? So this is the wavelength on the y-axis and the year on the x-axis. So we can see that there are UVOT, UVIT there. Of course, HST is also there, but it has completed a lot of years, and we really do not know how long it is going to stay. But it has got a very small footprint, but it is still producing some amount of UV data. With respect to larger upcoming missions, they are mostly in the optical, near-infrared, and mid-infrared, including a lot of them which are already mentioned in this conference, JWST, TMT, and there are renamed WFIRST and Euclid. The LSST is already started operations, but this will be within this optical and range. UVIT is in place, but we will not know how long it will function, maybe a few more years. And in the upcoming proposed missions, there are only two of them. One is INSIS, the other is CASTOR, which is led by the CSA. So these are of similar missions. And the CASTOR team also presented their proposal during the first meeting. That's the first UVIT science meeting as well. So only these two are the major science programs which are being projected. There are some more projected, but they have not reached the project phase at all as of now. Coming to science goal which were put together,
we looked at subtopics, and each subtopic under there, you can see that several of them are there. So it appears to be wide-ranging science goals. And we also, in the initial phase itself, got the requirement in terms of field of view, the imaging resolution, and the multiplexing of spectroscopy if it is required for a certain number of stars. So this was the kind of table which was arrived at. So which means that there's a wide spectrum of science topics required, more or less having a decent field of view with a very good resolution and moderate resolution spectroscopy with moderate multiplexing. So what is possible for a mission which can be done in the near future was looked into. And the big science questions were segregated into two: imaging, which requires deep imaging and with good resolution, which can take you to high Z universe types, and spectroscopy, which can be done moderately, because this is a kind of a moderately sized mirror if you use. Then spectroscopy with resolution of 1000 will give science results for nearby objects, not very deep objects, but unless its brightness limitation is there. So these are the kind of spectroscopic possibility which can be looked at, like accretion mechanisms, chemical mass assembly of galaxies, chemistry of multiple population in globular clusters, chemical enrichment history of nearby galaxies, and exosphere of giant planets. So these kind of things were proposed together. And then we also had a discussion on operational philosophy. It could be a combination of legacy surveys of a few down select topics, because you can cover and actually do multiple science with a particular set of legacy surveys. And then a guest investigator program with a limited observing time. This is just a beginning. So not that we have finalized everything. So these are the science-driven specifications, and we have put together we had submitted the proposal initially, but then we also have come up with a much refined science proposal with much more details, as well as some of the number estimations as well. So expecting a high resolution imager with a spatial resolution of 0.2 arcsecond with a field of view of half a degree in the wavelength range 150 to 550 nanometer. The wavelength coverage is the 150 to 550 is split into 3 bands: 150 to 300, 300 to 400, and 400 to 550. Now these are done to have a fairly good overlap with the LSST program, because if you have a larger field of view and if you're covering a large part of the sky, then it is very important that this data needs to be combined effectively with LSST program, which is going to throw out a lot of objects in the near future. And this kind of a combination will bring out a lot of science, interesting science cases. And so that is the reason why this is split into this. And we also plan to perform a slitless spectroscopy and UV and U bands. And G band is dedicated for to get the resolution actually. So tracking, etc. So UV and U band will have a slitless spectroscopy for the same imaging field. The resolution will be about 500. The multi-object spectrograph is proposed for a smaller region with a R of 1000 plus, with a multiplexing capability of about 200 plus only in the UV band. The field of view will be similar to the HST, and the sensitivity of 27 MAB at 27 for 1 kilosecond in UV. So if you look at the optical design, which is almost this is done in collaboration with Castro team as well. So we have a 3-mirror assembly here with the primary mirror. It's an astigmatic design, and then off-axis, then the M2, and then the M3, and then you have a fold mirror that is here, and then it is a FSM is here, like it's basically the fine sense guider, where it basically means that if there's a small jitter or drift, it corrects for it and makes it's a live guiding basically. It's like, unlike in the case of UVIT imaging, where we are correcting for the drift offline, there's an online correction, and then comes to fold mirror, and then the back and focal plane. Now, to give you an idea of what exactly the back focal plane looks like, these are the mirrors, and then FSM, and then the fold mirror. Finally, you have the focal plane array, where directly the beam comes to the transmitted beam comes to with a dichroic here. the beam comes to G band. We plan to have a G band imager of 0.5 degree, and then precision photometric field small one, and then imaging for a multi-object field here. And the beam then goes to the reflected beam goes to the UV, where one part is going to the imager, and then a small field goes to the multi-object spectrograph. Then the transmitted beam goes to the U band. So that is the whole layout here. And giving you a picture of how it looks like, the field of view of the main imaging field will be this, the red color over here, and the green will be like the imager, and the G-band precision photometry, and then the blue is for the multi-object spectroscopic field. It's small one. And this is, if you have an array, which is CCD array, which is actually a rectangular with mosaics. But if you have a circular thing, it will be like, you can actually compare the sizes of various missions like this. These are all taken from the detailed science document. This is the central region where this is the HST field. This is the globular cluster, this is the central field of the HST. And then the UVIT field is shown in circle. HST field will be like this. And galaxy is the much bigger field shown here. So the idea is that if these all will be simultaneous, the UV, U, and G band will be simultaneous. This will also be operational. This will also be operational all the time. So if you are going to look at the central part of this galaxy and get high resolution multi-object spectroscopy, then you position, this becomes the center of the field, this comes here, and this red becomes onto the side. So when you are getting a full imaging of this galaxy, then while you're imaging on the outer region of this galaxy, the center can be positioned onto this multi-object spectrograph, and the multi-object spectroscopy of the central region can be obtained. So this is the morphology here. We expect to, this is the kind of a science case for a globular cluster. This is the kind of field of view of an HST. And if you look at, this is the HST image in F275, 3-arc-minute field. You can actually see a number of objects, and these objects we'll be able to pick out each and every object and get the spectrum of each of these objects. So we should be able to do multiplexing within this field. To give another science case, this is the image of NGC 2574 as a irregular galaxy with a high amount of star formation on one end of the galaxy. And this is the region of interest, and it has been studied by HST as well. This is a UVIT image. You can clearly see a number of regions which are having strong star formation. And UVIT was able to pick up these regions with large flux. And if you look at the corresponding HST image in the optical, you can see the clusters out here. But what we plan to do is that we plan to get these isolated, because this is optical, you will get a background from, or rather large age range of stars is seen. But once you have the image in UV, we expect to have only the young stars, OB stars present out there. And then not only identifying these stars, we also plan to get their spectrum taken. So these are simulated spectra. So depending upon the age of the population which is present there, you can actually see the difference in the slope, which can be used to understand the age of these population, and which will give rise to understanding of what is triggering the star formation at the remote end of this galaxy, as well as the age gradient among the sub-regions found within this particular region. And if you have characteristics lines, it will also help us to understand the chemistry of the young star-forming regions. The other science case which is projected is these jellyfish galaxies. This is a case of JO201. And this we will be able to resolve star-forming knots of up to about 0.2 kiloparsec and identify them and take their spectra, because this is a galaxy, or this is a generic kind of a systems where when galaxies fall into large groups, they lose gas. And the star formation happening on the outskirts will be able to tell us the kinematics, the chemistry of these particular regions, and what exactly will happen. The internal kinematics will be able to be resolved. So these are things which are come to the forefront thanks to UVIT imaging with moderate resolution. We are able to understand them, but we expect that
with better resolution and spectroscopic capability, we'll be able to do that. And even with larger field of view or larger cases, the GRISM will be able to help us in at least identifying some important aspects of star formation in large-scale systems. How do we do this for multi-object spectroscopy in a small field with resolution of about 0.2 arcsecond? That is actually a big challenge, because you can't lose lens slits because the sampling size is very, very small. The space available is very, very small. So you're not going to image the 0.2 arcseconds on a larger area where you can put slitlets. So you need to have looking at things like 10 to 20 microns. So in that case, we will not be able to use slitlets. So we are planning to use something called the digital micromirror device. So this device is shown here, is very small thing here. And then this is the readout and other cables connected to the readout chip, etc. So how do they perform? They are like small mirrorlets, and they reflect the mirror, and these can actually turn. You can actually put it in the angles of preference, and when you turn them, the light gets reflected and goes onto one direction, and if you don't turn them, it goes into another direction. So from the same beam which is coming in. So you can actually identify which of these pixelets of this array. You can choose the array by 1K by 1K or something, and then identify which of this IJ pixel is going to be used for spectroscopy, and then that can be this can be programmed to turn the kind of pixels to turn particular angle, and those can be used pass through the spectrograph and a reimaging system to get their spectra. So what you can do is that within a certain row, you can turn only a set of pixels, but each row you will get one particular pixel, and then the perpendicular axis is the dispersion axis. So you can use a column or row, and then the perpendicular will be the resolution axis, dispersion axis. So this is how the multi-object spectroscopy is planned to be carried out. Now we have acquired this DMD controller. This is not flown in any previous missions, but there are several number of tests which are being carried out by various groups, and this is a huge potential to become the way in which we do multi-object spectroscopy in space. So we are carrying out a lot of tests now, and then we have this unit, and we are developing skill sets to program this, and also we are developing a tabletop spectrograph to demonstrate the use, and probably we'll be able to demonstrate in one of the smaller telescopes as well as part of the demonstration. So the current design with respect to the previous design has evolved, and we are planning to have detailed discussion with the mission team to finalize the size, shape, weight, etc. And a in-house team is working on the details of the mechanical design as well. So what is the timeline? So this is something which is projected at the time of the submission of the proposal, but then obviously things will take a longer time than what is projected, especially with COVID hitting us a year ago. So what we are trying to say is that we would need about T0 to 5 years for the entire thing, and a flight model, and 6 years will be required for the entire built up, etc. if we go from start from today. So I just want to have a summary. It's in a nutshell. What has happened so far is the origin of the proposal is the first UVA science meeting in July 2017. The proposal submitted in response to the call for future astronomy missions in January 2018. This was a call was there, and we submitted the proposal in April 2018. And because we started discussing a kind of a proposal from about 6 months back, we actually had built up steam and built up material by then. So it was helpful for us to submit a fairly detailed proposal by then. And there was a subcommittee which was formed by at cost then, to look into all the submitted proposals as mentioned by Dr. Srikumar. And the subcommittee recommended, and the ADCOS recommended us for seed funding by October 2018. We got seed funding by March 2019, and that is when the proposal moved to the pre-project phase. It was also mentioned that we had to talk to Castor mission to figure out whether we would like to go for a joint mission or how we can combine a science cases, etc. So we had a joint meeting with Castor mission in September 2019. The joint mission top-level requirement of optical design was finalized and the workshop had been discussed. So major outcome of this meeting in September 2019 was a decision to go forward together to have a joint mission. Several things had to be understood and several things had to be finalized. So the team started working together since then. We also set up Indian collaborators, and we had several discussions, and we defined roles and responsibilities of the Indian collaborators as well. And after that, we had detailed science document we had several reviews which were going on in between. After the COVID stuck, we used some of this lockdown times to prepare a detailed science document. A detailed document along with certain simulations as well as sensitivity estimations were submitted to ISRO in August 2020. In the meantime, we kept working with the Castor team to finalize the optical design. And CSA, the Canadian Space Agency, sent a letter of interest for collaboration in the project to ISRO in October 2020. And we started working on a detailed India-Canada workshare by November 2020. We had the first CSA ISRO INSYS Castor meeting on 22nd January 2021 with agreement to work together to develop a common mission in the next phase as a workshare document. So workshare document was mostly agreed upon, so we'll develop on that and jointly work together for a common proposal to be submitted to both ISRO and CSA. CSA is investing in a major study this year because their Canadian long-range proposals, that is their equivalent to the decadal survey and decadal report, gave the top priority to Castor in their country, and CSA is willing to invest in it. And as a first step, they are investing in a major study, maturation study, to study particularly those which are part of CSA's contribution to the mission, joint mission. And they expect to go on to the phase 0 later this year. We also held a workshop called UVIT and Beyond as part of the 39th ASI meeting. We had a good response, and a lot of people, we had a lot of interesting discussions and presentations as well. We also had a third review of INSYST on 15th of March, and I think it went quite well, and we look forward to moving into the next phase. I don't know what it is. Maybe it could be called as a phase A thing. So we have completed 2 years of pre-project phase, and we have submitted several documents, and many of the work has progressed. And we are still working on the demonstration of the DMD on the spectrograph in the lab as well as in the, it could be used in the telescope to demonstrate its use. So that's all. This is the INSYS Castor meeting photograph, and thank you for your attention.
Thank you, Annapurni. That was very wonderful talk. Very nice presentation, very lucid presentation. And let us see if there are any queries or comments. Looking at any raises hands.
I guess it's been a long 5-day week, lots and lots of discussions and science and talks, right?
So this Castor was also the similar project, is it? That is folded into now INSYST?
Castor, sorry, let me put it first. Castor is kind of similar, but they had only imaging. And, it is similar design. They were looking for collaboration, and they had partial ability to make, but then they wanted ISRO to collaborate with them on launch and etc.
Okay.
Yeah, but our aim was also to have imaging, but with high resolution, but also spectroscopy.
Is the multiplexing, how much multiplexing you can do? That is number of fibers you can.
Here, yeah. So you can. This is in this particular DMD, this is an array which we are, the number is not yet decided because we are just finalizing the optical design. So I think it will be about 1K by 1K. And depending upon what is the angle it will be falling on a particular pixel. So you can actually do a 2 by 2 or 3 by 3 pixel together to actually capture the footprint of particular star. So this is what I showed here. So you can actually, let's say this is a chip, and this is the kind of image it will fall. So you can actually take these all chips and then say that they turn to one direction. So if you turn to one direction, that will be going through the spectrograph, like I showed here earlier. So this will go to the spectrograph, and that will go to the grating. So like if it's a DMP here, whatever wants to go into the spectrograph will go here, whatever will be thrown out. So these you will get the multi-object spectrograph.
I'm sure this is going to be a game changer in the UV astronomy. Great. There is one question from.
Yeah, I can read that. It will be useful to hear the within India partnership on the developmental efforts, if this has been concluded. Yeah, so it's from Sri Kumar. So we have had one round of discussion prior to that. There will be, I don't quite remember what it is. I'll message it to you, Sri Kumar. I don't quite remember because there are Aries wanted to do something on. There will be collaboration in optics, some amount of mechanical and electronics, and PRL wanted to do something on data pipeline and some amount of electronics as well. And IUCA also taking care of the proposal management system, some amount of electronics, etc. But one of the questions which we are still grappling about is that if the institutions have to share their engineering, technical human resources, then they also need to know the timeline. So within which they have to commit. So this was the same thing which was expressed by TIFR as also. So if we can identify a certain timeline within which their commitment is required, then based on the availability of their resources, they're willing to step in. So this is a chicken and egg problem. So we have to look into it.
Okay. Let's see, is there any raised hands? No. Okay, if there are no questions, let us thank Khandapuni with this wonderful talk. And then also the other previous two talks, let us thank them.
Yeah, thank you.
Thank you, Khandapuni. That was good. And Sissy, are you there? Okay. So you have any announcements to make now? Or?
Not really. I think we are 10 minutes ahead of our 12 minutes ahead of our plan. So I would suggest to include that time into the tea break and let us gather as per the schedule.
Yeah.
So is that fine?
Oh, that's perfect. Perfect. That's good.
All right.
So let us meet at 4:45.
Sure.
Sure. Thank you. Thank you, Shashi. Okay, see you at 4:45.
हमारा वाला चला देख लो तो एक्चुअली सबको देख लो हाँ नहीं ठीक है कोई बात नहीं
Ishwar, can you hear Ishwar? This is Sivrani. Hello.
Shivrani, we are on a break. I think if you're trying to share, I think they have already shared. You have to wait till they unshare or something. It's a tea break. So
I got it. Yes. So
yeah,
Ishwar is the
there.
chair.
No,
right?
no. Sorry, Professor Annapurni, we are here.
Yeah.
Who wants to test?
Shivrani is talking. You can.
Yeah, please share it.
Yeah,
share it.
I'll just try. Okay. Does it come out okay?
Yes.
Okay.
Please, yes, it's moving.
Yeah, okay, thanks.
Yeah, thank you.
Hi, Surani, are you there?
Yeah, yes, sure. I'm there.
So you can't put up your presentation?
I can. You want me to share? I shared and checked it.
You checked it. Okay, that's
yeah.
good. Yeah, I just went for my coffee.
Who gives you coffee at this time? You are at IIA or at home?
At home. Today, since morning, I have these various meetings.
Mm-hmm.
So to come to IIA, then I had to take some 30-40 minutes off, no?
Yeah. Yes.
Yeah, actually, that's what I've been finding. When you have day-long meetings,
yeah,
it's better to be at home itself.
Yeah. Morning, we had this special board meeting.
Oh, okay. Okay. So Shivrani, thanks for those slides.
Yeah, it's again a last minute again. Yeah. But yeah, I think we should follow it up and try to.
Who is saying thanks to whom?
Huh?
Oh, okay.
This is for
what?
No. Who sent slides to whom?
Who sent slides to whom? Yeah, Shivrani gave me some slides.
Oh, on an LOT.
Yes.
How come, Surani, you have TMT slides, not an LOT slide?
Shivrani has everything, don't worry. What you did? Oh, you didn't attend the NLOT meetings, huh? You would have known that she's done that thing, no?
No, I was there.
Throughput calculation and all that, no?
Oh, those slides, okay.
Yeah.
No, I was there. No, it is a nice talk. You, Ram.
Ram's talk was really nice.
Yeah.
And everything was projected, but still, it left you with a very positive feeling.
Yeah.
The way he put it across, no, it was like.
It's a good story.
The feeling has to be always positive.
Yes.
Now positive has a different connotation, Ram.
Yeah. The most negative thing to have today is being positive.
Yeah.
Sorry all for keeping you on hold for this long. We also realized that in this COVID situation, this meeting was rather, I would say, boring and longer. No. I can't say this officially, but somehow COVID situation being rather bad, it got somewhat boring.
So Shashi, go ahead, Ishi.
It's not boring, it's a bit stressful, but then actually we are missing that near your auditorium, coming out and then having coffee. That's another fantastic thing one could experience.
Yeah.
So Shashi, for these online meetings, whole day is a bit stressful because
yes,
people,
it is stressful. I can understand. Yeah.
So maybe half-day meetings are much better suited for these online versions. If you are physically there anyway, you are at a place together. You have breaks. You move around. Now, when you're in office, people often have other things to deal with, and so it's often, and also it's stressful to keep looking at a computer screen and focusing on the talks.
Yeah.
For whole day, there will be emails coming, somebody popping into your office. Anyway, so maybe all this will evolve depending on our time. But maybe a few hours a day is a better format than whole day.
Some people have the multiple meetings on the same computer screen.
Yes.
Yeah.
Not on the same. I have done it with different computers.
But I also realized that it has been a very good summary meeting on this subject area, though it was longer and a bit stressful.
Oh, yeah. But the program is also
will be available.
Nicely done. Very themes properly in a linear fashion. So,
Shashi?
Yeah.
These recordings will be available somewhere?
Yeah, it is all on YouTube uploaded already.
Just send the link.
Ah,
It would be nice to go through them
yes.
at leisure, kind of.
Yeah, if on YouTube, if you simply type Aries Nainital, all 5 of them are popping up as the first 5 videos.
Okay. Okay, that's good. Yeah.
Anyway, I will send you.
Sure.
And we are also planning, with the help of Professor Annaponi, we are planning to summarize some of the talks in one of the special issues of JA. Hopefully, not all, but at least some of them we will try to have in a volume.
What time are we starting? 4:45.
Right.
2 minutes to go.
So Ram, what is the status of the COVID tests at Ayuka?
Yeah, we are having quite a few incidences. About total number of city cases detected so far is close to 35 or something. But out of which only 10 or 11 are people who are resident in campus. The remaining are mostly security people, the cosmetic people, gardeners, people who are coming from outside and doing external work. In that sense, the spread within campus is not an explosive one, but even then 10 people is a large number for a small campus. But fortunately, none of them are these 10 people have all recovered now. I think 1 or 2 may be still remaining in quarantine, but by and large, everybody has recovered. It's all been mild so far, so which is fortunate. There were some people who are on the relatively older side, so we were a bit worried about them, but they are also okay. They have all recovered.
I think it's time now. Surani, maybe you should just share your screen.
Yeah, you can see it.
So again, welcome back to this last talk of this entire wonderful program. And Surani is going to make a presentation on TMT science and instrumentation.
Recording on.
Yeah.
And Surani, you have 45 minutes. I think you are. I don't see gave 5 minutes extra for you.
Yeah, that's nice. Yeah, I would like to thank the organizers.
Please go ahead.
You can hear me well, right?
We can hear you well, but maybe probably just move towards your mic a bit closer.
Okay, is it better?
Now better.
Okay. Yeah. Yeah, I would like to thank the organizers for this opportunity to present the great work which is done by the India TMT team. So I'm presenting on behalf of the team. So these are the partners, both the international and the Indian partners, and the key institutes are IIA, Ayuka, and Aries, TIFR. And so some of these are already covered by Ram. So I just wanted to show for the given size of the primary mirror diameter, the dome is much more compact for TMT, which is kind of helpful in reducing the cost, for example. And another thing also to point out, as you go for larger and larger telescopes, it's become, we are going mostly background limited observations, and AO becomes essential part of large telescopes and to gain the advantage of this. sensitivity advantage of the aperture. And this is the comparison of the optical layouts. So TMT is a RC telescope, whereas GMT is a Gregorian, and ELT has 5 mirror optics that feeds. So in terms of comparison of ELT and TMT, for example, there is the blue sensitivity of TMT is superior, and also ELT is fed by like 30 meter is the kind of an optimal size for fully seeing limited instrumentation within the current technological limitations what we have on the blank optical, for example, calcium fluoride, blank sizes, grating sizes. So 30 meter is kind of an optimal to make a telescope fully seeing limited and take advantage of the blue wavelengths. So, and the TMT is the only telescope which goes up to the atmospheric blue cutoff. So these are some aspects of GMT. And on the, yeah, so on the, in terms of the adaptive optics, TMT also has one of the best performing adaptive optics system, which is called the nefarious. And so if you look at the graph here, you could see the below 1 microns TMT fares better than ELT. And again, it comes from the current technology of as the adaptive optics. We have more sensors and lenslets and more computing powers. Things could be better, but even for TMT, we are still under the current technology is not adequate. And again, to compare TMT with JWST. So in terms of spatial resolution, we have very high spatial resolution. Of course, sensitivity is limited by the ground-based observations because of the background and other absorptions. Yeah, so this is the instrument suite for TMT. So see one part of the one side of the NASMET platform is dedicated for the seeing limited instruments. That's HROS, WFOS, and IRMOS. And the other side is populated with AO, adaptive optics assisted instruments. And nefarious is the adaptive optics facility that feeds up to 3 instruments. And IRIS, currently we have MODIS, which is fed by nefarious. And other instruments like PFS and MICHI, they would have its own adaptive optics system. And the current, the M3, the way M3 is above the primary mirror allows us, like it's an agile telescope. You can move to any instrument and target acquisition can be done within 5 minutes. So this is a comparison of various instruments within GMT and TMT and ELT. And what is underlined are the first light instruments. So the first light instrument for GMT is the GCLIF, which is their stable instrument for GMT. Whereas ELT is focusing on the mid-infrared and IR instruments at the first light. TMT has IRIS, which is AO-assisted imaging and low-resolution spectrograph, like IFS basically, and WFOS, which is a wide-field optical spectrometer. And MODIS is a single object diffractional limit fed by nefarious and high resolution optical spectrograph, infrared spectrograph, which you would see in the next coming slides. So India is significantly contributing to WFOS and also leading HROS and also contributing to some of the other instruments as well. So these are the first light instruments. So I would just quickly go into different instruments just to give a flavor of what's the capability and just summarize give a flavor of the kind of activities which are going on within ITCC. So IRIS is imaging and spectrograph, and it has different spatial scales. and it has various resolutions. And one of the challenge with the IRIS is the adaptive optics is decoupled from the instrument rotators. And also for TMT, we would, to reach the diffraction limit, we also need a atmospheric dispersion corrector. So performance of a atmospheric dispersion corrector is also very challenging, and vibration control and rotators precision. So these are the challenging aspects, along with a huge volume of data, because you have like 10 H4RG detectors for images and 15 H4RG detector for spectroscopy. And this is the optical layout. So the overall, the field, the imaging field is 16.4 by 16.4 field of view. Simultaneously, one can have a imaging as well as spectroscopy. Spectroscopy is done in the central field, and the spectroscopy has several spatial resolution offered by lenslets and slicers. And there are also various different camera which would allow for different spatial scales. And the design is kind of very cleverly made. The slicer and lenslets, which are the complex parts, they don't change. Just switching the collimator, which and the four optics kind of changes the spatial scale, and the detectors and gratings are all common to the spectrographs. So which is kind of, the spectrograph is also common. So it's only the input end changes. So you can, so these are the various observing modes, and there are 37 filters and various gratings. I think there are more than 100 observing modes possible with this instrument. So the spatial sampling is about 4 milliarc seconds in imaging mode, and with the spectrograph, you have 4 to up to 50 milliarc seconds in the case of the slicer, and various resolutions of 4,000 to 10,000 is possible. And so this is kind of to show how the optical train changes. Like you can, as I switch, you can say that the entire optics remains the same, except just moving some stages of the collimators move to get the appropriate spatial scales. Yeah, so coming to the science part. So this is how the lenslet and the slicers reformat the field. And I think most of you are familiar, and the data is a kind of a 3D data cube from which one can construct the images at different wavelengths. So for 0.01 arc seconds, these are the kind of spatial scales one would get at different distances. And this is kind of nice to see when from parsec scales to few kilometers from on the solar system objects, one should be able to do. And again, this is a simulation comparing how Keck and TMT at the galactic center. So there are many more stars which one can resolve in the case of IRIS. And this is again a simulation of the M31. You can see the comparison of HST versus IRIS. And again, another interesting science cases for IRIS is the solar system objects to study volcanism and the bulk density of these objects. And resolved spectroscopy is also another important aspect of science for IRIS. And so one should be able to resolve objects up to Virgo cluster distances, the AGBs and RGBs. And some of the ITCC contribution to IRIS is, like Ram mentioned, Smita Subramaniam has contributed to the IR guide star catalog, which is important for guiding, because guide stars are important for the AO observations. Currently, there are no deep IR catalogs available, so Smita has been working on using the deep optical catalogs to get accurate IR catalogs. So, and another contribution is from Arun Surya. Mostly it is done as part of his postdoc position at the USD, at San Diego, University of California, San Diego. And he has contributed tremendously for this data reduction pipeline. And this pipeline is available in online. It's in GitHub, you can see them. This is based on the JWST Python codes. So it's based on that platform. The entire data reduction is developed. And these are some examples of the simulated raw data and the reduced spectra. And this is again for slices. And he has also worked on this subarray reading for bright objects in the case of when you have crowded objects with a lot of bright sources. And another thing which is also problematic for iris is the diffraction pattern of this lens slits. So he has done some physical optics modeling to reduce the wings contribution to in removing them. So currently it is progressing well. The preliminary design review is in 2021 June. And these are some of the science team members who are part of ITCC. And I'm moving over to WFOSS. WFOSS has evolved in different designs, like from 2005, the designs have evolved into different versions, and up to 2015, this was the old design called MOBI. And this is the current WFOSS 2020 design, where a lot of risks are reduced. Like one of the risks was the flexure compensation, flexure for such a large instrument, because it also has to correct for the field rotation. So current design is a gravity invariant design. So it allows for also articulation of camera. And as you would see in the future, I don't know whether I don't have an optical design, I think. Yeah, so the main characteristics of WFOSS is the resolution of 1500 to 5000. And the field of view is 8.3 by 3 arc minutes. This is the most widest field we have for any ELTs. And it is again slit-based, multi-slit based. So currently the ELT equivalent is a fiber-based spectrograph, which is called Mosaic, and which is probably okay because ELT does not plan to go below 400 nanometers for Mosaic. So these are the sensitivities, what you can see in so continuous coverage of the entire optical. So this is the instrument has two spectrographs, blue and red, and it can have up to 70 slits simultaneously, and in 1500 angstrom, 1500 resolution, one can get the entire optical spectra from 310 to 100 nanometers. But at higher resolution, like 3500 and 5000, you would only get a part of the spectra. So the camera has to be rotated to cover camera, and the grating has to be moved to cover the entire spectral region. So this is the field of view. And so compared to the previous version of WFOSS design, which is off-axis design, this is on-axis, this is telescope optical axis, and it's a on-axis field. And these are the 4 circles so this is the for the auto-guiding and wavefront sensing field, where we have 4 of them to cover at least 2 for a given field. So this also is used for correcting the, so different field, one would have multiple slits. So to align the slit masks, these guide star, the 4 guide stars are used. At least 2 of them should be sufficient to correct for alignment of these slit masks. So one great thing about the WFOSS is the efficiency. Because of the now grating articulation is possible, we have used VPH grating, which has a very high efficiency, and you can see it's 70%. And this is for the lower resolution, and 3500 in 2 settings, you can cover the entire wavelength. And so you can see the peak efficiencies are really good. But one of the issues which is these VPH gratings used sol gel as adhesives, which are thought to be not very good in UV transmission. So there are teams looking at it, but it doesn't look like it's a showstopper. Some of the key sciences are baryonic, the distribution of galaxies and quasars across different redshifts to understand the distribution of baryonic matter. And so this is one of the key science, looking at a different line of sights. So multiplicity is important aspect of WFAS, which would help in this science case. And other science cases are clusters of galaxy clusters, and other interesting science are resolved stellar objects like white dwarfs, and also planetary nebulae. So these are kind of important to get this science case require good sky subtraction. So the WFAS also offers nod and shuffle mode to get sky subtraction up to 0.1%. So these are the various aspects and where different countries are contributing, the partners. And India is contributing to the mechanical design and development of camera rotation system, grating exchange system, and the filter exchange system, and also the complete optomechanical development of the calibration system, and the end-to-end optical simulations, and instrument control software, and also design of this cable wrap and other electrical cabinets. So ARIS also is contributing to significantly for these efforts. I had to remove the good, nice videos which was made by the team on this articulation of various observing modes when the camera rotates, and the grating synchronously they rotate to achieve a different observing mode. So these are done at the ITCC. And these are again various grating exchange systems which were explored in the conceptual design phase 2. Now we are much more firm. So at that time we have tried various possible robotic mechanism and other conventional rotation mechanisms. And now we have narrowed down to using conventional rotation mechanism, which are much simpler. And this is the calibration system. So we have a large, so since we don't have, there is no possibility of taking dome flaps, and if we want to really accurately estimate the slit profile of this multi-slit, the slit mask, which is required for accurate background subtraction. So we have to, as close as possible, mimic the sky illumination. So this is what you see in the box. This is the calibration system. It has an integrating sphere of 2 meters diameter. It's quite huge, and trade studies been made, and various uniformities were checked, and this is all done by ITCC, and also various calibration sources which are needed for achieving calibration exposures within a limited time. So those also have been studied. So this is the current, so the team is expecting a conceptual design review in August, and this is the science team members for WFAS. And this is another third instrument which is the first light instrument. So MODIS. So you can see it's a diffractional. So you can see it's very compact, two spectrographs and bench top. And this is the optical design. So it's a diffraction limited single object spectrograph. So it's more compact. It's a R2 grade, Echelle grating is used, and VPH grisms are used for the cross dispersers, and TMA is used for collimator and the camera. And so the resolution is about 100,000, and it covers Y to Y band, like 0.9 microns to 2.4 microns. And it was because it's a kind of a diffraction limit compact stable spectrograph. So this is one of our stable TMT things. MODIS is their stable spectrograph. For the example, in GMT, their optical spectrograph is designed to have this higher stability, whereas in the case of TMT, MODIS will be the high stability spectrograph, which is kind of suitable for M dwarfs, for example. And one of the challenges is feeding the single mode fiber, so without light losses. So the team is exploring photonic lanterns to feed these fibers. So that design is on the way. Laser combs will be now, it's the kind of standard turnkey mechanism. You can get laser combs. So laser combs will be used for calibrations. So it has three modes of operation, like directly observing the object, and also observing, taking a spectra of exoplanet close to a star by using coronagraph. And also it also has a vertex coronagraph to get much better contrast. So for objects which are within lambda by d, close to lambda by d. So these are a list of science cases: transit spectroscopy and direct spectroscopy and precision RV. These are the main thrust areas. However, stellar physics also can be done, especially galactic center bulges of galaxies. So these are near infrared adaptive optics fed is very suitable for these crowded regions. And then precision RV is also interesting for the cosmology, like physical constant variation across redshifts. So this is just a illustration of how one can see the RV variation in this, in terms of cross correlation function, like how the line shifts when the planet transits. So this has been done for several objects in VL. Right now, it's been done in high resolution spectroscopy already with the high resolution 8 to 10 meter class telescopes. And then coming to the second generation instruments. So these are the second generation instruments which are planned. One is the high resolution optical spectrometer, where India is leading, and other is the planetary imaging spectrograph, where there are three different institutes which are focusing on different modules of the different wavelength region of the instrument. And MICHI is the mid-IR, like a general purpose mid-IR imaging and spectrograph. And near IR mass is still ongoing. The trade studies are being planned. And these instruments, again, there was a committee which looked at optimizing these upcoming instruments for exoplanet studies. So Jeevan, as a SAC member from ITCC, was leading this effort from India. For high resolution HROS, this is the allotted space in the NASMET, and you can see it's like it's 11 by 10 meters and like a basketball court size, and height is about 4 meters. That's the allotted space for HROS. And these are the requirements. One of the requirements is HROS is thought to be like a bad weather instrument, like because any observatory would have significant portion of the time where the seeing is poor and it should be still usable. So HROS is designed to take care of mediocre seeing, so and still keep the full total collecting area, the aperture advantage of TMT. And the expected stability is like 1 meter per second without compromising the nature of HROS as a general purpose instrument. So one of the challenging aspect of HROS is the volume. So Eshel gratings of, this is the size of Eshel gratings, like 1600 by 250 grating. So we need large mosaic gratings. And all the other optics is again really huge. So the team has, so these are various observing modes. So we wanted to make as flexible as possible to, because WFAS, the highest resolution is about 5,000. Maybe it will go up to 8,000. So we want to cover from 8,000 to 100,000. So allow all the possible science cases. So it's flexible enough to cover 20,000 to 100,000 spectral resolution, and also allows for multi-objects. This is still, we are working on it because there are some issues with the feeding of TMT from M3 to the NASMET platform. I'll just explain that. So this is the 4 optics. So from the TMT focal plane, you have the K mirror, which is a derotator of the field, and then the beam is split into 2 blue and red arms. So we have optimized the blue region up to 400 nanometers to kind of use highest blue throughput. So that's the way we have split. And red spectrograph will be a stable spectrograph. So 400 nanometers to 1 micron will be the red spectrograph. And these are various layouts we have tried. And so this is like the US type of layout, and these are different layouts have been tried. So currently we are working with the TMT team to understand what is the allowed field of view possible for HRAS without some of the telescope structure not obstructing the light coming from M3. These are well-known good sciences which can be done by HRAS, that is the variation of fundamental constants, and which requires a wide coverage because you want to look at several multiplets simultaneously to access this. And again, metal poor stars and blue throughput is, so there is a SAC team studied the need for the blue throughput below 0.35 microns, whether it's really essential or how good the science drivers are. And SAC recommended that it's unique for TMT, and TMT HRAS should go till the atmospheric cutoff if possible. So some of the interesting blue science cases are these R process abundances, and these are some of the key elements which can be probed only at which requires both larger aperture as well as high blue throughput. And other interesting HRAS science is the detection of oxygen, and again it's using the radial velocity variation as the planet transit in the front of the star. So which can be seen as a variation in the cross correlation of these like fixed comb of these lines, the molecular lines. So current status is the spectrograph design and the camera designs are complete. So this design has also been reviewed by Bernard Delabre, who is kind of very well known, who designed all the ESO instruments. And he's currently a consultant at TMT. So he reviewed the design and suggested some the optimization. So he was very happy with the way we have split the spectrograph into blue and red. And so currently we are looking at optimizing the camera, allowing some tilts because we have a fixed wavelength format. And other thing is pupil slicing instead of fiber slicing. So that is also being looked at. And the exoplanet team suggested the possibility of getting up to 300,000 for a narrow region close to oxygen. So that is also being looked at. And other instruments is MICHI, it's the mid-infrared imager and spectrograph. It is led by Chris Packham at University of Texas at San Antonio. And so this has various modes, like you can see here. Imager, long slit spectrograph, and high resolution, and IFU, and also polarimetric mode. And ITCC is looking at these polarimetric modes for this Michi instrument. So some of the sciences are this protoplanetary disks, and you can look at the formation of ice lines and different molecules at different distances from the central star. So which is important to understand the formation of both star formation as well as planetary formation. And again, the high resolution also offers transit spectroscopy of these molecular lines, and also possible winds and which are seen in some of the hard Jupiters. So terminator, the shifting of the terminator velocities from zero kind of gives an indicator of the geometry. And this is what is done at VLT CO observations with CRIRIS, and you can see similar thing can be done in much better for with GMT. And this is a comparison of Michi and another planetary system imager instrument. And yeah, so with GMT we get much better resolution compared to JWST, which is though the sensitivity is less. And this is the other second generation instrument, which is called the PSI. So it has a blue arm and red arm. And so it can be, so it has its own adaptive optics system, and also coronagraph and various masks to block the central star. And so currently the red is kind of a standard current wavefront sensing, and the deformable mirror, the technology kind of supports the current PSI red, but whereas the blue is still challenging. The blue goes from 0.6 to 0.95 microns, which is kind of important for reflective, studying the planets which are reflective. They don't have their own self-luminescence planet, so they are not hot. Rocky planets can be studied better with this PSI blue. So, and there are large number of targets which are available for such. So, but the technology is still developing, so it's not very clear. So the PSI next focuses on the PSI red. And so this is a list of various science cases that can be done by PSI red. And the team is also looking at various precursor to this instruments. For example, like MODIS, what we've talked about, it's also the precursor is called high spec for Keck. And similarly, there is also a scales instrument, which is for Keck, which will become the PSI red. So the technology is kind of, the precursors kind of helps in retiring some of these risks. Similarly, there are other techniques which have been developed, especially the photonic lantern feeding and other detector technology, which has been done with other spectrographs. So scales is and high spec, the team, the TMT partners are kind of engaged along with in this precursor instrument as well, especially high spec team, since it's a first generation instrument. And there are partners are part of this science team of this precursor instrument development. In the case of scales, IA is contributing. So they recently got the full funding from Keck also. So IA is contributing to some of the design development, especially the imager filter system and the bench analysis and the calibration system. And so this is the kind of science what you can see. So if when we have the lenslet, so with using lenslets, one can image the object at different wavelengths. So speckles have a different, it has a wavelength dependency, whereas the planets don't. So that can be used to suppress some of these speckle signal. Yeah, thank you. I think I abruptly stopped. Please feel free to ask me any questions.
Thank you, Shivran. That was very nice, detailed talk on TMT instruments. Let us see if there are any questions. Hands raised.
It's the last talk of this long meeting. So
no, but everyone is there on the screen. So, so what is the level of funding they got for scales? This is a KEC funding, no?
Yeah, it is from KEC. Just last week we came to know from them that, yeah.
So that small part of the fund also comes to funds to your team.
Yes, exactly. Especially the expensive part is the H2RG detectors. So they have the new H2RG detector for the imager. So, KEC is planning to replace their NI, like NIRCam, basically, which was used for this galactic center imaging with the new detectors. So scales will have a imager that will replace that as well. So
good, Suran. So there is a question from Sri Kumar. Sri Kumar, are you there? You want to ask the question or?
Yeah. Just a quick question, Shivrani. Thank you. Nice talk. I wanted to ask you on that K mirror that you talked about in the HROS design, right?
Yeah.
Is that the standard 3 mirror reflector system?
Yeah, it is a standard system which has to rotate.
And because you're always adding these additional optical elements is not a concern, I suppose, to cut throughput.
Yeah, so that is, you are quite correct, Srikumar. Like we also, like for example, in the case when we are feeding directly with fiber, we would remove that and allow the fiber to twist. But in the case of slit mode, especially if it's not crowded, we would we can deploy. So we want to keep the K-mirror deployable. So
oh, I see. So you have a system that moves in and out of that beam.
Yeah, like if because when we need the sky subtraction and if it's a crowded field, that is required for signal. Yeah, that's a good point.
Thank you. Nice to see all the involvement from the Indian side. Yeah, thank you.
So,
chat. Who is there in chat?
Chart, there is no.
He already asked the question.
Okay, if there are no further questions on that, let us thank all the speakers of this session, and also thank the organizers and both local and scientific organizing people for putting up the wonderful program. And I think people might have enjoyed all the talks, and so let us applaud them. So Ceci, now over to you, and then I think you are the one who had to take it up now.
Yeah. Thank you very much, Ishwar, for your coordination, and thanks to all the speakers of this afternoon session. Now it's time to summarize things. So on behalf of SOC, it's time to just summarize things, and I have been given the responsibility because I think some of the SOC members might be around. Who all are around? Sudip, Poonam.
Yes. Yeah, that's the participation. And next is.
Yeah. Anyway, so in this pandemic phase, it's quite exciting to see the kind of audience we had and kind of people who participated, registered, and so on. So this is just to summarize that around 230 participants across different institutions, universities, colleges. We counted numbers, and it's roaring around 70. So that's quite exciting to see, including 6 IITs, 3 NITs, around 20 research institutes, and 25 universities, including private sectors. And I was also amazed to see that Sterling Tools Limited, one of the private company, and Delhi Metro people were also registered. I don't know if they attended, but we got registration from there as well. So as we all know, that the workshop was all about astrophysical jets and observational facilities as a national perspective. So only Indians were allowed. And even those Indians who had foreign affiliations, they kindly requested for talks and so on. But SOC decided that only Indian participants with Indian affiliation will speak and participate. So that was the kind of limitation because this Ministry of External Affairs guidelines and so on. So there was some relaxation, but ultimately we decided to follow it up and so on. So it was all about astrophysical jets, which is nothing but the outflows of ionized matter, and it has been seen in several forms, all the way from galactic to extra-galactic objects. In galactic end, we know that microquasars and microblazars, and to gamma ray bursts, and some of the supernovae, and then AGN blazar jets at thousands of millions of light years long across. So the concept came from SOC that from Felix Mirabel and colleagues, there is a concept that if at all we can see unification of the jets, then probably these objects could be understood better for the jets, followed by accretion and so on. And I mean, along those lines, studies are going on, but we decided to have separate days for dedicated for each one of the 3 objects, followed by observational facilities. So we inaugurated the session on 5th of April with the inaugural speech by Professor P.C. Agrawal, one of the founder PIs of the AstroSat, the first Indian multi-wavelength space mission. And in his talk, Professor Agrawal highlighted the importance of multi-wavelength astronomy and the good coordination between space and ground-based astronomy. Followed by that, we had our inaugural talk by Professor Ajit Kembhavi, one of our senior astronomers, and he highlighted the importance of techniques like artificial intelligence, machine learning, deep learning, and so on. And only with these high-level techniques, he highlighted that the importance, without knowledge of these techniques, in future doing astronomy, particularly observational astronomy, would be very difficult. And by taking examples, he really showed that how machine learning and deep learning kind of techniques are useful to decipher whether the object is a star or a galaxy. So unless we really know whether it is a dog or a cat, how we are going to really decide that what kind of science is going to drive those objects and so on. He also mentioned, I like the statement passed by him, that machine learning and AI will not replace scientists, but scientists who know these techniques will replace those scientists who are unaware about these techniques. And that is very, very correct. So we are left with no choice. So the future is, of course, with machine learning and AIs, and all kind of younger generation is kind of encouraged to follow it. Then we started our session with a review talk by Professor K.P. Singh about AGNs, and we all know that AGNs are the legacy subject in India, and Indian astronomers are involved towards AGN science and related astronomy, if I'm not wrong, since last 4 or 5 decades and so on. And along those lines, for jets from active galactic nuclei was covered by Professor K.P. Singh. Then gamma rays and gamma ray flares from relativistic magnetic reconnection in blazar jets was covered by Amit Sukla from IIT Indore. And the things were continued in case of a very particular and very kind of important object in AGN field OJ287. and its multi-wavelength observations and how the supermassive black hole surrounding it might be behaving was covered by Lankeshwar Day. And then Gulab Devangan covered AstroSat series of type 1 AGNs. AstroSat has really contributed significantly towards these areas. And then kiloparsec scale jets in radio galaxies was covered by Dharamveer Lal, followed by Rupajyoti Gogoi, who was talking about the host galaxy morphology of these galaxies and jets surrounding and so on. And then Jahir Shah covered about a particular object where flaring happened in 2017 and how AstroSat observations were there and what kind of things came out. Later on, these things were further covered by about OG 287 by Pankaj Kuswaha and Vaidehi Palia, one of the new faculties at Aries, summarized on the origin of relativistic jets 2021 and beyond in case of AGNs and blazars. And our senior astronomer, Professor Dhruvajyoti DJ Saikia, talked about young radio sources and so on, followed by one of the students, Vineet Oja, where he talked about the internight variability, which have been a program at Aries since last more than a decade and so on, to see that what kind of variability is there among these kind of outflows and jetted blazars and so on. Again, researchers like Pranjupriya Goswami and Suvendu Rakshit again from Aries and Suman Anandi covered from different kind of objects and what kind of GMRT and VLBI observations have told and what we have learned about these parsec scales jets coming out from blazars and AGNs. Then second day was dedicated for the gamma ray burst supernovae and GW candidates. And as mentioned today afternoon by Professor Sri Kumar, that actually the study about gamma ray bursts and the history is very old. And ISRO was the first organization in India with the help of SROS C2 class of satellites, the localization of GRBs were done, where SROS C2 satellites were participated. So long back, their discoveries in the 70s, this area was known among Indian astronomers. And later on, I believe, since last 2 or 3 decades, we have put more time and energy understanding this time domain astronomy area. And if I'm not wrong, then with supernova 1987A was the first object which was followed up in using ground-based facilities in India. And in 1997, optical follow-up observations of GRBs happened. And all the way from SROS C2 to afterglow follow-up to prompt emission observations and prompt emission polarization observations now with AstroSat is the Indian contribution among observational part of gamma ray bursts and other kind of transients. And some sort of theoretical aspects were also covered and started particularly in India by Professor Dipankar Bhattacharya, who started the review talk by telling about physics of gamma ray burst and afterglows and supernovae. And in that talk, he summarized very nicely that how our observational efforts contributed to this field in this country and abroad, and what kind of science prospects are coming up later on by Srihas Tendulkar, one of the very new upcoming emerging areas to understand transients in a larger perspective called FRBs, fast radio burst, was covered by Srihas Tendulkar. And later on, AstroSat observations by prompt emission, polarization and other observations were covered by Shabnam Miani. Untal Misra from Aries covered that how afterglow modeling and energetics of gamma ray bursts are important and how we can contribute better in coming years. Then KG Arun, he covered short duration GRBs and DW events. As we know that short duration GRBs are probably connected with gravitational wave candidates, and 170817 is the object which was a kind of breakthrough. And since then we know a lot that probably some of the GRBs and their electromagnetic counterpart like kilonovae might be connected with the class of GW events, which are of ultimate importance since their serendipitous discovery. And then one of the very specific object where 140102 was covered by Rahul Gupta, and what kind of learnings we have in prompt emission and in afterglow phase. And then Ankur Ghosh and students like Amit Kumar from Aries highlighted about the importance of optical follow-up observations. and particular supernovae called superluminous supernovae, which have been recently catching up, and their connections, possible connections with the FRBs and so on, and being very luminous. These are going to be the prime targets to be understood in future to understand transients in more detail. Then GW prospects of GRBs, SGRBs were covered by Varun Ballerao from IIT Mumbai, and he highlighted about the upcoming missions like Daksha and so on, and how we can contribute better. Then AJ Naina talked about fast blue optical transients, one of the new upcoming transients and very important for future studies and so on. Then Surajit Mandal and other students like Amar Aryan from Aries talked about the core collapse supernovae and publicly available tools like MESA, how we can use using MESA and Stella, how it is possible to understand the progenitors is also a very emerging key areas globally, which is very important to understand supernova progenitors. And then Anjasha Gangopadhyay talked about interacting supernova. Then third day was covered by was dedicated for X-ray binaries and microquasars, and this is another very established area in the country where since last 4 or 5 decades people are working, and in this area was nicely reviewed by Professor Ranjiv Misra about X-ray binaries and microquasars, that what kind of observational facts are there and how actually we are evolving and what kind of theoretical challenges are still remaining. Then jets, outflows, and the spectral states of black hole binaries was covered by Professor Sandeep Chakravarti, where he highlighted about his more than 3 decades of experience and what he has learned and what kind of prospects are still remaining and so on. Then Mayuk Pahadi also covered about the radio jets and its properties in microquasars. Then Aruberi also covered about the fast timing astrosat observations in extra binaries and their multi-wavelength approach. Indranil Chattopadhyay from Aries covered jets around X-ray binaries, and he highlighted that how many kinds of jets are possible in X-ray binaries and how theoretical implications are able to resolve some of the outstanding problems in this area of the research. Then Silpa Sarkar talked about pair production, annihilation, and the accretion disks around black holes, followed by Deepak Devnath, who was talking about accretion ejection properties in short orbital period transient black hole candidates. And then his student Kaushik Chatterjee continued talking about specific objects and the kind of outbursts we observed. In the afternoon session, it was Santavrata Das who talked about role of pseudopotential in studying black holes and X-ray binaries and some of the outstanding theoretical issues in this area. Then Professor J.S. Yadav talked about astrosat, very specific instrument called LAX-PC, and how microquasar studies are being done and what kind of outputs we have got. This was followed by several students and young researchers like Kavita Deka, Sneha Modambi, Malu Sriram, and Indu. They talked about the jets, disk wind oscillations and their properties and what kind of objects, specific objects and their specific properties, which really indicate that how many frontiers are still remaining to be studied in this field. And then fourth day was dedicated for observational facilities, where we existing observational Indian observational facilities and major results. And in this day, we started the day with Professor Jairam Chengalur talking about observational facilities using GMRT, one of the internationally recognized IEEE certified recognized facility, and how we proceeded ahead from GMRT to upgraded GMRT, and then plans are there for eGMRT, that is extended GMRT. And this is all paving a very kind of a path to participate towards projects like SK in future as a mega science. Professor Chengalur highlighted the kind of very path-breaking results which we have obtained at low frequencies using GMRT. The session was followed by Professor Ram Sagar who talked about the 3.6 meter DOT. And in 3.6 meter DOT, he highlighted that what kind of difficulties we had while installing this facility. The India's largest optical facility is now working, and what kind of prospects that we have and instrumentation using which we can really try to have much better science in a multi-wavelength fashion in coming years. And then Professor D.K. Sahu summarized the 2-meter Himalayan Chandra telescope and major results obtained from this facility, all the way from comets to extra-galactic objects. Then our senior astronomer, Professor P.C. Agrawal, talked about AstroSat being one of the founder PIs, and he talked about extra payloads and what kind of results we have got in extra payloads, all the way from binaries to AGNs to magnetars, and the kind of QPO we have discovered at the millisecond level magnetars using AstroSat. And then Professor Syam Tandon talked about UV, one of the first space-based ultraviolet imaging telescope on board AstroSat, and that how we built it and what kind of science that we are doing and we have done using UV, the first ultraviolet space telescope. Then in the afternoon, observational facilities using Cherenkov imaging technique and so on were covered by Dr. K.K. Singh from BARC, and Hager and Pact kind of facilities, gamma ray facilities from TIFR were covered by Varsa Chitnish, and Professor Bhalch and Joshi later on continued the Indian and international pulsar timing array and their implications. Then Professor Sri Anand, by taking example of SALT 10 meter, highlighted that what kind of science could be done and what we have learned and how participating in such large projects could help us to understand science in a better way. And by taking examples of several quasars studies, he highlighted that if at all in future we have our 8 to 10 meter class telescope, or if at all we participate in other facilities, then taking example of SALT, it's a good learning for us that how we can participate and what kind of science could be done. Later on, Professor D.K. Oja nicely covered about ground and space-based infrared instrumentation and facilities where meter class ground-based telescopes have been flown in space using balloon facilities of TIFR, and the kind of the results we are getting is very, very encouraging and very exciting. And later on, he also continued that how these infrared developmental activities and detection and other techniques have been helpful to deploy several instruments all the way from HCT to 3.6 meter DOT. And on the very last day, that is today, here is a slide I borrowed from Professor P. Srikumar's slides, where you can see the x-axis is the time scale and y-axis is the frequency. And this slide is basically prepared by Professor P. Srikumar. He showed around an hour or two back, where you can see that how all the way from radio to cosmic rays, gamma rays, we have facilities. And if you see x-axis 2020, we are somewhere here, and that's where we are planning to have terahertz facilities and upgraded GMRT, expanded GMRT, and then later on followed by participation to SKA. And then if we talk about Venubapu telescope to other 3.6 meter DOT, we have Aditya L1 coming up. For solar study, the NLST is planned, and NLOT, as it was talked by Professor J.C. Anupama. And in X-ray, all the way from AstroSat, now we have ExpoSat, talked in detail by Professor Biswajit Paul, to all the way INSIST, Indian Spectroscopic Imaging Space Telescope, that is 1.2 meter ultraviolet telescope with spectroscopic capabilities, is going to be there in space soon. And with this, we are in really multi-wavelength, multi-messenger astronomy, time domain astronomy era, which is demanded internationally. And tactic, Hager, grapes, of course, we did not cover, but that's another important facility. And now we have MACE, which was talked by KK Singh from BARC. And with MACE, as you can see, that's the third biggest gamma ray facility working at very high energies in gamma rays. So with all the way from MACE to propose Daksha to insist to exoworlds to terahertz mission, we are really full of activities during coming decades or so. And all these other mega projects which we talked about, like TMT by Professor Ram Prakash and SK by Professor Yaswant Gupta, LIGO India by Director Ayuka. As you can see that the timelines are really full, and with all these activities, NLOT coming up, and with CTA probably coming up, we are full with activities, and probably if we keep on working with this pace, then probably 2030, we will be in a condition to do something more relevant or lead something which what other countries are leading, and at the moment we are just partners. So this diagram, I felt like as a very relevant one to show and demonstrate that how it is important for us to go the pace we are moving. And this was one small effort where astrophysical jets and observational facilities in national perspective were discussed in the last 5 days. I hope you might have enjoyed and so on. So with this short summary, now I would like to invite Director Aries, Professor Dipankar Banerjee, to say a few words on this occasion, and as a concluding remarks, please say a few words before I come back and extend my sincere thanks to all the people who helped. So.
Thanks, Shashi. I shouldn't take too long because it's been a long week and it's getting late as well. But I'm very happy to see really a good number of astronomers in the country who are interested in the jets and related science. Incidentally, I just realized that probably I should have also volunteered for a talk, because sun also shows some jets, and solar jets are also important science areas. So probably I missed that in the planning process. I'm really happy to see also this coordination between the different national current facilities and upcoming facilities, because to me actually that's a very important exercise. We are talking about multi-wavelength. So coordination between the ground-based facilities and the space-based facilities, the team able to work at different wavelength, their data processing, data sharing. So this is an element I think we have to also parallelly think about. In fact, I was also thinking that, we are doing this period, a lot of online meetings and workshop, but I think we have to also work out the follow-up of these workshops. I mean, somehow we have to have some activity plans that you have this, shared discussions, which is very nice, a lot of science inputs. But then as action plans, you have to work out what is the, follow-up of, say, coming years. I think that another important exercise which should come out of this workshop. In terms of the data, again, I am a big proponent of open data. At least, even if it is a sort of proprietary data, how you share the data. So in terms of data archiving, because we are really getting into big data. Of course, Ajit did mention in the first talk itself that all these AI ML applications are very important. So how you handle this big data and how you attract the next generation or younger generation into this domain is, I think, a major responsibility. So I think some follow-up actions from these kind of workshops is important. I did attend few talks today from morning. Ram, Anupama, Shomok did point out about this entire, enormous facilities which are coming up. I also appreciate and I strongly believe that participation in the international programs are helping us in building our technological involvement, and subsequently it is allowing us to get into our own national programs. So I think Anupama highlighted this, that how TMT's participation helping us to get into NLOT, for example. And I was quite impressed that that synergy into this. The last point, what I would like to also address is about the student participation. I think Ishwar pointed this out, and Sri Kumar also, highlighted that how important it is that at least the PhD students, how they can be more, involved in these programs. I realized that there is a challenge in terms of the time scale of these projects, because these projects sometimes run for a very extended period of time, whereas the PhD students need to finish their projects within a stipulated time. So how do you match that? And depending on the stage of the project, or the phase of the project, the students find it sort of a bit risky to participate. So that's actually our I think responsibility and challenge, how to compartmentalize these programs. Or so I'm very happy. I run this MTech PhD program, and Aries, we are starting also this MTech PhD program. So that's actually a big avenue to me, because instrumentation sometimes do not demand 10 papers in a PhD period. So I think as organizations or senior members of the different institutions, I think we have to figure it out. I think Ishwar pointed out, Sri Kumar also pointed out, that how do we make that happen, right? The demand for certain number of publications and all that from the system has to be somehow addressed, so that we can attract more number of younger members into these programs. So I think that's all I wanted to convey. I'm very happy that Shashi Alok unfortunately couldn't participate because of his personal crisis, but the way you have structured this different lectures all across the country, at least we had challenges some time back when you started this planning of participation of foreign members, which were relaxed later on, but I think you couldn't sort of venture into that domain. So I'm still happy that even in the national level, it was a very successful workshop. So all the best, and let's hope that this multi-messenger and multi-wavelength venture, including the solar, I saw Sri Kumar always puts these two solar major missions in that graph, and I'm very happy on that. We need to also talk to each other, exchange our ideas in terms of course, the science, the physics, and as well instrumentation. There's a lot of synergy and overlap, so that's very important as well. So thank you very much, and all the best. And Shashi, if you have some last minutes, yeah, go on.
Thank you, sir, for your kind remarks, and the follow-up will definitely be taken care of. And with these things, I will not take much time, but I would definitely like to take some time to say thanks to the Scientific Organizing Committee, including Dr. Alok Gupta, Dr. Gopakumar, Dr. C.S. Stalin, Dr. K.K. Yadav, Dr. Nayantara Gupta, Dr. Poonam Chandra, Dr. Pratik Majmudar, Dr. Ranjiv Misra, Dr. Sudip Bhattacharya, Dr. Sachindra Naik, and Dr. V. Girish for their great contributions to make this program a successful one. And particularly, I'm thankful to the local organizing committee, particularly to our Director Aries for his consistent support to make sure that we are able to host this program here during this pandemic and crisis era, and other committee members of the local organizing committee. Particularly, I would like to all available audience to please clap for Mr. Amar Aryan, particularly. He is my PhD student, and it's just because of his help, consistent help, I was able to kind of coordinate everything. And I'm also thankful. I would also like to take the opportunity to thank all the media people of this local vicinity to be part of this team and continuously kind of publishing these things for common people and school students who are unable to attend colleges due to this pandemic era. I would also like to inform and emphasize and acknowledge here that this program is very much part of the 50 years of Department of Science and Technology being 50 years celebrations. So this program is hosted at Aries as a part of that to commemorate also the Azadi and the 75 years of the freedom, Azadi Ka Amrit Mahotsav by our Honorable Prime Minister. This program was launched recently, and this workshop is very much part of that program, where, as I highlighted in the very beginning, that 230 participants all across the country from 70 institutes have participated, and we have reviewed the subject for the last 5 days. So from astronomy and from all the astronomers of the country, this is one of the programs dedicated for Azadi Ka Amrit Mahotsav. So with this small remarks,
group picture. So
yeah, the group picture.
Whoever is there, if you could just
switch
turn on your
videos. And it's nice to be.
So you can, I think.
It's okay.
Yeah, please.
Well, I can stand close to you.
Yeah. Is that fine?
So, facing towards the camera.
Yeah.
Sure.
Yes, I'll take the screen.
Yeah.
Ready?
Maintain 6 feet, Sasi.
Sorry?
Be away from Dipankar.
Social distancing.
Yeah, social distancing. I took the vaccine yesterday, so I think
tomorrow I am planning to take. Yes.
I hope that is the only connotation there.
We have taken this.
Okay, thank you very much.
All right. Thanks all for your kind support and participation and being available for this session.
Thank you, Sasi.
Bye for now.
Bye.
Bye.
Thanks.
Thank you. Bye-bye.